A type is how Python represents different types of data. In this video, we will discuss some widely used types in Python. You can have different types in Python. They can be integers like 11, real numbers like 21.213. They can even be words. Integers, real numbers, and words can be expressed as different data types. The following chart summarizes 3 data types for the last examples. The first column indicates the expression. The second column indicates the data type. We can see the actual data type in Python by using the type command. We can have int, which stands for an integer, and float, that stands for float, essentially a real number. The type string is a sequence of characters. Here are some integers. Integers can be negative or positive. It should be noted that there is a finite range of integers, but it is quite large. Floats are real numbers. They include the integers but also numbers in between the integers. Consider the numbers between 0 and 1. We can select numbers in between them. These numbers are floats. Similarly, consider the numbers between 0.5 and 0.6. We can select numbers in between them. These are floats as well. We can continue the process, zooming in for different numbers. Of course, there is a limit, but it is quite small. You can change the type of the expression in Python. This is called typecasting. You can convert an int to a float. For example, you can convert or cast the integer 2 to a float 2. Nothing really changes. If you cast a float to an integer, you must be careful. For example, if you cast the float 1.1 to 1, you will lose some information. If a string contains an integer value, you can convert it to int. If we convert a string that contains a non-integer value, we get an error. Check out more examples in the lab. You can convert an int to a string, or a float to a string. Boolean is another important type in Python. A Boolean can take on 2 values. The first value is true. Just remember we use an uppercase T. Boolean values can also be false, with an uppercase F. Using the type command on a Boolean value, we obtain the term bool. This is short for Boolean. If we cast a Boolean true to an integer or float, we will get a 1. If we cast a Boolean false to an integer or float, we get a 0. If you cast a 1 to a Boolean, you get a true. Similarly, if you cast a 0 to a Boolean, you get a false. Check the labs for more examples or check python.org for other kinds of types in Python. In this video, we'll cover expressions and variables. Expressions describe a type of operation that computers perform. Expressions are operations that Python performs. For example, basic arithmetic operations like adding multiple numbers. The result in this case is 160. We call the numbers operands, and the math symbols, in this case addition, are called operators. We can perform operations such as subtraction using the subtraction sign. In this case, the result is a negative number. We can perform multiplication operations using the asterisk. The result is 25. In this case, the operands are given by negative and asterisks. We can also perform division with the forward slash. 25 divided by 5 is 5. 25 divided by 6 is approximately 4.167. In Python 3, the version we will be using in this course, both will result in a float. We can use the double slash for integer division, where the result is rounded. Be aware, in some cases, the results are not the same as regular division. Python follows mathematical conventions when performing mathematical expressions. The following operations are in a different order. In both cases, Python performs multiplication, then addition to obtain the final result. There are a lot more operations you can do with Python. Check the labs for more examples. We will also be covering more complex operations throughout the course. The expressions in the parentheses are performed first. We then multiply the result by 60. The result is 1,920. Now let's look at variables. We can use variables to store values. In this case, we assign a value of 1 to the variable my_variable using the assignment operator, i.e. the equal sign. We can then use the value somewhere else in the code by typing the exact name of the variable. We will use a colon to denote the value of the variable. We can assign a new value to my_variable using the assignment operator. We assign a value of 10. The variable now has a value of 10. The old value of the variable is not important. We can store the results of expressions. For example, we add several values and assign the result to x. X now stores the result. We can also perform operations on x and save the result to a new variable y. Y now has a value of 2.666. We could also perform operations on x and assign the value x. The variable x now has a value 2.666. As before, the old value of x is not important. We can use the type command in variables as well. It's good practice to use meaningful variable names, so you don't have to keep track of what the variable is doing. Let's say we would like to convert the number of minutes in the highlighted examples to number of hours in the following music dataset. We call the variable that contains the total number of minutes total_min. It's common to use the underscore to represent the start of a new word. You can also use a capital letter. We call the variable that contains the total number of hours total_hour. We can obtain the total number of hours by dividing total_min by 60. The result is approximately 2.367 hours. If we modify the value of the first variable, the value of the variable will change. The final result values change accordingly, but we do not have to modify the rest of the code. In Python, a string is a sequence of characters. A string is contained within two quotes. You could also use single quotes. A string can be spaces or digits. A string can also be special characters. We can bind or assign a string to another variable. It is helpful to think of a string as an ordered sequence. Each element in the sequence can be accessed using an index represented by the array of numbers. The first index can be accessed as follows. We can access index 6. Moreover, we can access the 13th index. We can also use negative indexing with strings. The last element is given by the index -1. The first element can be obtained by index -15, and so on. We can bind a string to another variable. It is helpful to think of string as a list or tuple. We can treat the string as a sequence and perform sequence operations. We can also input a stride value as follows. The 2 indicates we'd select every second variable. We can also incorporate slicing. In this case, we return every second value up to index 4. We can use the len command to obtain the length of the string. As there are 15 elements, the result is 15. We can concatenate or combine strings. We use the addition symbols. The result is a new string that is a combination of both. We can replicate values of a string. We simply multiply the string by the number of times we would like to replicate it, in this case 3. The result is a new string. The new string consists of 3 copies of the original string. This means you cannot change the value of the string, but you can create a new string. For example, you can create a new string by setting it to the original variable and concatenate it with a new string. The result is a new string that changes from Michael Jackson to Michael Jackson is the best. Strings are immutable. Backslashes represent the beginning of escape sequences. Escape sequences represent strings that may be difficult to input. For example, \n represent a new line. The output is given by a new line after the \n is encountered. Similarly, \t represents a tab. The output is given by a tab where the \t is. If you want to place a backslash in your string, use a double backslash. The result is a backslash after the escape sequence. We can also place an R in front of the string. Now let's take a look at string methods. Strings are sequences, and, as such, have apply methods that work on lists and tuples. Strings also have a second set of methods that just work on strings. When we apply a method to the string A, we get a new string B that is different from A. Let's do some examples. Let's try with the method upper. This method converts lowercase characters to uppercase characters. In this example, we set the variable a to the following value. We apply the method upper and set it equal to b. The value for b is similar to a, but all the characters are uppercase. The method replaces a segment of the string, i.e., a substring, with a new string. We input the part of the string we would like to change. The second argument is what we would like to exchange the segment with. The result is a new string with the segment changed. The method find finds substrings. The argument is the substring you would like to find. The output is the first index of the sequence. We can find the substring Jack. If the substring is not in the string, the output is -1. Check the labs for more examples. In this video, we will cover lists and tuples. These are called compound data types and are one of the key types of data structures in Python. Tuples. Tuples are an ordered sequence. Here is a tuple ratings. Tuples are expressed as comma-separated elements within parentheses. These are values inside the parentheses. In Python, there are different types: strings, integer, float. They can all be contained in a tuple, but the type of the variable is tuple. Each element of a tuple can be accessed via an index. The following table represents the relationship between the index and the elements in the tuple. The first element can be accessed by the name of the tuple followed by a square bracket with the index number, in this case 0. We can access the second element as follows. We can also access the last element. In Python, we can use negative index. The relationship is as follows. The corresponding values are shown here. We can concatenate or combine tuples by adding them. The result is the following, with the following index. If we would like multiple elements from a tuple, we can also slice tuples. For example, if we want the first 3 elements, we use the following command. The last index is 1 larger than the index you want. Similarly, if we want the last 2 elements, we use the following command. Notice how the last index is 1 larger than the length of the tuple? We can use the len command to obtain the length of a tuple. As there are 5 elements, the result is 5. Tuples are immutable, which means we can't change them. To see why this is important, let's see what happens when we set the variable ratings1 to ratings. Let's use the image to provide a simplified explanation of what's going on. Each variable does not contain a tuple, but references the same immutable tuple object. See the Objects and Classes module for more about objects. Let's say we want to change the element at index 2. Because tuples are immutable, we can't. Therefore, ratings1 will not be affected by a change in rating because the tuple is immutable, i.e., we can't change it. We can assign a different tuple to the ratings variable. The variable ratings now references another tuple. As a consequence of immutability, if we would like to manipulate a tuple, we must create a new tuple instead. For example, if we would like to sort a tuple, we use the function sorted. The input is the original tuple. The output is a new sorted list. For more on functions, see our video on functions. A tuple can contain other tuples as well as other complex data types. This is called nesting. We can access these elements using the standard indexing methods. If we select an index with a tuple, the same index convention applies. As such, we can then access values in the tuple. For example, we could access the second element. We can apply this indexing directly to the tuple variable nt. It is helpful to visualize this as a tree. We can visualize this nesting as a tree. The tuple has the following indexes. If we consider indexes with other tuples, we see the tuple at index 2 contains a tuple with 2 elements. We can access those 2 indexes. The same convention applies to index 3. We can access the elements in those tuples as well. We can continue the process. We can even access deeper levels of the tree by adding another square bracket. We can access different characters in the string or various elements in the second tuple contained in the first. Lists are also a popular data structure in Python. Lists are also an ordered sequence. Here is a list L. A list is represented with square brackets. In many respects, lists are like tuples. One key difference is they are mutable. Lists can contain strings, floats, integers. We can nest other lists. We also nest tuples and other data structures. The same indexing conventions apply for nesting. Like tuples, each element of a list can be accessed via an index. The following table represents the relationship between the index and the elements in the list. The first element can be accessed by the name of the list followed by a square bracket with the index number, in this case 0. We can access the second element as follows. We can also access the last element. In Python, we can use a negative index. The relationship is as follows. The corresponding indexes are as follows. We can also perform slicing in lists. For example, if we want the last two elements in this list, we use the following command. Notice how the last index is one larger than the length of the list? The index conventions for lists and tuples are identical. Check the labs for more examples. We can concatenate or combine lists by adding them. The result is the following. The new list has the following indices. Lists are mutable, therefore we can change them. For example, we apply the method extends by adding a dot followed by the name of the method, then parentheses. The argument inside the parentheses is a new list that we are going to concatenate to the original list. In this case, instead of creating a new list, L1, the original list L is modified by adding two new elements. To learn more about methods, check out our video on objects and classes. Another similar method is append. If we apply append instead of extended, we add one element to the list. If we look at the index, there is only one more element. Index 3 contains the list we appended. Every time we apply a method, the list changes. If we apply extend, we add two new elements to the list. The list L is modified by adding two new elements. If we append the string A, we further change the list, adding the string A. As lists are mutable, we can change them. For example, we can change the first element as follows. The list now becomes hard rock 10, 1.2. We can delete an element of a list using the del command. We simply indicate the list item we would like to remove as an argument. For example, if we would like to remove the first element, the result becomes 10, 1.2. We can delete the second element. This operation removes the second element of the list. We can convert a string to a list using split. For example, the method split converts every group of characters separated by a space into an element of a list. We can use the split function to separate strings on a specific character, known as a delimiter. We simply pass the delimiter we would like to split on as an argument, in this case a comma. The result is a list. Each element corresponds to a set of characters that have been separated by a comma. When we set one variable, b equal to a, both a and b are referencing the same list. Multiple names referring to the same object is known as aliasing. We know from the list slide that the first element in b is set as hard rock. If we change the first element in A to banana, we get a side effect. The value of B will change as a consequence. A and B are referencing the same list. Therefore, if we change A, list B also changes. If we check the first element of B after changing list A, we get banana instead of hard rock. You can clone list A by using the following syntax. Variable A references one list. Variable B references a new copy or clone of the original list. Now, if you change A, B will not change. We can get more info on list, tuples, and many other objects in Python using the help command. Simply pass in the list, tuple, or any other Python object. See the labs for more things you can do with lists. Let's cover dictionaries in Python. Dictionaries are a type of collection in Python. If you recall, a list has integer indexes. These are like addresses. A list also has elements. A dictionary has keys and values. The key is analogous to the index. They are like addresses, but they don't have to be integers. They are usually characters. The values are similar to the element in a list and contain information. To create a dictionary, we use curly brackets. The keys are the first elements. They must be immutable and unique. Each key is followed by a value separated by a colon. The values can be immutable, mutable, and duplicates. Each key and value pair is separated by a comma. Consider the following example of a dictionary. The album title is the key and the value is the release data. We can use yellow to highlight the keys and leave the values in white. It is helpful to use the table to visualize a dictionary, where the first column represents the keys and the second column represents the values. We can add a few more examples to the dictionary. We can also assign the dictionary to a variable. The key is used to look up the value. We use square brackets. The argument is the key. This outputs the value. Using the key of back in black, this returns the value of 1980. The key the dark side of the moon gives us the value of 1973. Using the key the bodyguard gives us the value 1992, and so on. We can add a new entry to the dictionary as follows. This will add the value 2007 with a new key called graduation. We can delete an entry as follows. This gets rid of the key thriller and its value. We can verify if an element is in the dictionary using the in command as follows. The command checks the keys. If they are in the dictionary, they return a true. If we try the same command with a key that is not in the dictionary, we get a false. In order to see all the keys in a dictionary, we can use the method keys to get the keys. The output is a list-like object with all the keys. In the same way, we can obtain the values using the method values. Check out the labs for more examples and info on dictionaries. Let's cover sets. They are also a type of collection. Sets are a type of collection. This means that like lists and tuples, you can input different Python types. Unlike lists and tuples, they are unordered. This means sets do not record element position. Sets only have unique elements. This means there is only one of a particular element in a set. To define a set, you use curly brackets. You place the elements of a set within the curly brackets. You notice there are duplicate items. When the actual set is created, duplicate items will not be present. You can convert a list to a set by using the function set. This is called typecasting. You simply use the list as the input to the function set. The result will be a list converted to a set. Let's go over an example. We start off with a list. We input the list to the function set. The function set returns a set. Notice how there are no duplicate elements. Let's go over set operations. These can be used to change the set. Consider the set A. Let's represent this set with a circle. If you are familiar with sets, this can be part of a Venn diagram. A Venn diagram is a tool that uses shapes usually to represent sets. We can add an item to a set using the add method. We just put the set name followed by a dot, then the add method. The argument is the new element of the set we would like to add. In this case, in sync. The set A now has in sync as an item. If we add the same item twice, nothing will happen as there can be no duplicates in a set. Let's say we would like to remove in sync from set A. We can also remove an item from a set using the remove method. We just put the set name followed by a dot, then the remove method. The argument is the element of the set we would like to remove. In this case, in sync. After the remove method is applied to the set, set A does not contain the item in sync. You can use this method for any item in the set. We can verify if an element is in the set using the in command as follows. The command checks if the item, in this case AC/DC, is in the set. If the item is in the set, it returns true. If we look for an item that is not in the set, in this case for the item who, As the item is not in the set, we will get a false. These are types of mathematical set operations. There are other operations we can do. There are lots of useful mathematical operations we can do between sets. Let's define the set album set 1. We can represent it using a red circle or Venn diagram. Similarly, we can define the set album set 2. We can also represent it using a blue circle or Venn diagram. The intersection of two sets is a new set containing elements which are in both of those sets. It's helpful to use Venn diagrams. The two circles that represent the sets combine. The overlap represents the new set. As the overlap is comprised of the red circle and blue circle, we define the intersection in terms of AND. In Python, we use an ampersand to find the intersection of two sets. If we overlay the values of the set over the circle, placing the common elements in the overlapping area, we see the correspondence. After applying the intersection operation, all the items that are not in both sets disappear. In Python, we simply just place the ampersand between the two sets. We see that both AC/DC and Back in Black are in both sets. The result is a new set album, set 3, containing all the elements in both album set 1 and album set 2. The union of two sets is the new set of elements which contain all the items in both sets. We can find the union of the sets, album set 1 and album set 2, as follows. The result is a new set that has all the elements of album set 1 and album set 2. This new set is represented in green. Consider the new album set 3. The set contains the elements AC/DC and Back in Black. We can represent this with a Venn diagram, as all the elements in album set 3 are in album set 1. The circle representing album set 1 encapsulates the circle representing album set 3. We can check if a set is a subset using the isSubset method. As album set 3 is a subset of the album set 1, the result is true. There is a lot more you can do with sets. Check out the lab for more examples. In this video, you will learn about conditions and branching. Comparison operations compare some value or operand. Then, based on some condition, they produce a Boolean. Let's say we assign a value of a to 6. We can use the equality operator denoted with two equal signs to determine if two values are equal. In this case, if 7 is equal to 6. In this case, as 6 is not equal to 7, the result is false. If we performed an equality test for the value 6, the two values would be equal. As a result, we would get a true. Consider the following equality comparison operator. If the value of the left operand, in this case the variable, I, is greater than the value of the right operand, in this case 5, the condition becomes true, or else we get a false. Let's display some values for I on the left. Let's see the values greater than 5 in green and the rest in red. If we set I equal to 6, we see that 6 is larger than 5, and as a result, we get a true. We can also apply the same operations to floats. If we modify the operator as follows, if the left operand I is greater than or equal to the value of the right operand, in this case 5, then the condition becomes true. In this case, we include the value of 5 in the number line, and the color changes to green accordingly. If we set the value of I equal to 5, the operand will produce a true. If we set the value of I to 2, we would get a false because 2 is less than 5. We can change the inequality. If the value of the left operand, in this case I, is less than the value of the right operand, in this case 6, then condition becomes true. Again, we can represent this with a colored number line. The areas where the inequality is true are marked in green, and red where the inequality is false. If the value for I is set to 2, the result is a true, as 2 is less than 6. The inequality test uses an exclamation mark preceding the equal sign. If two operands are not equal, then the condition becomes true. We can use a number line. When the condition is true, the corresponding numbers are marked in green and red for where the condition is false. If we set I equal to 2, the operator is true as 2 is not equal to 6. We compare strings as well. Comparing AC/DC and Michael Jackson using the equality test, we get a false, as the strings are not the same. Using the inequality test, we get a true, as the strings are different. See the labs for more examples. Branching allows us to run different statements for a different input. It's helpful to think of an if statement as a locked room. If the statement is true, you can enter the room, and your program can run some predefined task. If the statement is false, your program will skip the task. For example, consider the blue rectangle representing an AC/DC concert. If the individual is 18 or older, they can enter the AC/DC concert. If they are under the age of 18, they cannot enter the concert. Individual proceeds to the concert. Their age is 17, therefore they are not granted access to the concert, and they must move on. If the individual is 19, the condition is true. They can enter the concert. Then they can move on. This is the syntax of the if statement from our previous example. We have the if statement. We have the expression that can be true or false. The brackets are not necessary. We have a colon. Within an indent, we have the expression that is run if the condition is true. The statements after the if statement will run regardless if the condition is true or false. For the case where the age is 17, we set the value of the variable age to 17. We check the if statement. The statement is false. Therefore, the program will not execute the statement to print "you will enter." In this case, it will just print "move on." For the case where the age is 19, we set the value of the variable age to 19. We check the if statement. The statement is true. Therefore, the program will execute the statement to print "you will enter." Then it will just print "move on." The else statement will run a different block of code if the same condition is false. Let's use the AC/DC concert analogy again. If the user is 17, they cannot go to the AC/DC concert, but they can go to the Meatloaf concert represented by the purple square. If the individual is 19, the condition is true. They can enter the AC/DC concert. Then they can move on as before. The syntax of the else statement is similar. We simply append the statement else. We then add the expression we would like to execute with an indent. For the case where the age is 17, we set the value of the variable age to 17. We check the if statement. The statement is false. Therefore, we progress to the else statement. We run the statement in the indent. This corresponds to the individual attending the Meatloaf concert. The program will then continue running. For the case where the age is 19, we set the value of the variable age to 19. We check the if statement. The statement is true. Therefore, the program will execute the statement to print "you will enter." The program skips the expressions in the else statement and continues to run the rest of the expressions. The elif statement, short for else if, allows us to check additional conditions if the preceding condition is false. If the condition is true, the alternate expressions will be run. Consider the concert example. If the individual is 18, they will go to the Pink Floyd concert instead of attending the AC/DC or Meatloaf concerts. The person of 18 years of age enters the area as they are not over 19 years of age. They cannot see AC/DC, but as they are 18 years, they attend Pink Floyd. After seeing Pink Floyd, they move on. The syntax of the elif statement is similar. We simply add the statement elif with the condition. We then add the expression we would like to execute if the statement is true, with an indent. Let's illustrate the code on the left. An 18-year-old enters. They are not older than 18 years of age. Therefore, the condition is false. So the condition of the elif statement is checked. The condition is true. So then we would print "go see Pink Floyd." Then we would move on, as before. If the variable age was 17, the statement "go see Meatloaf" would print. Similarly, if the age was greater than 18, the statement "you can enter" would print. Check the labs for more examples. Now let's take a look at logic operators. Logic operations take Boolean values and produce different Boolean values. The first operation is the not operator. If the input is true, the result is a false. Similarly, if the input is false, the result is a true. Let A and B represent Boolean variables. The OR operator takes in the two values and produces a new Boolean value. We can use this table to represent the different values. The first column represents the possible values of A. The second column represents the possible values of B. The final column represents the result of applying the OR operation. We see the OR operator only produces a false if all the Boolean values are false. The following lines of code will print out. This album was made in the 70s or 90s, if the variable album year does not fall in the 80s. Let's see what happens when we set the album year to 1990. The colored number line is green when the condition is true, and red when the condition is false. In this case, the condition is false. Examining the second condition, we see that 1990 is greater than 1989, so the condition is true. We can verify by examining the corresponding second number line. In the final number line, the green region indicates where the area is true. This region corresponds to where at least one statement is true. We see that 1990 falls in the area. Therefore, we execute the statement. Let A and B represent Boolean variables. The AND operator takes in the two values and produces a new Boolean value. We can use this table to represent the different values. The first column represents the possible values of A. The second column represents the possible values of B. The final column represents the result of applying the AND operation. We see the AND operator only produces a true if all the Boolean values are true. The following lines of code will print out. This album was made in the 80s if the variable album year is between 1980 and 1989. Let's see what happens when we set the album year to 1983. As before, we can use the colored number line to examine where the condition is true. In this case, 1983 is larger than 1980, so the condition is true. Examining the second condition, we see that 1990 is greater than 1983, so this condition is also true. We can verify by examining the corresponding second number line. In the final number line, the green region indicates where the area is true. Similarly, this region corresponds to where both statements are true. We see that 1983 falls in the area. Therefore, we execute the statement. Branching allows us to run different statements for different inputs. In this video, we will cover loops, in particular for loops and while loops. We will use many visual examples in this video. See the labs for examples with data. Before we talk about loops, let's go over the range function. The range function outputs an ordered sequence as a list I. If the input is a positive integer, the output is a sequence. The sequence contains the same number of elements as the input, but starts at 0. For example, if the input is 3, the output is the sequence 0, 1, 2.
If the range function has two inputs, where the first input is smaller than the second input, the output is a sequence that starts at the first input.
Then the sequence iterates up to, but not including the second number. For the input 10 and 15, we get the following sequence. See the labs for more capabilities of the range function. Please note, if you use Python 3, the range function will not generate a list explicitly like in Python 2. In this section, we will cover for loops. We will focus on lists, but many of the procedures can be used on tuples. Loops perform a task over and over. Consider the group of colored squares. Let's say we would like to replace each colored square with a white square. Let's give each square a number to make things a little easier and refer to all the group of squares as squares. If we wanted to tell someone to replace square 0 with a white square, we would say equals replace square 0 with a white square. Or we can say for square 0 in squares, square 0 equals white square. Similarly, for the next square, we can say for square 1 in squares, square 1 equals white square. For the next square, we can say for square 2 in squares, square 2 equals white square. We repeat the process for each square. The only thing that changes is the index of the square we are referring to. If we are going to perform a similar task in Python, we cannot use actual squares. So let's use a list to represent the boxes. Each element in the list is a string representing the color. We want to change the name of the color in each element to white. Each element in the list has the following index. This is a syntax to perform a loop in Python. Notice the indent. The range function generates a list. The code will simply repeat everything in the indent 5 times. If you were to change the value to 6, it would do it 6 times. However, the value of I is incremented by 1 each time. In this segment, we change the ith element of the list to the string white. The value of I is set to 0. Each iteration of the loop starts at the beginning of the indent. We then run everything in the indent. The first element in the list is set to white. We then go to the start of the indent. We progress down each line. When we reach the line to change the value of the list, we set the value of index 1 to white. The value of I increases by 1. We repeat the process for index 2. The process continues for the next index until we have reached the final element. We can also iterate through a list or tuple directly in Python. We do not even need to use indices. Here is the list squares. Each iteration of the list we pass one element of the list squares to the variable square. Let's display the value of the variable square on this section. For the first iteration, the value of square is red. We then start the second iteration. For the second iteration, the value of square is yellow. We then start the third iteration. For the final iteration, the value of square is green. A useful function for iterating data is enumerate. It can be used to obtain the index and the element in the list. Let's use the box analogy with the numbers representing the index of each square. This is the syntax to iterate through a list and provide the index of each element. We use the list squares and use the names of the colors to represent the colored squares. The argument of the function enumerate is the list, in this case squares. The variable I is the index, and the variable square is the corresponding element in the list. Let's use the left part of the screen to display the different values of the variable square, and I for the various iterations of the loop. For the first iteration, the value of the variable is red, corresponding to the 0th index, and the value for I is 0. For the second iteration, the value of the variable square is yellow, and the value of I corresponds to its index, i.e. 1. We repeat the process for the last index. While loops are similar to for loops, but instead of executing a statement a set number of times, a while loop will only run if a condition is met. Let's say we would like to copy all the orange squares from the list squares to the list new squares, but we would like to stop if we encounter a non-orange square. We don't know the value of the squares beforehand. We would simply continue the process while the square is orange, or see if the square equals orange. If not, we would stop. For the first example, we would check if the square was orange. It satisfies the condition, so we would copy the square. We repeat the process for the second square. The condition is met, so we copy the square. In the next iteration, we encounter a purple square. The condition is not met, so we stop the process. This is essentially what a while loop does. Let's use the figure on the left to represent the code. We will use a list with the names of the color to represent the different squares. We create an empty list of new squares. In reality, the list is of indeterminate size. We start the index at 0. The while statement will repeatedly execute the statements within the indent until the condition inside the bracket is false. We append the value of the first element of the list squares to the list new squares. We increase the value of I by 1. We append the value of the second element of the list squares to the list new squares. We increment the value of I. Now the value in the array squares is purple. Therefore, the condition for the while statement is false, and we exit the loop. Check out the labs for more examples of loop, many with real data. In this video, we will cover functions. You will learn how to use some of Python's built-in functions as well as how to build your own function. Functions take some input, then produce some output or change. The function is just a piece of code you can reuse. You can implement your own function, but in many cases you use other people's functions. In this case, you just have to know how the function works, and in some cases, how to import the functions. Let the orange and yellow squares represent similar blocks of code. We can run the code using some input and get an output. If we define a function to do the task, we just have to call the function. Let the small squares represent the lines of code used to call the function. We can replace these long lines of code by just calling the function a few times. Now we can just call the function. Our code is much shorter. The code performs the same task. You can think of the process like this. When we call the function f1, we pass an input to the function. These values are passed to all those lines of code you wrote. This returns a value. You can use the value. For example, you can input this value to a new function, f2. When we call this new function f2, the value is passed to another set of lines of code. The function returns a value. The process is repeated, passing the values to the function you call. You can save these functions and reuse them, or use other people's functions. Python has many built-in functions. You don't have to know how those functions work internally, but simply what task those functions perform. The function len takes in an input of type sequence, such as a string or list, or type collection, such as a dictionary or set, and returns the length of that sequence or collection. Consider the following list. The len function takes this list as an argument, and we assign the result to the variable L. The function determines there are 8 items in the list, then returns the length of the list, in this case 8. The function sum takes in an iterable like a tuple or list and returns the total of all the elements. Consider the following list. We pass the list into the sum function and assign the result to the variable s. The function determines the total of all the elements, then returns it. In this case, the value is 70. There are 2 ways to sort a list. The first is using the function sorted. We can also use the list method sort. Methods are similar to functions. Let's use this as an example to illustrate the difference. The function sorted returns a new sorted list or tuple. Consider the list album ratings. We can apply the function sorted to the list album ratings and get a new list sorted album rating. The result is a new sorted list. If we look at the list album ratings, nothing has changed. Generally, functions take an input, in this case a list. They produce a new output, in this instance a sorted list. If we use the method sort, the list album ratings will change and no new list will be created. Let's use the diagram to help illustrate the process. In this case, the rectangle represents the list album ratings. When we apply the method sort to the list album rating changes. Unlike the previous case, we see that the list album rating has changed. In this case, no new list is created. Now that we've gone over how to use functions in Python, let's see how to build our own functions. We will now get you started on building your own functions in Python. This is an example of a function in Python that returns its input value +1. To define a function, we start with the keyword def. The name of the function should be descriptive of what it does. We have the function formal parameter a in parentheses, followed by a colon. We have a code block with an indent. For this case, we add 1 to a and assign it to b. We return or output the value for b. After we define the function, we can call it. The function will add 1 to 5 and return a 6. We can call the function again, this time assign it to the variable c. The value for c is 11. Let's explore this further. Let's go over an example when you call a function. It should be noted that this is a simplified model of Python, and Python does not work like this under the hood. We call the function giving it an input 5. It helps to think of the value of 5 as being passed to the function. Now the sequences of commands are run. The value of a is 5. B would be assigned a value of 6. We then return the value of b. In this case, as b was assigned a value of 6, the function returns a 6. If we call the function again, the process starts from scratch. We pass in an 8. The subsequent operations are performed. Everything that happened the last call will happen again with a different value of a. The function returns a value, in this case 9. Again, this is just a helpful analogy. Let's try and make this function more complex. It's customary to document the function on the first few lines. This tells anyone who uses the function what it does. This documentation is surrounded in triple quotes. You can use the help command on the function to display the documentation as follows. This will print out the function name and the documentation. We will not include the documentation in the rest of the examples. A function can have multiple parameters. The function mult multiplies two numbers. In other words, it finds their product. If we pass the integers 2 and 3, the result is a new integer. If we pass the integer 10 and the float 3.14, the result is a float 31.4. If we pass in the integer 2 and the string Michael Jackson, the string Michael Jackson is repeated 2 times. This is because the multiplication symbol can also mean repeat a sequence. If you accidentally multiply an integer with a string instead of 2 integers, you won't get an error. Instead, you will get a string, and your program will progress, potentially failing later because you have a string where you expected an integer. This property will make coding simpler, but you must test your code more thoroughly. In many cases, a function does not have a return statement. In these cases, Python will return the special none object. Practically speaking, if your function has no return statement, you can treat it as if the function returns nothing at all. The function mj simply prints the name Michael Jackson. We call the function. The function prints Michael Jackson. Let's define the function noWork that performs no task. Python doesn't allow a function to have an empty body, so we can use the keyword pass, which doesn't do anything but satisfies the requirement of a non-empty body. If we call the function and print it out, the function returns a none. In the background, if the return statement is not called, Python will automatically return a none. It is helpful to view the function noWork with the following return statement. Usually functions perform more than one task. This function prints a statement, then returns a value. Let's use this table to represent the different values as the function is called. We call the function with an input of 2. We find the value of b. The function prints the statement with the value of a and b. Finally, the function returns the value of b, in this case 3. We can use loops in functions. This function prints out the values and indexes of a loop or tuple. We call the function with the list album ratings as an input. Let's display the list on the right with its corresponding index. Stuff is used as an input to the function enumerate. This operation will pass the index to I and the value in the list to S. The function would begin to iterate through the loop. The function will print the first index and the first value in the list. We continue iterating through the loop. The values of I and S are updated. The print statement is reached. Similarly, the next values of the list and index are printed. The process is repeated. The values of I and S are updated. We continue iterating until the final values in the list are printed out. Variadic parameters allow us to input a variable number of elements. Consider the following function. The function has an asterisk on the parameter names. When we call the function, 3 parameters are packed into the tuple names. We then iterate through the loop. The values are printed out accordingly. If we call the same function with only 2 parameters as inputs, the variable names only contain 2 elements. The result is only 2 values are printed out. The scope of a variable is the part of the program where that variable is accessible. Variables that are defined outside of any function are said to be within the global scope, meaning they can be accessed anywhere after they are defined. Here we have a function that adds the string DC to the parameter x. When we reach the part where the value of x is set to AC, this is within the global scope, meaning x is accessible anywhere after it is defined. A variable defined in the global scope is called a global variable. When we call the function, we enter a new scope or the scope of addDC. We pass as an argument to the addDC function, in this case AC. Within the scope of the function, the value of x is set to ACDC. The function returns the value and is assigned to z. Within the global scope, the value z is set to ACDC. After the value is returned, the scope of the function is deleted. Local variables only exist within the scope of a function. Consider the function thriller. The local variable date is set to 1982. When we call the function, we create a new scope. Within that scope of the function, the value of the date is set to 1982. The value of date does not exist within the global scope. Variables inside the global scope can have the same name as variables in the local scope, with no conflict. Consider the function thriller. The local variable date is set to 1982. The global variable date is set to 2017. When we call the function, we create a new scope. Within that scope, the value of the date is set to 1982. If we call the function, it returns the value of date in the local scope, in this case 1982. When we print in the global scope, we use the global variable value. The global value of the variable is 2017. Therefore, the value is set to 2017. If a variable is not defined within a function, Python will check the global scope. Consider the function ACDC. The function has the variable rating with no value assigned. If we define the variable rating in the global scope, then call the function, Python will see there is no value for the variable rating. As a result, Python will leave the scope and check if the variable ratings exists in the global scope. It will use the value of ratings in the global scope within the scope of ACDC. In the function, we'll print out a 9. The value of z in the global scope will be 10, as we added 1. The value of rating will be unchanged within the global scope. Consider the function Pink Floyd. If we define the variable claimed sales with the keyword global, the variable will be a global variable. We call the function Pink Floyd. The variable claimed sales is set to the string 45 million in the global scope. When we print the variable, we get a value of 45 million. There is a lot more you can do with functions. Check out the lab for more examples.
Hello and welcome to Exception Handling. After watching this video, you will be able to explain exception handling, demonstrate the use of exception handling, and understand the basics of exception handling. Have you ever mistakenly entered a number when you were supposed to enter text in an input field? Most of us have, either in error or when testing out a program. But do you know why it gave an error message instead of completing and terminating the program? In order for the error message to appear, an event was triggered in the background. This event was activated because the program tried to perform a computation on the name entry and realized the entry contained numbers and not letters. By encasing this code in an exception handler, the program knew how to deal with this type of error and was able to output the error message to continue with the program. This is one of many errors that can happen when asking for user input. So let us see how exception handling works. We will first explore the try except statement. This type of statement will first attempt to execute the code in the try block, but if an error occurs, it will kick out and begin searching for the exception that matches the error. Once it finds the correct exception to handle the error, it will then execute that line of code. For example, perhaps you are writing a program that will open and write a file. After starting the program, an error occurred as the data was not able to be read. Because of this error, the program skipped over the code lines under the try statement and went directly to the exception line. Since this error fell within the I/O error guidelines, it printed unable to open or read the data in the file to our console. When writing simple programs, we can sometimes get away with only one except statement. But what happens if another error occurs that is not caught by the I/O error? If that happened, we would need to add another except statement. For this except statement, you will notice that the type of error to catch is not specified. While this may seem a logical step so the program will catch all errors and not terminate, this is not a best practice. For example, perhaps our small program was just one section of a much larger program that was over 1,000 lines of code. Our task was to debug the program as it kept throwing an error causing a disruption for our users. When investigating the program, you found this error kept appearing. Because this error had no details, you ended up spending hours trying to pinpoint and fix the error. So far in our program, we have defined that an error message should print out if an error occurs, but we do not receive any messages that the program executed properly. This is where we can now add an else statement to give us that notification. By adding this else statement, it will provide us a notification to the console that the file was written successfully. Now that we have defined what will happen if our program executes properly, or if an error occurs, there is one last statement to add. For this example, since we are opening a file, the last thing we need to do is close the file. By adding a finally statement, it will tell the program to close the file no matter the end result, and print "File is now closed" to our console. In this video, you learned how to write a try except statement, why it is important to always define errors when creating exceptions, and how to add an else and finally statement.
In this module, we are going to talk about objects and classes. Python has many different kinds of data types: integers, floats, strings, lists, dictionaries, booleans. In Python, each is an object. Every object has the following: a type, internal representation, a set of functions called methods to interact with the data. An object is an instance of a particular type. For example, we have two types, type 1 and type 2. We can have several objects of type 1 as shown in yellow. Each object is an instance of type 1. We also have several objects of type 2 shown in green. Each object is an instance of type 2. Let's do several less abstract examples. Every time we create an integer, we are creating an instance of type integer, or we are creating an integer object. In this case, we are creating 5 instances of type integer or 5 integer objects. Similarly, every time we create a list, we are creating an instance of type list, or we are creating a list object. In this case, we are creating 5 instances of type list or 5 list objects. We can find out the type of an object by using the type command. In this case, we have an object of type list. We have an object of type integer. We have an object of type string. Finally, we have an object of type dictionary. A class or type's methods are functions that every instance of that class or type provides. It's how you interact with the object. We have been using methods all this time, for example, on lists. Sorting is an example of a method that interacts with the data in the object. Consider the list ratings. The data is a series of numbers contained within the list. The method sort will change the data within the object. We call the method by adding a period at the end of the object's name, and the method's name we would like to call with parentheses. We have the ratings list represented in orange. The data contained in the list is a sequence of numbers. We call the sort method. This changes the data contained in the object. You can say it changes the state of the object. We can call the reverse method on the list, changing the list again. We call the method reversing the order of the sequence within the object. In many cases, you don't have to know the inner workings of the class and its methods. You just have to know how to use them. Next, we will cover how to construct your own classes. You can create your own type or class in Python. In this section, you will create a class. The class has data attributes. The class has methods. We then create instances of that class or objects. The class data attributes define the class. Let's create two classes. The first class will be a circle. The second will be a rectangle. Let's think about what constitutes a circle. Examining this image, all we need is a radius to define a circle, and let's add color to make it easier to distinguish between different instances of the class later. Therefore, our class data attributes are radius and color. Similarly, examining the image in order to define a rectangle, we need the height and width. We will also add color to distinguish between instances later. Therefore, the data attributes are color, height, and width. To create the class circle, you will need to include the class definition. This tells Python you are creating your own class, the name of the class. For this course, in parentheses, you will always place the term object. This is the parent of the class. For the class rectangle, we change the name of the class, but the rest is kept the same. Classes are outlines we have to set the attributes to create objects. We can create an object that is an instance of type circle. The color data attribute is red, and the data attribute radius is 4. We can also create a second object that is an instance of type circle. In this case, the color data attribute is green, and the data attribute radius is 2. We can also create an object that is an instance of type rectangle. The color data attribute is blue, and the data attribute of height and width is 2. The second object is also an instance of type rectangle. In this case, the color data attribute is yellow, and the height is 1, and the width is 3. We now have different objects of class circle or type circle. We also have different objects of class rectangle or type rectangle. Let us continue building the circle class in Python. We define our class. We then initialize each instance of the class with data attributes, radius, and color using the class constructor. The function init is a constructor. It's a special function that tells Python you are making a new class. There are other special functions in Python to make more complex classes. The radius and color parameters are used to initialize the radius and color data attributes of the class instance. The self parameter refers to the newly created instance of the class. The parameters radius and color can be used in the constructor's body to access the values passed to the class constructor when the class is constructed. We can set the value of the radius and color data attributes to the values passed to the constructor method. Similarly, we can define the class rectangle in Python. The name of the class is different. This time, the class data attributes are color, height, and width. After we have created the class, in order to create an object of class circle, we introduce a variable. This will be the name of the object. We create the object by using the object constructor. The object constructor consists of the name of the class, as well as the parameters. These are the data attributes. When we create a circle object, we call the code like a function. The arguments passed to the circle constructor are used to initialize the data attributes of the newly created circle instance. It is helpful to think of self as a box that contains all the data attributes of the object. Typing the object's name followed by a dot and the data attribute name gives us the data attribute value, for example, radius. In this case, the radius is 10. We can do the same for color. We can see the relationship between the self parameter and the object. In Python, we can also set or change the data attribute directly, typing the object's name followed by a dot and the data attribute name, and set it equal to the corresponding value. We can verify that the color data attribute has changed. Usually, in order to change the data in an object, we define methods in the class. Let's discuss methods. We have seen how data attributes consist of the data defining the objects. Methods are functions that interact and change the data attributes, changing or using the data attributes of the object. Let's say we would like to change the size of a circle. This involves changing the radius attribute. We add a method addRadius to the class circle. The method is a function that requires the self as well as other parameters. In this case, we are going to add a value to the radius. We denote that value as r. We are going to add r to the data attribute radius. Let's see how this part of the code works when we create an object and call the addRadius method. As before, we create an object with the object constructor. We pass 2 arguments to the constructor. The radius is set to 2 and the color is set to red. In the constructor's body, the data attributes are set. We can use the box analogy to see the current state of the object. We call the method by adding a dot followed by the method name in parentheses. In this case, the argument of the function is the amount we would like to add. We do not need to worry about the self parameter when calling the method. Just like with the constructor, Python will take care of that for us. In many cases, there may not be any parameters other than self specified in the method's definition, so we don't pass any arguments when calling the function. Internally, the method is called with a value of 8 and the proper self object. The method assigns a new value to self.radius. This changes the object, in particular the radius data attribute. When we call the addRadius method, this changes the object by changing the value of the radius data attribute. We can add default values to the parameters of a class's constructor. In the labs, we also create the method called drawCircle. See the lab for the implementation of drawCircle. In the labs, we can create a new object of type circle using the constructor. The color will be red and the radius will be 3. We can access the data attribute radius. We can access the attribute color. Finally, we can use the method drawCircle to draw the circle. Similarly, we can create a new object of type circle. We can access the data attribute of radius. We can access the data attribute color. We can use the method drawCircle to draw the circle. In summary, we have created an object of class circle called redCircle with a radius attribute of 3 and a color attribute of red. We also created an object of class circle called blueCircle with a radius attribute of 10 and a color attribute of blue. In the lab, we have a similar class for rectangle. We can create a new object of type rectangle using the constructor. We can access a data attribute of height. We can also access the data attribute of width. We can do the same for the data attribute of color. We can use the method drawRectangle to draw the rectangle. So we have a class, an object that is a realization or instantiation of that class. For example, we can create 2 objects of class circle or 2 objects of class rectangle. The dir function is useful for obtaining the list of data attributes and methods associated with a class. The object you're interested in is passed as an argument. The return value is a list of that object's data attributes. The attributes surrounded by underscores are for internal use, and you shouldn't have to worry about them. The regular-looking attributes are the ones you should concern yourself with. These are the object's methods and data attributes. There is a lot more you can do with objects in Python. Check python.org for more info. In this section, we will use Python's built-in open function to create a file object and obtain the data from a txt file. We will use Python's open function to get a file object. We can apply a method to that object to read data from the file. We can open the file example1.txt as follows. We use the open function. The first argument is the file path. This is made up of the file name and the file directory. The second parameter is the mode. Common values used include R for reading, W for writing, and A for appending. We will use R for reading. Finally, we have the file object. We can now use the file object to obtain information about the file. We can use the data attribute name to get the name of the file. The result is a string that contains the name of the file. We can see what mode the object is in using the data attribute mode, and R is shown representing read. You should always close the file object using the method close. This may get tedious sometimes, so let's use the with statement. Using a with statement to open the file is better practice because it automatically closes the file. The code will run everything in the indent block, then closes the file. This code reads the file example1.txt. We can use the file object file1. The code will perform all operations in the indent block, then close the file at the end of the indent. The method read stores the values of the file in the variable file_stuff as a string. You can print the file content. You can check if the file content is closed but you cannot read from it outside the indent. But you can print the file content outside the indent as well. We can print the file content. We will see the following. When we examine the raw string, we will see the /n. This is so Python knows to start a new line. We can output every line as an element in a list using the method readLines. The first line corresponds to the first element in the list. The second line corresponds to the second element in the list, and so on. We can use the method readLine to read the first line of the file. If we run this command, it will store the first line in the variable file_stuff, then print the first line. We can use the method readLine twice. The first time it's called, it will save the first line in the variable file_stuff, and then print the first line. The second time it's called, it will save the second line in the variable file_stuff, and then print the second line. We can use a loop to print out each line individually as follows. Let's represent every character in a string as a grid. We can specify the number of characters we would like to read from a string as an argument to the method readLines. When we use a 4 as an argument in the method readLines, we print out the first 4 characters in the file. Each time we call the method, we will progress through the text. If we call the method with the argument 16, the first 16 characters are printed out and then the new line. If we call the method a second time, the next 5 characters are printed out. Finally, if we call the method the last time with the argument 9, the last 9 characters are printed out. Check out the labs for more examples of methods and other file types. We can also write to files using the open function. We will use Python's open function to get a file object, to create a text file. We can apply method write to write data to that file. As a result, text will be written to the file. We can create the file example2.txt as follows. We use the open function. The first argument is the file path. This is made up of the file name. If you have that file in your directory, it will be overwritten, and the file directory. We set the mode parameter to W for writing. Finally, we have the file object. As before, we use the with statement. The code will run everything in the indent block, then close the file. We create the file object, file1. We use the open function. This creates a file example2.txt in your directory. We use the method write to write data into the file. The argument is the text we would like input into the file. If we use the write method successively, each time it's called, it will write to the file. The first time it is called, we will write, "This is line A" with a /n to represent a new line. The second time we call the method, it will write, "This is line B," then it will close the file. We can write each element in a list to a file. As before, we use a with command and the open function to create a file. The list lines has 3 elements consisting of text. We use a for loop to read each element of the first lines and pass it to the variable line. The first iteration of the loop writes the first element of the list to the file example2. The second iteration writes the second element of the list, and so on. At the end of the loop, the file will be closed. We can set the mode to appended using a lowercase a. This will not create a new file, but just use the existing file. If we call the method write, it will just write to the existing file, then add, "This is line C," then close the file. We can copy one file to a new file as follows. First, we read the file example1 and interact with it via the file object, readFile. Then we create a new file example3 and use the file object, writeFile to interact with it. The for loop takes a line from the file object, readFile, and stores it in the file example3 using the file object, writeFile. The first iteration copies the first line. The second iteration copies the second line till the end of the file is reached. Then both files are closed. Check out the labs for more examples. Dependencies or libraries are pre-written code to help solve problems. In this video, we will introduce pandas, a popular library for data analysis. We can import the library or a dependency like pandas using the following command. We start with the import command, followed by the name of the library. We now have access to a large number of pre-built classes and functions. This assumes the library is installed. In our lab environment, all the necessary libraries are installed. Let's say we would like to load a CSV file using the pandas built-in function, read CSV. A CSV is a typical file type used to store data. We simply type the word pandas, then a dot and the name of the function with all the inputs. Typing pandas all the time may get tedious. We can use the as statement to shorten the name of the library. In this case, we use the standard abbreviation PD. Now we type PD and a dot followed by the name of the function we would like to use. In this case, read_CSV. We are not limited to the abbreviation PD. In this case, we use the term banana. We will stick with PD for the rest of this video. Let's examine this code more in depth. One way pandas allows you to work with data is with a data frame. Let's go over the process to go from a CSV file to a data frame. This variable stores the path of the CSV. It is used as an argument to the read_CSV function. The result is stored to the variable df. This is short for data frame. Now that we have the data in a data frame, we can work with it. We can use the method head to examine the first 5 rows of a data frame. The process for loading an Excel file is similar. We use the path of the Excel file. The function reads Excel. The result is a data frame. A data frame is comprised of rows and columns. We can create a data frame out of a dictionary. The keys correspond to the column labels. The values are lists corresponding to the rows. We then cast the dictionary to a data frame using the function DataFrame. We can see the direct correspondence between the table. The keys correspond to the table headers. The values are lists corresponding to the rows. We can create a new data frame consisting of one column. We just put the data frame name, in this case DF, and the name of the column header enclosed in double brackets. The result is a new data frame comprised of the original column. You can do the same thing for multiple columns. We just put the data frame name, in this case DF, and the name of the multiple column headers enclosed in double brackets. The result is a new data frame comprised of the specified columns. When we have a data frame, we can work with the data and save the results in other formats. Consider the stack of 13 blocks of different colors. We can see there are 3 unique colors. Let's say you would like to find out how many unique elements are in a column of a data frame. This may be much more difficult because instead of 13 elements, you may have millions. Pandas has the method unique to determine the unique elements in a column of a data frame. Let's say we would like to determine the unique year of the albums in the data set. We enter the name of the data frame, then enter the name of the column released within brackets. Then we apply the method unique. The result is all of the unique elements in the column released. Let's say we would like to create a new database consisting of songs from the 1980s and after. We can look at the column released for songs made after 1979, then select the corresponding rows. We can accomplish this within one line of code in pandas, but let's break up the steps. We can use the inequality operators for the entire data frame in pandas. The result is a series of Boolean values. For our case, we simply specify the column released and the inequality for the albums after 1979. The result is a series of Boolean values. The result is true when the condition is true and false otherwise. We can select the specified columns in one line. We simply use the data frame's names, and in square brackets we place the previously mentioned inequality and assign it to the variable df1. We now have a new data frame, where each album was released after 1979. We can save the new data frame using the method to_CSV. The argument is the name of the CSV file. Make sure you include a .csv extension. There are other functions to save the data frame in other formats. In this video, we will be covering NumPy in 1D, in particular ND arrays. NumPy is a library for scientific computing. It has many useful functions. There are many other advantages like speed and memory. NumPy is also the basis for pandas, so check out our pandas video. In this video, we will be covering the basics and array creation, indexing and slicing, basic operations, universal functions. Let's go over how to create a NumPy array. A Python list is a container that allows you to store and access data. Each element is associated with an index. We can access each element using a square bracket as follows. A NumPy array, or ND array, is similar to a list. It's usually fixed in size, and each element is of the same type, in this case integers. We can cast a list to a NumPy array by first importing NumPy. We then cast the list as follows. We can access the data via an index. As with the lists, we can access each element with an integer and a square bracket. The value of A is stored as follows. If we check the type of the array, we get numpy.ndArray. As NumPy arrays contain data of the same type, we can use the attribute dType to obtain the data type of the array's elements. In this case, a 64-bit integer. Let's review some basic array attributes using the array A. The attribute size is the number of elements in the array. As there are 5 elements, the result is 5. The next two attributes will make more sense when we get to higher dimensions, but let's review them. The attribute ndim represents the number of array dimensions or the rank of the array, in this case 1. The attribute shape is a tuple of integers indicating the size of the array in each dimension. We can create a NumPy array with real numbers. When we check the type of the array, we get numpy.ndArray. If we examine the attribute dType, we see float64 as the elements are not integers. There are many other attributes. Check out numpy.org. Let's review some indexing and slicing methods. We can change the first element of the array to 100 as follows. The array's first value is now 100. We can change the fifth element of the array as follows. The fifth element is now 0. Like lists and tuples, we can slice a NumPy array. The elements of the array correspond to the following index. We can select the elements from 1 to 3 and assign it to a new NumPy array, D, as follows. The elements in D correspond to the index. Like lists, we do not count the element corresponding to the last index. We can assign the corresponding indices to new values as follows. The array C now has new values. See the labs or numpy.org for more examples of what you can do with NumPy. NumPy makes it easier to do many operations that are commonly performed in data science. These same operations are usually computationally faster and require less memory in NumPy compared to regular Python. Let's review some of these operations on one-dimensional arrays. We will look at many of the operations in the context of Euclidean vectors to make things more interesting. Vector addition is a widely used operation in data science. Consider the vector u with 2 elements. The elements are distinguished by the different colors. Similarly, consider the vector v with 2 components. In vector addition, we create a new vector, in this case z. The first component of z is the addition of the first component of vectors u and v. Similarly, the second component is the sum of the second components of u and v. This new vector z is now a linear combination of the vector u and v. Representing vector addition with line segment or arrows is helpful. The first vector is represented in red. The vector will point in the direction of the 2 components. The first component of the vector is 1. As a result, the arrow is offset 1 unit from the origin in the horizontal direction. The second component is 0. We represent this component in the vertical direction. As this component is 0, the vector does not point in the vertical direction. We represent the second vector in blue. The first component is 0, therefore the arrow does not point to the horizontal direction. The second component is 1. As a result, the vector points in the vertical direction 1 unit. When we add the vector u and v, we get the new vector z. We add the first component. This corresponds to the horizontal direction. We also add the second component. It's helpful to use the tip-to-tail method when adding vectors, placing the tail of a vector v on the tip of vector u. The new vector z is constructed by connecting the base of the first vector u with the tail of the second v. The following 3 lines of code will add the 2 lists and place the result in the list z. We can also perform vector addition with 1 line of NumPy code. It would require multiple lines to perform vector subtraction on 2 lists as shown on the right side of the screen. In addition, the NumPy code will run much faster. This is important if you have lots of data. We can also perform vector subtraction by changing the addition sign to a subtraction sign. It would require multiple lines to perform vector subtraction on 2 lists, as shown on the right side of the screen. Vector multiplication with a scalar is another commonly performed operation. Consider the vector y. Each component is specified by a different color. We simply multiply the vector by a scalar value, in this case 2. Each component of the vector is multiplied by 2. In this case, each component is doubled. We can use the line segment or arrows to visualize what's going on. The original vector y is in purple. After multiplying it by a scalar value of 2, the vector is stretched out by 2 units, as shown in red. The new vector is twice as long in each direction. Vector multiplication with a scalar only requires 1 line of code using NumPy. It would require multiple lines to perform the same task as shown with Python lists as shown on the right side of the screen. In addition, the operation would also be much slower. Hadamard product is another widely used operation in data science. Consider the following 2 vectors, u and v. The Hadamard product of u and v is a new vector z. The first component of z is the product of the first element of u and v. Similarly, the second component is the product of the second element of u and v. The resultant vector consists of the entry-wise product of u and v. We can also perform Hadamard product with 1 line of code in NumPy. It would require multiple lines to perform Hadamard product on 2 lists as shown on the right side of the screen. The dot product is another widely used operation in data science. Consider the vector u and v. The dot product is a single number given by the following term and represents how similar 2 vectors are. We multiply the first component from v and u. We then multiply the second component and add the result together. The result is a number that represents how similar the 2 vectors are. We can also perform dot product using the NumPy function dot and assign it with the variable result as follows. Consider the array u. The array contains the following elements. If we add a scalar value to the array, NumPy will add that value to each element. This property is known as broadcasting. A universal function is a function that operates on ND arrays. We can apply a universal function to a NumPy array. Consider the arrays A. We can calculate the mean or average value of all the elements in A using the method mean. This corresponds to the average of all the elements. In this case, the result is 0. There are many other functions. For example, consider the NumPy arrays B. We can find the maximum value using the method 5. We see the largest value is 5. Therefore, the method max returns a 5. We can use NumPy to create functions that map NumPy arrays to new NumPy arrays. Let's implement some code on the left side of the screen and use the right side of the screen to demonstrate what's going on. We can access the value of pi in NumPy as follows. We can create the following NumPy array in radians. This array corresponds to the following vector. We can apply the function sign to the array x and assign the values to the array y. This applies the sign function to each element in the array. This corresponds to applying the sign function to each component of the vector. The result is a new array y, where each value corresponds to a sign function being applied to each element in the array x. A useful function for plotting mathematical functions is line space. Line space returns evenly spaced numbers over a specified interval. We specify the starting point of the sequence, the ending point of the sequence. The parameter num indicates the number of samples to generate. In this case, 5. The space between samples is 1. If we change the parameter num to 9, we get 9 evenly spaced numbers over the interval from -2 to 2. The result is the difference between subsequent samples is 0.5 as opposed to 1 as before. We can use the function linespace to generate 100 evenly spaced samples from the interval 0 to 2π. We can use the NumPy function sign to map the array x to a new array y. We can import the library pyplot as plt to help us plot the function. As we are using a Jupyter notebook, we use the command matplotlib inline to display the plot. The following command plots a graph. The first input corresponds to the values for the horizontal or x-axis. The second input corresponds to the values for the vertical or y-axis. There's a lot more you can do with NumPy. Check out the labs at numpy.org for more. Thanks for watching this video. We can create NumPy arrays with more than one dimension. This section will focus only on 2D arrays, but you can use NumPy to build arrays of much higher dimensions. In this video, we will cover the basics and array creation in 2D, indexing and slicing in 2D, and basic operations in 2D. Consider the list A. The list contains 3 nested lists, each of equal size. Each list is color-coded for simplicity. We can cast the list to a NumPy array as follows. It is helpful to visualize the NumPy array as a rectangular array. Each nested list corresponds to a different row of the matrix. We can use the attribute ndim to obtain the number of axes or dimensions referred to as the rank. The term rank does not refer to the number of linearly independent columns like a matrix. It's useful to think of ndim as the number of nested lists. The first list represents the first dimension. This list contains another set of lists. This represents the second dimension or axes. The number of lists the list contains does not have to do with the dimension, but the shape of the list. As with the 1D array, the attribute shape returns a tuple. It's helpful to use the rectangular representation as well. The first element in the tuple corresponds to the number of nested lists contained in the original list or the number of rows in the rectangular representation, in this case 3. The second element corresponds to the size of each of the nested lists, or the number of columns in the rectangular array 0. The convention is to label this axis 0 and this axis 1 as follows. We can also use the attribute size to get the size of the array. We see there are 3 rows and 3 columns. Multiplying the number of columns and rows together, we get the total number of elements, in this case 9. Check out the labs for arrays of different shapes and other attributes. We can use rectangular brackets to access the different elements of the array. The following image demonstrates the relationship between the indexing conventions for the list like representation. The index in the first bracket corresponds to the different nested lists, each a different color. The second bracket corresponds to the index of a particular element within the nested list. Using the rectangular representation, the first index corresponds to the row index. The second index corresponds to the column index. We can also use a single bracket to access the elements as follows. Consider the following syntax. This index corresponds to the second row, and this index the third column. The value is 23. Consider this example. This index corresponds to the first row, and the second index corresponds to the first column, and a value of 11. We can also use slicing in NumPy arrays. The first index corresponds to the first row. The second index accesses the first 2 columns. Consider this example. The first index corresponds to the first 2 rows. The second index accesses the last column. We can also add arrays. The process is identical to matrix addition. Consider the matrix X. Each element is colored differently. Consider the matrix Y. Similarly, each element is colored differently. We can add the matrices. This corresponds to adding the elements in the same position, i.e. adding elements contained in the same color boxes together. The result is a new matrix that is the same size as matrix Y or X. Each element in this new matrix is the sum of the corresponding elements in X and Y. To add two arrays in NumPy, we define the array, in this case, X. Then we define the second array, Y. We add the arrays. The result is identical to matrix addition. Multiplying a NumPy array by a scalar is identical to multiplying a matrix by a scalar. Consider the matrix Y. If we multiply the matrix by the scalar 2, we simply multiply every element in the matrix by 2. The result is a new matrix of the same size where each element is multiplied by 2. Consider the array Y. We first define the array. We multiply the array by a scalar as follows and assign it to the variable z. The result is a new array where each element is multiplied by 2. Multiplication of two arrays corresponds to an element Y's product or Hadamard product. Consider array X and array Y. Hadamard product corresponds to multiplying each of the elements in the same position, i.e. multiplying elements contained in the same color boxes together. The result is a new matrix that is the same size as matrix Y or X. Each element in this new matrix is the product of the corresponding elements in X and Y. Consider the array X and Y. We can find the products of two arrays X and Y in one line and assign it to the variable z as follows. The result is identical to Hadamard product. We can also perform matrix multiplication with NumPy arrays. Matrix multiplication is a little more complex, but let's provide a basic overview. Consider the matrix A, where each row is a different color. Also, consider the matrix B, where each column is a different color. In linear algebra, before we multiply matrix A by matrix B, we must make sure that the number of columns in matrix A, in this case 3, is equal to the number of rows in matrix B, in this case 3. For matrix multiplication, to obtain the ith row and jth column of the new matrix, we take the dot product of the ith row of A with the jth columns of B. For the first column, first row, we take the dot product of the first row of A with the first column of B as follows. The result is 0. For the first row and the second column of the new matrix, we take the dot product of the first row of the matrix A, but this time we use the second column of matrix B. The result is 2. For the second row and the first column of the new matrix, we take the dot product of the second row of the matrix A with the first column of matrix B. The result is 0. Finally, for the second row and the second column of the new matrix, we take the dot product of the second row of the matrix A with the second column of matrix B. The result is 2. In NumPy, we can define the NumPy arrays A and B. We can perform matrix multiplication and assign it to array C. The result is the array C. It corresponds to the matrix multiplication of array A and B. There is a lot more you can do with it in NumPy. Check out numpy.org. Thanks for watching this video.
In this video, we will discuss Application Program Interfaces, or APIs for short. Specifically, we will discuss what an API is, API libraries, and REST APIs, including request and response, and an example with PyCoin Gecko. An API lets two pieces of software talk to each other. For example, you have your program, you have some data, and you have other software components. You use the API to communicate with other software via inputs and outputs. Just like a function, you don't have to know how the API works, just its inputs and outputs. Pandas is actually a set of software components, much of which are not even written in Python. You have some data, you have a set of software components. We use the Pandas API to process the data by communicating with the other software components. Let us clean up the diagram. When you create a dictionary, then create a Pandas object with the data frame constructor, in API lingo, this is an instance. The data in the dictionary is passed along to the pandas API. You then use the data frame to communicate with the API. When you call the method head, the data frame communicates with the API displaying the first few rows of the data frame. When you call the method mean, the API will calculate the mean and return the values. REST APIs are another popular type of API. They allow you to communicate through the internet, letting you take advantage of resources like storage, access more data, artificial intelligence algorithms, and much more. The RE stands for representational, the S for state, and T for transfer. In REST APIs, your program is called the client. The API communicates with a web service you call through the internet. There is a set of rules regarding communication: input or request, and output or response. Here are some common terms. You or your code can be thought of as a client. The web service is referred to as a resource. The client finds the service via an endpoint. We will review this more in the next section. The client sends requests to the resource and the response to the client. HTTP methods are a way of transmitting data over the internet. We tell the REST APIs what to do by sending a request. The request is usually communicated via an HTTP message. The HTTP message usually contains a JSON file. This contains instructions for what operation we would like the service to perform. This operation is transmitted to the web service via the internet, and the service performs the operation. In a similar manner, the web service returns a response via an HTTP message where the information is usually returned via a JSON file, and this information is transmitted back to the client. Cryptocurrency data is excellent to use in an API because it is constantly updated and is vital to cryptocurrency trading. We will use the PyCoinGecko Python client or wrapper for the CoinGecko API, updated every minute by CoinGecko. We use the wrapper or client because it is easy to use so you can focus on the task of collecting data. We will also introduce pandas time series functions for dealing with time series data. Using PyCoinGecko to collect data is simple. All we need is to install and import the library, then create a client object, and finally use a function to request our data. In this function, we are getting data on Bitcoin in US dollars for the past 30 days. In this case, our response is a JSON file expressed as a Python dictionary of nested lists, including price, market cap, and total volumes, which contain the Unix timestamp and the price at the time. We are only interested in price, so that is what we will select using the key price. To make things simple, we can convert our nested list to a data frame. With the column's timestamp and price, it is difficult to understand the column timestamp. We will convert it to a more readable format using the pandas function to_datetime. Using this to_datetime function, we create readable time data. The input is the timestamp column. Unit of time is set to milliseconds. We append the output to the new column date. Now we want to create a candlestick plot. To get the data for the daily candlesticks, we will group by the date to find the minimum, maximum, first, and last price of each day. Finally, we will use Plotly to create the candlestick chart and plot it. Now we can view the candlestick chart by opening the HTML file and clicking Trust HTML in the top left of the tab. It should look something like this.
In this video, we will discuss application program interfaces that use some kind of artificial intelligence. We will transcribe an audio file using the Watson Text-to-Speech API. We will then translate the text to a new language using the Watson Language Translator API. In the API call, you will send a copy of the audio file to the API. This is sometimes called a POST request. Then the API will send the text transcription of what the individual is saying. Under the hood, the API is making a GET request. We then send the text we would like to translate into a second language to a second API. The API will translate the text and send the translation back to you. In this case, we translate English to Spanish. We then provide an overview of API keys and endpoints, Watson Speech to Text, and Watson Translate. First, we will review API keys and endpoints. They will give you access to the API. An API key is a way to access the API. It's a unique set of characters that the API uses to identify you and authorize you. Usually your first call to the API includes the API key. This will allow you access to the API. In many APIs, you may get charged for each call, so like your password, you should keep your API key a secret. An endpoint is simply the location of the service. It's used to find the API on the internet, just like a web address. Now we will transcribe an audio file using the Watson Text-to-Speech API. Before you start the lab, you should sign up for an API key. We will download an audio file into your directory. First, we import speech-to-text v1 from IBM Watson. The service endpoint is based on the location of the service instance. We store the information in the variable URL_S2T. To find out which URL to use, view the service credentials. You will do the same for your API key. You create a speech-to-text adapter object. The parameters are the endpoint and API key. You will use this object to communicate with the Watson speech-to-text service. We have the path of the WAV file we would like to convert to text. We create the file object WAV with the WAV file using Open. We set the mode to RB, which means to read the file in binary format. The file object allows us access to the WAV file that contains the audio. We use the method recognize from the speech-to-text adapter object. This basically sends the audio file to Watson's speech-to-text service. The parameter audio is the file object. The content type is the audio file format. The service sends a response stored in the object response. The attribute result contains a Python dictionary. The key results value has a list that contains a dictionary. We are interested in the key transcript. We can assign it to the variable recognized_text as follows. Recognized_text now contains a string with the transcribed text. Now let's see how to translate the text using the Watson Language Translator. First, we import Language Translator v3 from IBM_Watson. We assign the service endpoint to the variable URL_LT. You can obtain the service in the lab instructions. You require an API key. See the lab instructions on how to obtain the API key. This API request requires the date of the version. See the documentation. We create a language translator object, Language Translator. We can get a list of the languages that the service can identify as follows. The method returns the language code. For example, English has a symbol EN to Spanish, which has the symbol ES. In the last section, we assign the transcribed text to the variable to recognized_text. We can use the method translate. This will translate the text. The result is a detailed response object. The parameter text is the text. Model_ID is the type of model we would like to use. In this case, we set it to EN-ES for English to Spanish. We use the method getResult to get the translated text and assign it to the variable translation. The result is a dictionary that includes the translation word count and character count. We can obtain the translation and assign it to the variable Spanish_translation as follows. Using the variable Spanish_translation, we can translate the text back to English as follows. The result is a dictionary. We can obtain the string with the text as follows. We can then translate the text to French as follows. Thanks for watching this video.
In this video, we will discuss the HTTP protocol. Specifically, we will discuss Uniform Resource Locator, or URL, request, and response. We touched on REST APIs in the last section. The HTTP protocol can be thought of as a general protocol of transferring information through the web. This includes many types of REST APIs. Recall that REST APIs function by sending a request, and the request is communicated via HTTP message. The HTTP message usually contains a JSON file. When you, the client, use a web page, your browser sends an HTTP request to the server where the page is hosted. The server tries to find the desired resource, by default index.html. If your request is successful, the server will send the object to the client in an HTTP response. This includes information like the type of the resource, the length of the resource, and other information. The table under the web server represents a list of resources stored in the web server, in this case an HTML file, PNG image, and a text file. When the request is made for the information, the web server sends the requested information, that is, one of the files. A Uniform Resource Locator, or URL, is the most popular way to find resources on the web. We can break the URL into 3 parts. First, we have the scheme. This is the protocol, and for this lab, it will always be http://. The internet address, or base URL. This will be used to find the location. Some examples include www.ibm.com and www.gitlab.com. And finally, the route. This is the location on the web server. For example, /images/idsnlogo.png. Let us review the request and response process. The following is an example of the request message for the GetRequest method. There are other HTTP methods we can use. In the start line, we have the GET method. This is an HTTP method. In this case, it's requesting the file index.html. The request header passes additional information with an HTTP request. In the GET method, the request header is empty. Some requests have a body. We will have an example of a request body later. The following table represents the response. The response start line contains the version number followed by a descriptive phrase. In this case, HTTP/1.0, a status code, 200, meaning success, and the descriptive phrase, OK. We have more on status codes later. The response header contains information. Finally, we have the response body containing the requested file, in this case, an HTML document. Let us look at other status codes. Some status code examples are shown in the table below. The prefix indicates the class. For example, the 100s are informational responses. 100 indicates that everything is okay so far. The 200s are successful responses. For example, 200, the request has succeeded. Anything in the 400s is bad news. 401 means the request is unauthorized. 500s stand for server errors, like 501 for not implemented. When an HTTP request is made, an HTTP method is sent. This tells the server what action to perform. A list of several HTTP methods is shown here. In the next video, we will use Python to apply the GET method that retrieves data from the server and the POST method that sends data to the server. In this video, we will discuss the HTTP protocol using the requests library, a popular method for dealing with the HTTP protocol in Python. We will review Python library requests for working with the HTTP protocols, and we will provide an overview of GET requests and POST requests. Let us review the request module in Python. This is one of several libraries, including httplib and urllib, that can work with the HTTP protocol. Requests is a Python library that allows you to send HTTP/1.1 requests easily. We can import the library as follows. You can make a GET request via the method GET to www.ibm.com. We have the response object R. This has information about the request, like the status of the request. We can view the status code using the attribute status_code, which is 200 for OK. You can view the request headers. You can view the request body in the following line. As there is no body for a GET request, we get a none. You can view the HTTP response header using the attribute headers. This returns a Python dictionary of HTTP response headers. We can look at the dictionary values. We can obtain the date the request was sent by using the key date. The key content type indicates the type of data. Using the response object R, we can also check the encoding. As the content type is text or HTML, we can use the attribute text to display the HTML in the body. We can review the first 100 characters. You can also download other content. See the lab for more. You can use the get method to modify the results of your query. For example, retrieving data from an API. In the lab, we will use http://bin.org, a simple HTTP request and response service. We send a GET request to the server. Like before, we have the base URL in the route. We append /get. This indicates we would like to perform a GET request. This is demonstrated in the following table. After GET is requested, we have the query string. This is part of a Uniform Resource Locator, or URL, and this sends other information to the web server. The start of the query is a question mark, followed by a series of parameter and value pairs, as shown in the table below. The first parameter name is name, and the value is Joseph. The second parameter name is ID, and the value is 123. Each pair, parameter, and value is separated by an equal sign. The series of pairs is separated by the ampersand. Let us complete an example in Python. We have the base URL with get appended to the end. To create a query string, we use the dictionary payload. The keys are the parameter names, and the values are the value of the query string. Then we pass the dictionary payload to the params parameter of the get function. We can print out the URL and see the name and values. We can see the request body. As the info is sent in the URL, the body has a value of none. We can print out the status code. We can view the response as text, and we can look at the key content type to look at the content type. As the content type is in the JSON, we format it using the method JSON. It returns a Python dict. The key args has the name and values for the query string. Like a GET request, a POST request is used to send data to a server, but the POST request sends the data in a request body, not the URL. In order to send the POST request in the URL, we change the route to POST. This endpoint will expect data, and it is a convenient way to configure an HTTP request to send data to a server. We have the payload dictionary. To make a POST request, we use the POST function. The variable payload is passed to the parameter data. Comparing the URL using the attribute URL from the response object of the GET and POST request, we see the POST request has no name or value pairs in its URL. We can compare the POST and GET request body. We see only the POST request has a body, and we can view the key form to get the payload. In this video, we will review Hypertext Markup Language, or HTML, for web scraping. Lots of useful data is available on web pages, such as real estate prices and solutions to coding questions. The website Wikipedia is a repository of the world's information. If you have an understanding of HTML, you can use Python to extract this information. In this video, you will review the HTML of a basic web page, understand the composition of an HTML tag, understand HTML trees, and understand HTML tables. Let us say you had a request to find the name and salary of players in a national basketball league from the following page. The web page is comprised of HTML. It consists of text surrounded by a series of blue text elements enclosed in angle brackets called tags. The tags tell the browser how to display the content. The data we require is in this text. The first portion contains the doc type HTML, which declares this document is an HTML document. HTML element is the root element of an HTML page, and head element contains meta information about the HTML page. Next, we have the body. This is what is displayed on the web page. This is usually the data we are interested in. We see the elements with an H3. This means type 3 heading, which makes the text larger and bold. These tags have the names of the players. Notice the data is enclosed in the elements. It starts with an H3 in brackets and ends in a /H3 in brackets. There is also a different tag, P. This means paragraph. Each P tag contains a player's salary. Let us take a closer look at the composition of an HTML tag. Here is an example of an HTML anchor tag. It will display IBM, and when you click it, it will send you to ibm.com. We have the tag name, in this case, A. This tag defines a hyperlink, which is used to link from one page to another. It is helpful to think of each tag name as a class in Python and each individual tag as an instance. We have an opening or start tag, and we have the end tag. This has the tag name preceded by a slash. These tags contain the content, in this case, what is displayed on the web page. We have the attribute. This is composed of the attribute name and attribute value. In this case, it is the URL to the destination web page. Real web pages are more complex, and depending on your browser, you can select the HTML element, then click Inspect. The result will give you the ability to inspect the HTML. There is also other types of content, such as CSS and JavaScript, that we will not go over in this course. The actual element is shown here. Each HTML document can actually be referred to as a document tree. Let us go over a simple example. Tags may contain strings and other tags. These elements are the tag's children. We can represent this as a family tree. Each nested tag is a level in the tree. The tag HTML tag contains the head and body tag. The head and the body tag are the descendants of the HTML tag. In particular, they are the children of the HTML tag. HTML tag is their parent. The head and body tag are siblings as they are on the same level. Title tag is the child of the head tag, and its parent is the head tag. The title tag is a descendant of the HTML tag, but not its child. The heading and paragraph tags are the children of the body tag, and as they are all children of the body tag, they are siblings of each other. The bold tag is a child of the heading tag. The content of the tag is also part of the tree, but this can get unwieldy to draw. Next, let us review HTML tables. To define an HTML table, we have the table tag. Each table row is defined with a TR tag, and you can also use a table header tag for the first row. The table row cell contains a set of TD tags. Each defines a table cell. For the first row, first cell, we have. For the first row, second cell, we have. And so on. For the second row, we have. And for the second row, first cell, we have. And for the second row, second cell, we have. And so on. We now have some basic knowledge of HTML. Now let us try and extract some data from a web page. In this video, we will cover web scraping. After watching this video, you will be able to define web scraping, understand the role of beautiful soup objects, apply the find_all method, and web scrape a website. What would you do if you wanted to analyze hundreds of points of data to find the best players of a sports team? Would you start manually copying and pasting information from different websites into a spreadsheet, spending hours trying to find the right data, and eventually giving up because the task was too overwhelming? That is where web scraping can help. Web scraping is a process that can be used to automatically extract information from a website and can easily be accomplished within a matter of minutes and not hours. To get started, we just need a little Python code and the help of two modules named Requests and Beautiful Soup. Let us say you were asked to find the name and salary of players in a national basketball league from the following web page. First, we import Beautiful Soup. We can store the web page HTML as a string in the variable HTML. To parse a document, pass it into the Beautiful Soup constructor. We get the Beautiful Soup object, soup, which represents the document as a nested data structure. Beautiful Soup represents HTML as a set of tree-like objects with methods used to parse the HTML. We will review the Beautiful Soup object. Using the Beautiful Soup object, Soup, we created. The tag object corresponds to an HTML tag in the original document, for example, the tag title. Consider the tag h3. If there is more than one tag with the same name, the first element with that tag is selected. In this case, with LeBron James, we see the name is enclosed in the bold attribute B. To extract it, use the tree representation. So let us use the tree representation. The variable tag-object is located here. We can access the child of the tag or navigate down the branch as follows. You can navigate up the tree by using the parent attribute. The variable tag child is located here, and we can access the parent. This is the original tag object. We can also find the sibling of tag object. We simply use the next-sibling attribute. We can find the sibling of sibling 1. We simply use the next sibling attribute. Consider the tag-child object. You can access the attribute name and value as a key value pair in a dictionary as follows. You can return the content as a navigable string. This is like a Python string that supports Beautiful Soup functionality. Now let us review the method findAll. This is a filter. You can use filters to filter based on a tag's name, its attributes, the text of a string, or on some combination of these. And consider the list of pizza places. Like before, create a Beautiful Soup object, but this time name it table. The find_all method looks through a tag's descendants and retrieves all descendants that match your filters. Apply it to the table with the tag tr. The result is a Python iterable just like a list. Each element is a tag object for tr. This corresponds to each row in the list, including the table header. Each element is a tag object, so consider the first row. For example, we can extract the first table cell. We can also iterate through each table cell. First, we iterate through the list table rows via the variable row. Each element corresponds to a row in the table. We can apply the method findAll to find all the table cells. Then we can iterate through the variable cells for each row. For each iteration, the variable cell corresponds to an element in the table for that particular row. And we continue to iterate through each element and repeat the process for each row. Let us see how to apply Beautiful Soup to a web page. To scrape a web page, we also need the requests library. The first step is to import the modules that are needed. Use the get method from the requests library to download the web page. The input is the URL. Use the text attribute to get the text and assign it to the variable page. Then create a Beautiful Soup object, soup, from the variable page. It will allow you to parse through the HTML page. And you can now scrape the page. Check out the labs for more. Hello, welcome to working with different file formats. After watching this video, you will be able to define different file formats such as CSV, XML, and JSON. Write simple programs to read and output data, and list what Python libraries are needed to extract data. When collecting data, you will find there are many different file formats that need to be collected or read in order to complete a data-driven story or analysis. When gathering the data, Python can make the process simpler with its predefined libraries. But before we explore Python, let us first check out some of the various file formats. Looking at a file name, you will notice an extension at the end of the title. These extensions let you know what type of file it is and what is needed to open it. For instance, if you see a title like fileexample.csv, you will know this is a CSV file. But this is only one example of different file types. There are many more, such as JSON or XML. When coming across these different file formats and trying to access their data, we need to utilize Python libraries to make this process easier. The first Python library to become familiar with is called pandas. By importing this library in the beginning of the code, we are then able to easily read the different file types. Since we have now imported the Panda library, let us use it to read the first CSV file. In this instance, we have come across the file example.csv file. The first step is to assign the file to a variable. Then, create another variable to read the file with the help of the Panda library. We can then call read_CSV function to output the data to the screen. With this example, there were no headers for the data, so it added the first line as the header. Since we do not want the first line of data as the header, let us find out how to correct this issue. Now that we have learned how to read and output the data from a CSV file, let us make it look a little more organized. From the last example, we were able to print out the data, but because the file had no headers, it printed the first line of data as the header. We easily solve this by adding a data frame attribute. We use the variable df to call the file, then add the columns attribute. By adding this one line to our program, we can then neatly organize the data output into the specified headers for each column. The next file format we will explore is the JSON file format. In this type of file, the text is written in a language-independent data format and is similar to a Python dictionary. The first step in reading this type of file is to import JSON. After importing JSON, we can add a line to open the file, call the load attribute of JSON to begin, and read the file. And lastly, we can then print the file. The next file format type is XML, also known as Extensible Markup Language. While the Pandas library does not have an attribute to read this type of file, let us explore how to parse this type of file. The first step to read this type of file is to import XML. By importing this library, we can then use the eTree attribute to parse the XML file. We then add the column headers and assign them to the data frame. Then create a loop to go through the document to collect the necessary data and append the data to a data frame. In this video, you learned how to recognize different file types, how to use Python libraries to extract data, and how to use data frames when collecting data. In this video, we will review Hypertext Markup Language, or HTML, for web scraping. Lots of useful data is available on web pages, such as real estate prices and solutions to coding questions. The website Wikipedia is a repository of the world's information. If you have an understanding of HTML, you can use Python to extract this information. In this video, you will review the HTML of a basic web page, understand the composition of an HTML tag, understand HTML trees, and understand HTML tables. Let us say you had a request to find the name and salary of players in a National Basketball League from the following page. The web page is comprised of HTML. It consists of text surrounded by a series of blue text elements enclosed in angle brackets called tags. The tags tell the browser how to display the content. The data we require is in this text. The first portion contains the doctype HTML, which declares this document is an HTML document. HTML element is the root element of an HTML page, and head element contains meta information about the HTML page. Next, we have the body. This is what is displayed on the web page. This is usually the data we are interested in. We see the elements with an H3. This means type 3 heading, which makes the text larger and bold. These tags have the names of the players. Notice the data is enclosed in the elements. It starts with an H3 in brackets and ends in a /H3 in brackets. There is also a different tag, P. This means paragraph. Each P tag contains a player's salary. Let us take a closer look at the composition of an HTML tag. Here is an example of an HTML anchor tag. It will display IBM, and when you click it, it will send you to IBM.com. We have the tag name, in this case, A. This tag defines a hyperlink, which is used to link from one page to another. It is helpful to think of each tag name as a class in Python and each individual tag as an instance. We have an opening or start tag, and we have the end tag. This has the tag name preceded by a slash. These tags contain the content, in this case, what is displayed on the web page. We have the attribute. This is composed of the attribute name and attribute value. In this case, it is the URL to the destination web page. Real web pages are more complex, and depending on your browser, you can select the HTML element, then click Inspect. The result will give you the ability to inspect the HTML. There is also other types of content, such as CSS and JavaScript, that we will not go over in this course. The actual element is shown here. Each HTML document can actually be referred to as a document tree. Let us go over a simple example. Tags may contain strings and other tags. These elements are the tag's children. We can represent this as a family tree. Each nested tag is a level in the tree. The tag HTML tag contains the head and body tag. The head and the body tag are the descendants of the HTML tag. In particular, they are the children of the HTML tag. HTML tag is their parent. The head and body tag are siblings as they are on the same level. Title tag is the child of the head tag, and its parent is the head tag. The title tag is a descendant of the HTML tag, but not its child. The heading and paragraph tags are the children of the body tag, and as they are all children of the body tag, they are siblings of each other. The bold tag is a child of the heading tag. The content of the tag is also part of the tree, but this can get unwieldy to draw. Next, let us review HTML tables. To define an HTML table, we have the table tag. Each table row is defined with a TR tag, and you can also use a table header tag for the first row. The table row cell contains a set of TD tags. Each defines a table cell. For the first row, first cell, we have. For the first row, second cell, we have. And so on. For the second row, we have. And for the second row, first cell, we have. And for the second row, second cell, we have. And so on. We now have some basic knowledge of HTML. Now let us try and extract some data from a web page. In this video, we will cover web scraping. After watching this video, you will be able to define web scraping, understand the role of beautiful soup objects, apply the find_all method, and web scrape a website. What would you do if you wanted to analyze hundreds of points of data to find the best players of a sports team? Would you start manually copying and pasting information from different websites into a spreadsheet? Spending hours trying to find the right data, and eventually giving up because the task was too overwhelming. That is where web scraping can help. Web scraping is a process that can be used to automatically extract information from a website, and can easily be accomplished within a matter of minutes and not hours. To get started, we just need a little Python code and the help of two modules named Requests and Beautiful Soup. Let us say you were asked to find the name and salary of players in a national basketball league from the following web page. First, we import Beautiful Soup. We can store the web page HTML as a string in the variable HTML. To parse a document, pass it into the Beautiful Soup constructor. We get the Beautiful Soup object, soup, which represents the document as a nested data structure. Beautiful Soup represents HTML as a set of tree-like objects with methods used to parse the HTML. We will review the Beautiful Soup object. Using the Beautiful Soup object, soup, we created. The tag object corresponds to an HTML tag in the original document, for example, the tag title. Consider the tag h3. If there is more than one tag with the same name, the first element with that tag is selected. In this case, with LeBron James, we see the name is enclosed in the bold attribute B. To extract it, use the tree representation. So let us use the tree representation. The variable tag-object is located here. We can access the child of the tag or navigate down the branch as follows. You can navigate up the tree by using the parent attribute. The variable tag child is located here, and we can access the parent. This is the original tag object. We can also find the sibling of tag object. We simply use the next-sibling attribute. We can find the sibling of sibling 1. We simply use the next sibling attribute. Consider the tag-child object. You can access the attribute name and value as a key-value pair in a dictionary as follows. You can return the content as a navigable string. This is like a Python string that supports Beautiful Soup functionality. Now, let us review the method findAll. This is a filter. You can use filters to filter based on a tag's name, its attributes, the text of a string, or on some combination of these. And consider the list of pizza places. Like before, create a Beautiful Soup object, but this time name it table. The find_all method looks through a tag's descendants and retrieves all descendants that match your filters. Apply it to the table with the tag tr. The result is a Python iterable just like a list. Each element is a tag object for tr. This corresponds to each row in the list, including the table header. Each element is a tag object, so consider the first row. For example, we can extract the first table cell. We can also iterate through each table cell. First, we iterate through the list table rows via the variable row. Each element corresponds to a row in the table. We can apply the method findAll to find all the table cells. Then we can iterate through the variable cells for each row. For each iteration, the variable cell corresponds to an element in the table for that particular row. And we continue to iterate through each element and repeat the process for each row. Let us see how to apply Beautiful Soup to a web page. To scrape a web page, we also need the requests library. The first step is to import the modules that are needed. Use the get method from the requests library to download the web page. The input is the URL. Use the text attribute to get the text and assign it to the variable page. Then create a Beautiful Soup object, soup, from the variable page. It will allow you to parse through the HTML page. And you can now scrape the page. Check out the labs for more.
Hello, and welcome to SQL for Data Science. The demand for data scientists is high, boasting a median base salary of $110,000 and job satisfaction score of 4.4 out of 5. It's no wonder that it's the top spot on Glassdoor's Best Jobs in America. Glassdoor analyzed data from data scientist job postings on Glassdoor and found that SQL is listed as one of the top 3 skills for a data scientist. Before you step into the field of data science, it is vitally important that you set yourself apart by mastering the foundations of this field. One of the foundational skills that you will require is SQL. SQL is a powerful language that's used for communicating with databases. Every application that manipulates any kind of data needs to store that data somewhere, whether it's big data or just a table with a few simple rows for government or a small startup, or a big database that spans over multiple servers or a mobile phone that runs its own small database. Here are some of the advantages of learning SQL for someone interested in data science. SQL will boost your professional profile as a data scientist, as it is one of the most sought-after skills by hiring employers. Learning SQL will give you a good understanding of relational databases. Tapping into all this information requires being able to communicate with the databases that store the data. Even if you work with reporting tools that generate SQL queries for you, it may be useful to write your own SQL statements so that you need not wait for other team members to create SQL statements for you. In this course, you will learn the basics of both the SQL language and relational databases. The course includes interesting quizzes and hands-on lab assignments, where you can get experience working with databases. In the first few modules, you work directly with the database and develop a working knowledge of SQL. Then, you will connect to a database and run SQL queries like a data scientist typically would, where you will use Python and Jupyter notebooks to connect to relational databases to access and analyze data. There is also an assignment included towards the end of the course, where you will get an opportunity to apply the concepts that you learned. So let's get started with SQL for data science. Hello, and welcome to SQL for data science. First, we will talk a little bit about what you'll learn in this course. This course teaches you the basics of the SQL language and the relational database model. There will be some lab exercises, and at the end of each section, there are a few review questions, and at the end, there is a final exam. By the end of this course, you will be able to discuss SQL basics and explain various aspects of the relational database model. In this video, we will learn about SQL and relational databases. By the end of this video, you will be able to describe SQL, data, database, a relational database, and list 5 basic SQL commands. But wait, what is SQL and what is a relational database? What is SQL? SQL is a language used for relational databases to query or get data out of a database. SQL is also referred to as SQL and is short for its original name, Structured English Query Language. So SQL is a language used for a database to query data. But what is data? And what is a database? Data is a collection of facts in the form of words, numbers, or even pictures. Data is one of the most critical assets of any business. It is used and collected practically everywhere. Your bank stores data about you, your name, address, phone number, account numbers, etc. Your credit card company and your PayPal accounts also store data about you. Data is important, so it needs to be secure, and it needs to be stored and accessed quickly. The answer is a database. So, what is a database? Databases are everywhere and used every day, but they are largely taken for granted. A database is a repository of data. It is a program that stores data. A database also provides the functionality for adding, modifying, and querying that data. There are different kinds of databases of different requirements. The data can be stored in various forms. When data is stored in tabular form, the data is organized in tables, like in a spreadsheet, which is columns and rows. That's a relational database. The columns contain properties about the item, such as last name, first name, email address, city. A table is a collection of related things, like a list of employees or a list of book authors. In a relational database, you can form relationships between tables. So a database is a repository of data. A set of software tools for the data in the database is called a database management system, or DBMS for short. The terms database, database server, database system, data server, and database management systems are often used interchangeably. For relational databases, it's called a Relational Database Management System, or RDBMS. RDBMS is a set of software tools that controls the data, such as access, organization, and storage. An RDBMS serves as the backbone of applications in many industries, including banking, transportation, health, and so on. Examples of relational database management systems are MySQL, Oracle Database, DB2 Warehouse, and DB2 on Cloud. For the majority of people using a database, there are 5 simple commands to create a table, insert data to populate the table, select data from the table, update data in the table, delete data from the table. So those are the building blocks for SQL for data science. You can now describe what is SQL, what is data, what is a database, and what is a relational database. You know that RDBMS stands for Relational Database Management System. And you can list 5 basic SQL commands to create a table, insert data to populate the table, select data from the table, update data in the table, and delete data from the table. Thanks for watching this video. Hello, and welcome to Retrieving Data with a Select Statement. In this video, we will learn about retrieving data from a relational database table by selecting columns of a table. At the end of this lesson, you will be able to retrieve data from a relational database table define the use of a predicate, identify the syntax of the select statement using the where clause, and list the comparison operators supported by a relational database management system. The main purpose of a database management system is not just to store the data, but also facilitate retrieval of the data. So, after creating a relational database table and inserting data into the table, we want to see the data. To see the data, we use the select statement. The select statement is a data manipulation language statement. Data manipulation language statements, or DML statements, are used to read and modify data. The select statement is called a query, and the output we get from executing this query is called a result set, or a result table. In its simplest form, a select statement is select star from table name. Based on the book entity example, we would create the table using the entity name book and the entity attributes as the columns of the table. The data would be added to the book table by adding rows to the table using the insert statement. In the book entity example, select star from book gives a result set of 4 rows. All the data rows for all columns in the table book are displayed. In addition, you can also retrieve all the rows for all columns by specifying the column names individually in the select statement. You don't always have to retrieve all the columns in a table. You can retrieve just a subset of columns. If you want, you can retrieve just 2 columns from the table book, for example, book_ID and title. In this case, the select statement is select book_ID, title from book. In this case, only the 2 columns display for each of the 4 rows. Also notice that the order of the columns displayed always matches the order in the select statement. However, what if we want to know the title of the book whose book_ID is B1? Relational operation helps us in restricting the result set by allowing us to use the clause where. The where clause always requires a predicate. A predicate is a condition that evaluates to true, false, or unknown. Predicates are used in the search condition of the where clause. So, if we need to know the title of the book whose book_ID is B1, we use the where clause with the predicate book_ID equals B1. Select book_ID, title from book, where book_ID equals B1. Notice that the result set is now restricted to just one row whose condition evaluates to true. The previous example used the comparison operator equal to in the where clause. There are other comparison operators supported by a relational database management system: equal to, greater than, less than, greater than or equal to, less than or equal to, and not equal to. Now you can retrieve data and select columns from a relational database table, define the use of a predicate, identify the syntax of the select statement using the where clause, and list the comparison operators supported by a relational database management system. Thanks for watching this video.
Hello and welcome. In this video, we'll briefly present a few useful expressions that are used with select statements. The first one is count. Count is a built-in database function that retrieves the number of rows that match the query criteria. For example, get the total number of rows in a given table. Select count star from table name. Let's say you create a table called metals, which has a column called country, and you want to retrieve the number of rows where the medal recipient is from Canada. You can issue a query like this: select count country from metals where country equals Canada. The second expression is distinct. Distinct is used to remove duplicate values from a result set. Example, to retrieve unique values in a column. Select distinct column name from table name. In the metals table mentioned earlier, a country may have received a gold medal multiple times. Example, retrieve the list of unique countries that received gold medals, that is, removing all duplicate values of the same country. Select distinct country from metals where medal type equals gold. The third expression is limit. Limit is used for restricting the number of rows retrieved from the database. Example, retrieve just the first 10 rows in a table. Select star from table name, limit 10. This can be very useful to examine the results set by looking at just a few rows instead of retrieving the entire results set, which may be very large. Example, retrieve just a few rows in the metals table for a particular year. Select star from metals where year equals 2018, limit 5. In this video, we looked at some useful expressions that are used with select statements, namely the count, distinct, and limit built-in functions. Thanks for watching this video.
Hello, and welcome to the insert statement. In this video, we will learn about populating a relational database table. At the end of this video, you will be able to identify the syntax of the insert statement and explain two methods to add rows to a table. After a table is created, the table needs to be populated with data. To insert data into a table, we use the insert statement. The insert statement is used to add new rows to a table. The insert statement is one of the data manipulation language statements. Data manipulation language statements, or DML statements, are used to read and modify data. Based on the author entity example, we created the table using the entity name, author, and the entity attributes as the columns of the table. Now we will add the data to the author table by adding rows to the table. To add the data to the author table, we use the insert statement. The syntax of the insert statement looks like this. Insert into table name, column name, values. In this statement, table name identifies the table. The column name list identifies each column in the table, and the values clause specifies the data values to be added to the columns in the table. To add a row with the data for Raoul Chong, we insert a row with an author underscore ID of A1, the last name as Chong, the first name as Raoul, the email as rfc@ibm.com, the city as Toronto, and the country as CA for Canada. The author table has 6 columns, so the insert statement lists the 6 column names, separated by commas, followed by a value for each of the columns, also separated by commas. It is important that the number of values provided in the values clause is equal to the number of column names specified in the column name list. This ensures that each column has a value. Tables do not need to be populated one row at a time. Multiple rows can be inserted by specifying each row in the values clause. In the values clause, each row is separated by a comma. For example, in this insert statement, we are inserting 2 rows, one for Raoul Chong and one for Rav Ahuja. Now you can identify the syntax of the insert statement and explain the 2 methods to add rows to a table, one row at a time or multiple rows. Thanks for watching this video. Hello, and welcome to the update statement and the delete statement. In this video, we will learn about altering and deleting data in a relational database table. At the end of this lesson, you will be able to identify the syntax of the update statement and delete statement, and explain the importance of the where clause in these statements. After a table is created and populated with data, the data in a table can be altered with the update statement. The update statement is one of the data manipulation language, or DML statements. DML statements are used to read and modify data. Based on the author entity example, we created the table using the entity name author and the entity attributes as the columns of the table. Rows were added to the author table to populate the table. Sometime later, you want to alter the data in the table. To alter or modify the data in the author table, we use the update statement. The syntax of the update statement looks like this. Update table name set column name equal to value where condition. In this statement, table name identifies the table. The column name identifies the column value to be changed, as specified in the where condition. Let's look at an example. In this example, You want to update the first name and last name of the author with author_IDA2 from Rav Ahuja to Lakshmi Kata. In this example, to see the update statement in action, we start by selecting all rows from the author table to see the values. To change the first name and last name to Lakshmi Kata, where the author ID is equal to A2, enter the update statement as follows. Update author set last name equal to Kata, first name equal to Lakshmi, where author ID is equal to A2. Now to see the result of the update, select all rows again from the author table, and you will see that in row 2 the name changed from Rav Ahuja to Lakshmi Kata. Note that if you do not specify the where clause, all the rows in the table will be updated. In this example, without specifying the where clause, all rows in the table would have changed the first and last names to Lakshmi Kata. Sometime later, there might be a need to remove one or more rows from a table. The rows are removed with the delete statement. The delete statement is one of the data manipulation language statements used to read and modify data. The syntax of the delete statement looks like this. Delete from table name, where condition. The rows to be removed are specified in the where condition. Based on the author entity example, we want to delete the rows for author ID A2 and A3. Let's look at an example. Delete from author where author ID in A2, A3. Note that if you do not specify the where clause, all the rows in the table will be removed. Now you can identify the syntax of the update statement and delete statement, and explain the importance of the where clause in these statements. Thanks for watching this video.
Hello and welcome to Database Concepts. In this video, we will learn about different types of models, how we use models to map data to tables, and define relationships between tables. At the end of this lesson, you will be able to explain the advantage of the relational model, explain how the entity name and attributes map to a relational database table, describe the difference between an entity and an attribute, identify some commonly used data types, and describe the function of primary keys. The relational model is the most used data model for databases because this model allows for data independence. Data is stored in a simple data structure, tables. This provides logical data independence, physical data independence, and physical storage independence. An entity relationship data model, or ER data model, is an alternative to a relational data model. Using a simplified library database as an example, this figure shows an entity relationship diagram, or ERD, that represents entities, called tables, and their relationships. In the library example, we have books. A book can be written by one or many authors. The library can have one or many copies of a book. Each copy can be borrowed by only one borrower at a time. An entity relationship model proposes thinking of a database as a collection of entities. Rather than being used as a model on its own, the ER model is used as a tool to design relational databases. In the ER model, entities are objects that exist independently of any other entities in the database. The building blocks of an ER diagram are entities and attributes. An entity can be a noun, person, place, or thing. In an ER diagram, an entity is drawn as a rectangle. Entities have attributes, which are the data elements that characterize the entity. Attributes tell us more about the entity. In an ER diagram, attributes are drawn as ovals. Using a simplified library as an example, the book is an example of an entity. Attributes are certain properties or characteristics of an entity and tell us more about the entity. The entity book has attributes such as book title, the edition of the book, the year the book was written, etc. Attributes are connected to exactly one entity. The entity book becomes a table in the database, and the attributes become the columns in a table. A table is a combination of rows and columns. While mapping, the entity becomes the table. Having said that, the table has not yet taken the form of rows and columns. The attributes get translated into columns in a table, providing the actual table form of rows and columns. Later, we add some data values to each of the columns, which completes the table form. Each attribute stores data values of different formats: characters, numbers, dates, currency, and many more besides. In the book table example, the title is made up of characters. As book titles vary in length, we can set the variable character data type for the title column, varchar. For character columns that do not vary in length, we use character or char. The edition and year columns would be numeric. The ISBN column would be char because it contains dashes as well as numbers, and so on. Using the book entity mapping as an example, we can create the tables for the remainder of our simplified library example using entity names like author, author list, borrower, loan, and copy. The entity attributes will be the columns of the tables. Each table is assigned a primary key. The primary key of a relational table uniquely identifies each tuple or row in a table, preventing duplication of data and providing a way of defining relationships between tables. Tables can also contain foreign keys, which are primary keys defined in other tables, creating a link between the tables. Now you know that the key advantage of the relational model is logical and physical data independence and storage independence. Entities are independent objects which can have multiple characteristics called attributes. When mapping to a relational database, entities are represented as tables and attributes map to columns. Common data types include characters such as char and varchar, numbers such as integer and decimal, and timestamps including date and time. A primary key uniquely identifies a specific row in a table and prevents duplication of data. Hello and welcome. This video will cover the key concepts around databases in the cloud. In order to learn SQL, you first need to have a database available to practice your SQL queries. An easy way to do so is to create an instance of a database in the cloud and use it to execute your SQL queries. After completing this lesson, you will be able to understand basic concepts related to cloud databases, list a few cloud databases, describe database service instances, as well as demonstrate how to create a service instance on an IBM DB2 on cloud. A cloud database is a database service built and accessed through a cloud platform. It serves many of the same functions as traditional databases with the added flexibility of cloud computing. Some advantages of using cloud databases include ease of use. Users can access cloud databases from virtually anywhere using a vendor's API or web interface, or your own applications, whether on cloud or remote. Scalability. Cloud databases can expand and shrink their storage and compute capacities during runtime to accommodate changing needs and usage demands, so organizations only pay for what they actually use. Disaster recovery. In the event of a natural disaster or equipment failure or power outage, data is kept secure through backups on remote servers on cloud in geographically distributed regions. A few examples of relational databases on cloud include IBM DB2 on cloud, databases for PostgreSQL on IBM Cloud, Oracle Database Cloud Service, Microsoft Azure SQL Database, and Amazon Relational Database Services. These cloud databases can run in the cloud, either as a virtual machine which you can manage, or delivered as a managed service depending on the vendor. The database services can either be single or multi-tenant depending on the service plan. To run a database in cloud, you must first provision an instance of the database service on the cloud platform of your choice. An instance of a database as a service, or DBaaS, provides users with access to database resources in cloud without the need for setting up of the underlying hardware, installing the database software, and administering the database. The database service instance will hold your data in related tables. Once your data is loaded into the database instance, you can connect to the database instance using a web interface or APIs in your applications. Once connected, your application can send SQL queries across to the database instance. The database instance then resolves the SQL statements into operations against the data and objects in the database. Any data retrieved is returned to the application as a result set. Now let's see how a database instance is created for DB2 on Cloud. IBM DB2 on Cloud is a SQL database provisioned for you in the cloud. You can use DB2 on Cloud just as you would use any database software, but without the overhead and expense of hardware, setup, or software installation and maintenance. Now let's see how we can set up a service instance of DB2. Navigate to IBM Cloud Catalog and select the DB2 service. Note there are several variations of the DB2 service, including DB2 Hosted and DB2 Warehouse. For our purposes, we will choose the DB2 service, which comes with a free Lite plan. Select the Lite plan. If need to, change the defaults. You can type a service instance name, choose the region to deploy to, as well as an org and space for the service. Then click Create. You can view the IBM DB2 service that you created by selecting Services from your IBM Cloud dashboard. From this dashboard, you can manage your database instance. For example, you can click on the Open Console button to launch the web console for your database instance. The web console allows you to create tables, load data, explore data in your tables, and issue SQL queries. In order to access your database instance from your applications, you will need the service credentials. For the first time around, you'll need to create a set of new credentials. You can also choose to create multiple sets of credentials for different applications and users. Once a set of service credentials is created, you can view it as a JSON snippet. The credentials include the necessary details to establish a connection to the database and includes the following: a database name and port number, a host name, which is the name of the server on the cloud on which your database instance resides, a username, which is the user ID you'll use to connect along with the password. Note that your username is also the schema name in which your tables will be created by default. Now that you know how to create a database instance on cloud, the next step is to actually go and create one. Thank you for watching this video. Welcome to Types of SQL Statements. At the end of this video, you will be able to distinguish between data definition language statements and data manipulation language statements. SQL statements are used for interacting with entities, that is, tables, attributes, that is, columns, and their tuples, or rows with data values, in relational databases. SQL statements fall into two different categories: data definition language statements and data manipulation language statements. Data definition language, or DDL statements, are used to define, change, or drop database objects such as tables. Common DDL statement types include create, alter, truncate, and drop. Create, which is used for creating tables and defining its columns. Alter is used for altering tables, including adding and dropping columns and modifying their data types. Truncate is used for deleting data in a table, but not the table itself. Drop is used for deleting tables. Data manipulation language, or DML statements, are used to read and modify data in tables. These are also sometimes referred to as CRUD operations, that is, create, read, update, and delete rows in a table. Common DML statement types include insert, select, update, and delete. Insert is used for inserting a row or several rows of data into a table. Select reads or selects row or rows from a table. Update edits row or rows in a table, and delete removes a row or rows of data from a table. Now you know that DDL or data definition language statements are used for defining or changing objects in a database, such as tables. And DML or data manipulation language statements are used for manipulating or working with data in tables. Thanks for watching this video. Welcome to Create Table Statement. At the end of this video, you will be able to explain how the entity name and attributes are used to create a relational database table. Now let's look at the most common DDL statement, create. The syntax of the create table is shown here. You start with create table, followed by the name of the table you want to create. Then enclose the rest of the statement inside a pair of parentheses or round brackets. Each row inside the parentheses specifies the name of a column, followed by its data type and possibly some additional optional values that we will see later. Each attribute or column definition is separated by a comma. For example, if we want to create a table for provinces in Canada, you would specify create table provinces, open parentheses, ID car, 2, primary key, not null, comma, name varchar, 24, close parentheses. In this example, the data types used are car, which is a character string of a fixed length, in this case 2, and varchar, which is a character string of a variable length. In this case, the variable character field can be up to 24 characters long. Issuing this statement would create a table in the database with 2 columns. The first column, ID, for storing the abbreviated 2-letter province shortcodes such as AB, BC, etc. And the second column, called name, for storing the full name of the province such as Alberta, British Columbia, etc. Now let's look at a more elaborate example based on the library database. This database includes several entities such as author, book, borrower, etc. Let's start by creating the table for the author entity. The name of the table will be author, and its attributes such as author_ID, first name, last name, etc. will be the columns of the table. In this table, we will also assign the author_ID attribute as the primary key, so that no duplicate values can exist. Recall, the primary key of a relational table uniquely identifies each tuple or row in a table. To create the author table, issue the following command. Create table author, open parentheses, author_ID, car2, primary key not null, comma, last name varchar 15, not null, comma, first name varchar 15, not null, comma, email varchar 40, comma, city varchar 15, comma, country car 2, close parentheses. Note that the author_ID is the primary key. This constraint prevents duplicate values in the table. Also note that the last name and first name have the constraint not null. This ensures that these fields cannot contain a null value, since an author must have a name. Now you know that create is a DDL statement for creating entities or tables in a database, and the create table statement includes definition of attributes of columns in the table, including names of columns, data types of columns, and other optional values if required, such as the primary key constraint. Thanks for watching this video. Hello and welcome to Alter, Drop, and Truncate Tables. After watching this video, you will be able to describe the alter table, drop table, and truncate statements, explain the syntax, and use the statements in queries. You use the alter table statement to add or remove columns from a table, to modify the data type of columns, to add or remove keys, and to add or remove constraints. The syntax of the alter table statement is shown here. You start with alter table, followed by the name of the table that you want to alter. Differently to the create table statement, though, you do not use parentheses to enclose the parameters for the alter table statement. Each row in the alter table statement specifies one change that you want to make to the table. For example, to add a telephone number column to the author table in the library database to store the author's telephone number, use the following statement. Alter table author, add column, telephone underscore number, big int, semicolon. In this example, the data type for the column is big int, which can hold a number up to 19 digits long. You can also use the alter table statement to modify the data type of a column. To do this, use the alter column clause specifying the new data type for the column. For example, using a numeric data type for telephone number means that you cannot include parentheses, plus signs, or dashes as part of the number. You can change the column to use the car data type to overcome this. This code shows how to alter the author table. Alter table author, alter column telephone underscore number, set data type car, open parentheses, 20, close parentheses, semicolon. Altering the data type of a column containing existing data can cause problems, though, if the existing data is not compatible with the new data type. For example, changing a column from the car data type to a numeric data type will not work if the column already contains non-numeric data. If you try to do this, you will see an error message in the notification log and the statement will not run. If your spec changes and you no longer need this extra column, you can again use the alter table statement, this time with the drop column clause to remove the column as shown. Alter table author drop column telephone underscore number semicolon. Similar to using drop column to delete a column from a table, you use the drop table statement to delete a table from a database. If you delete a table that contains data, by default, the data will be deleted alongside the table. The syntax for the drop table statement is drop table, table underscore name, semicolon. So you use this statement, drop table author, semicolon, to remove the table from the database. Sometimes you might want to just delete the data in a table rather than deleting the table itself. While you can use the delete statement without a where clause to do this, it is generally quicker and more efficient to truncate the table instead. You use the truncate table statement to delete all of the rows in a table. The syntax of this statement is truncate table, table underscore name, immediate, semicolon. The immediate specifies to process the statement immediately and that it cannot be undone. So, to truncate the author table, you use this statement, truncate table, author immediate, semicolon. In this video, you learned that the alter table statement changes the structure of an existing table, for example, to add, modify, or drop columns. The drop table statement deletes an existing table, and the truncate table statement deletes all rows of data in a table.
Hello, and welcome to Retrieving Data with Select Statement String Patterns. In this video, we will learn about some advanced techniques in retrieving data from a relational database table. At the end of this lesson, you will be able to describe how to simplify a select statement by using string patterns, ranges, or sets of values. The main purpose of a database management system is not just to store the data, but also facilitate retrieval of the data. In its simplest form, a select statement is select star from table name. Based on our simplified library database model and the table book, select star from book gives a result set of 4 rows. All the data rows for all columns in the table book are displayed. Or you can retrieve a subset of columns, for example, just 2 columns from the table book, such as book_ID and title. or you can restrict the result set by using the where clause. For example, you can select the title of the book whose book_ID is B1. But what if we don't know exactly what value to specify in the where clause? The where clause always requires a predicate, which is a condition that evaluates to true, false, or unknown. But what if we don't know exactly what value the predicate is? For example, what if we can't remember the name of the author, but we remember that their first name starts with R? In a relational database, we can use string patterns to search data rows that match this condition. Let's look at some examples of using string patterns. If we can't remember the name of the author, but we remember that their name starts with R, we use the where clause with the like predicate. The like predicate is used in a where clause to search for a pattern in a column. The percent sign is used to define missing letters. The percent sign can be placed before the pattern, after the pattern, or both before and after the pattern. In this example, we use the percent sign after the pattern, which is the letter R. The percent sign is called a wildcard character. A wildcard character is used to substitute other characters. So, if we can't remember the name of the author, but we can remember that their first name starts with the letter R, we add the like predicate to the where clause. For example, select first name from author, where first name like R percentile. This will return all rows in the author table whose author's first name starts with the letter R. And here is the result set. 2 rows are returned for authors Raoul and Rav. What if we wanted to retrieve the list of books whose number of pages is more than 290 but less than 300? We could write the select statement like this, specifying the where clause as where pages is greater than or equal to 290 and pages is less than or equal to 300. But in a relational database, we can use a range of numbers to specify the same condition. Instead of using the comparison operators greater than or equal to, we use the comparison operator between and. Between and compares 2 values. The values in the range are inclusive. In this case, we rewrite the query to specify the where clause as where pages between 290 and 300. The result set is the same, but the select statement is easier and quicker to write. In some cases, there are data values that cannot be grouped under ranges. For example, if we want to know which countries the authors are from. If we wanted to retrieve authors from Australia or Brazil, we could write the select statement with the where clause repeating the 2 country values. However, what if we want to retrieve authors from Canada, India, and China? The where clause would become very long, repeatedly listing the required country conditions. Instead, we can use the in operator. The in operator allows us to specify a set of values in a where clause. This operator takes a list of expressions to compare against. In this case, the countries Australia or Brazil. Now you can describe how to simplify a select statement by using string patterns, ranges, or sets of values. Thanks for watching this video. Hello, and welcome to Sorting Select Statement Result Sets. In this video, we will learn about some advanced techniques in retrieving data from a relational database table and sorting how the result set displays. At the end of this lesson, you will be able to describe how to sort the result set by either ascending or descending order and explain how to indicate which column to use for the sorting order. The main purpose of a database management system is not just to store the data, but also facilitate retrieval of the data. In its simplest form, a select statement is select star from table name. Based on our simplified library database model and the table book, select star from book gives a result set of 4 rows. All the data rows for all columns in the table book are displayed. We can choose to list the book titles only, as shown in this example. Select title from book. However, the order does not seem to be in any order. Displaying the result set in alphabetical order would make the result set more convenient. To do this, we use the order by clause. To display the result set in alphabetical order, we add the order by clause to the select statement. The order by clause is used in a query to sort the result set by a specified column. In this example, we have used order by on the column title to sort the result set. By default, the results set is sorted in ascending order. In this example, the results set is sorted in alphabetical order by book title. To sort in descending order, use the keyword des. The results set is now sorted according to the column specified, which is title, and is sorted in descending order. Notice the order of the first 3 rows. The first 3 words of the title are the same, so the sorting starts from the point where the characters differ. Another way of specifying the sort column is to indicate the column sequence number. In this example, select title, pages from book, order by 2, indicates the column sequence number in the query for the sorting order. Instead of specifying the column name pages, the number 2 is used. In the select statement, the second column specified in the column list is pages, so the sort order is based on the values in the pages column. In this case, the pages column indicates the number of pages in the book. As you can see, the result set is in ascending order by number of pages. Now you can describe how to sort the result set by either ascending or descending order, and explain how to indicate which column to use for the sorting order. Thanks for watching this video. Hello, and welcome to grouping select statement result sets. In this video, we will learn about some advanced techniques in retrieving data from a relational database table, and sorting and grouping how the result set displays. At the end of this lesson, you will be able to explain how to eliminate duplicates from a result set, and describe how to further restrict a result set. At times, a select statement result set can contain duplicate values. Based on our simplified library database model, in the author table example, the country column lists the 2-letter country code of the author's country. If we select just the country column, we get a list of all of the countries. For example, select country from author order by 1. The order by clause sorts the result set. This result set lists the countries the authors belong to, sorted alphabetically by country. In this case, the result set displays 20 rows, 1 row for each of the 20 authors. But some of the authors come from the same country, so the result set contains duplicates. However, all we need is a list of countries the authors come from. So in this case, duplicates do not make sense. To eliminate duplicates, we use the keyword distinct. Using the keyword distinct reduces the result set to just 6 rows. But what if we wanted to also know how many authors come from the same country? So now we know that the 20 authors come from 6 different countries. But we might want to also know how many authors come from the same country. To display the result set listing the country and number of authors that come from that country, we add the group by clause to the select statement. The group by clause groups a result into subsets that has matching values for 1 or more columns. In this example, countries are grouped and then counted using the count function. Notice the column heading for the second column in the result set. The numeric value 2 displays as a column name because the column name is not directly available in the table. The second column in the result set was calculated by the count function. Instead of using the column name 2, we can assign a column name to the result set. We do this using the as keyword. In this example, we change the derived column name 2 to column name count using the as count keyword. This helps clarify the meaning of the result set. Now that we have the count of authors from different countries, we can further restrict the number of rows by passing some conditions. For example, we can check if there are more than 4 authors from the same country. To set a condition to a group by clause, we use the keyword having. The having clause is used in combination with the group by clause. It is very important to note that the where clause is for the entire result set, but the having clause works only with the group by clause. To check if there are more than 4 authors from the same country, we add the following to the select statement. Having count country greater than 4. Only countries that have 5 or more authors from that country are listed in the result set. In this example, those countries are China with 6 authors and India also with 6 authors. Now you can explain how to eliminate duplicates from a result set and describe how to further restrict a result set. Thanks for watching this video.
Hello and welcome. In this video, we'll go over SQL functions built into the database. So let's get started. While it is very much possible to first fetch data from a database and then perform operations on it from your applications and notebooks, most databases come with built-in functions. These functions can be included in SQL statements, allowing you to perform operations on data right within the database itself. Using database functions can significantly reduce the amount of data that needs to be retrieved from the database, that is, reduces network traffic and use of bandwidth. When working with large data sets, it may be faster to use built-in functions rather than first retrieving the data into your application and then executing functions on the retrieved data. Note that it is also possible to create your own functions, that is, user-defined functions, in the database, but that is a more advanced topic. For the examples in this lesson, let's consider this pet rescue table in the database for a pet rescue organization. It records rescue transaction details and includes the columns ID, animal, quantity, cost, and rescue date. For the purposes of this lesson, we have populated it with several rows of data as shown here. What are aggregate or column functions? An aggregate function takes a collection of like values, such as all of the values in a column, as input and returns a single value, or null. Examples of aggregate functions include sum, minimum, maximum, average, etc. Let's look at some examples based on the pet rescue table. The sum function is used to add up all the values in a column. To use the function, you write the column name within parentheses after the function name. For example, to add up all of the values in the cost column, select sum cost from pet rescue. When you use an aggregate function, the column in the result set by default is given a number. It is possible to explicitly name the resulting column. For example, let's say we want to call the output column in the previous query as sum of cost. Select sum cost as sum of cost from pet rescue. Note the use of as in this example. Minimum, as the name implies, is used to get the lowest value. Similarly, maximum is used to get the highest value. For example, to get the maximum quantity of any animal rescue in a single transaction, select max quantity from pet rescue. Aggregate functions can also be applied on a subset of data instead of an entire column. For example, to get the minimum quantity of ID column for dogs, select min ID from pet rescue where animal equals dog. The average function is used to return the average or the mean value. For example, to specify the average value of cost as select average cost from pet rescue. Note that we can perform mathematical operations between columns and then apply aggregate functions on them. For example, to calculate the average cost per dog, select average cost divided by quantity from pet rescue where animal equals dog. In this case, the cost is for multiple units, so we first divide the cost by the quantity of the rescue. Now let's look at the scalar and string functions. Scalar functions perform operations on individual values. For example, to round up or down every value in the cost column to the nearest integer, select round cost from pet rescue. There is a class of scalar functions called string functions that can be used for operations on strings, that is, char and varchar values. For example, to retrieve the length of each value in animal column, select length animal from pet rescue. Uppercase and lowercase functions can be used to return uppercase or lowercase values of strings. For example, to retrieve animal values in uppercase, select uppercase, animal, from, pet rescue. Scalar functions can be used in the where clause. For example, to get lowercase values of the animal column for cat, select star from pet rescue where lowercase animal equals cat. This type of a statement is useful for matching values in the where clause if you are not sure whether the values are stored in upper, lower, or mixed case in the table. You can also have one function operate on the output of another function. For example, to get unique cases for animal column in uppercase, select distinct uppercase animal from pet rescue. In this video, we looked at some built-in SQL aggregate functions, such as sum, minimum, maximum, and average. We also looked at scalar and string functions, such as round, lowercase, and uppercase. Thank you for watching. Hello and welcome. In this video, we'll go over date and time SQL functions built into the database. So let's get started. Most databases contain special data types for dates and times. DB2 contains date, time, and timestamp types. In DB2, date has 8 digits for year, month, and day. Time has 6 digits, hours, minutes, and seconds. Timestamp has 20 digits, year, month, day, hour, minute, seconds, and microseconds, where double X represents month and 6 Z's or Z's represents microseconds. Functions exist to extract the day, month, day of week, day of year, week, hour, minute, and second. Let us look at some examples of queries for date and time functions. The day function can be used to extract the day portion from a date. For example, to get the day portion for each rescue date involving cat, select day, rescue date, from pet rescue, where animal equals cat. Date and time functions can be used in the where clause. For example, to get the number of rescues during the month of May, that is, for month 5, select count, star, from pet rescue, where month, rescue date equals 05. You can also perform date or time arithmetic. For example, to find out what date it is 3 days after each rescue date. Maybe you want to know this because the rescue needs to be processed within 3 days. Select rescue date plus 3 days from pet rescue. Special registers current time and current date are also available. For example, to find out how many days have passed since each rescue date till now, select current date minus rescue date from pet rescue. The result will be in years, months, days. In this video, we looked at different types of built-in SQL functions for working with dates and times. Thank you for watching.
Hello and welcome. In this video, you'll learn how to write subqueries or nested select statements. Subqueries or subselects are like regular queries but placed within parentheses and nested inside another query. This allows you to form more powerful queries than would have been otherwise possible. An example of a nested query is shown. In this example, the subquery is inside the where clause of another query. Consider the employees table from the previous video. The first few rows of data are shown here. The table contains several columns, including an employee ID, first name, last name, salary, etc. We will now go over some examples involving this table. Let's consider a scenario which may necessitate the use of subqueries. Let's say we want to retrieve the list of employees who earn more than the average salary. To do so, we could try this code. Select star from employees where salary is greater than average salary. However, running this query will result in an error like the one shown, indicating an invalid use of the aggregate function. One of the limitations of built-in aggregate functions, like the average function, is that they cannot always be evaluated in the where clause. So, to evaluate a function like average in the where clause, we can make use of a sub-select expression, like the one shown here. Select employee ID, first name, last name, salary from employees where salary is less than, open parenthesis, select average salary from employees, close parenthesis. Notice that the average function is evaluated in the first part of the sub-query, allowing us to circumvent the limitation of evaluating it directly in the where clause. The sub-select doesn't just have to go in the where clause. It can also go in other parts of the query, such as in the list of columns to be selected. Such sub-queries are called column expressions. Now, let's look at a scenario where we might want to use a column expression. Say we wanted to compare the salary of each employee with the average salary. We could try a query like select employee ID, salary, average salary as average salary from employees. Running this query will result in an error indicating that no group by clause is specified. We can circumvent this error by using the average function in a subquery placed in the list of the columns. For example, select employee ID, salary, open left parenthesis, select average salary from employees, closed right parenthesis, as average salary from employees. Another option is to make the subquery be part of the from clause. Subqueries like these are sometimes called derived tables or table expressions because the outer query uses the results of the subquery as a data source. Let's look at an example to create a table expression that contains non-sensitive employee information. Select star from select employee ID, first name, last name, department ID from employees as employee for all. The derived table in the subquery does not include sensitive fields like date of birth or salary. This example is a trivial one, and we could just as easily have included the columns in the outer query. However, such derived tables can prove to be powerful in more complex situations, such as when working with multiple tables and doing joins. In this video, you have seen how subqueries and nested queries can be used to form richer queries, and how they can overcome some of the limitations of aggregate functions. You also learned to use subqueries in the where clause, in the list of columns, and in the from clause. Thanks for watching this video.
Hello and welcome.
In this video, you will learn how to write queries that access more than one table. There are several ways to access multiple tables in the same query, namely using subqueries, implicit join, and join operators, such as inner join and outer join. In this video, we'll examine the first two options. The third option is covered in more detail in other videos. Let's consider the employees and departments tables from a previous video. The employees table contains several columns for categories such as employee ID, first name, last name, and salary, to name a few. The departments table contains a department ID, department name, manager ID, and location ID. Some sample data from these tables is shown here. We will utilize these tables for the examples in this video. In a previous video, we learned how to use subqueries. Now, let's use subqueries to work with multiple tables. If we want to retrieve only the employee records from the Employees table for which a department ID exists in the Departments table, we can use a subquery as follows. Select star from Employees, where Department ID in, select Department ID, Department from Departments. Here the outer query accesses the Employees table, and the subquery on the Departments table is used for filtering the result set of the outer query. Let's say we want to retrieve only the list of employees from a specific location. We do not have any location information in the Employees table, but the Departments table has a column called Location ID. Therefore, we can use a subquery from the Departments table as input to the Employee table query as follows. Select star from Employees, where Department ID in, select Department ID, Department from Departments, where Location ID equals L0002. Now, let's retrieve the department ID and department name for employees who earn more than $70,000. To do so, we will need a subquery on the Employees table to satisfy the salary criteria, and then feed it as input to an outer query on the Departments table in order to get the matching department info. Select Department ID, Department, Department Name from Departments, where Department ID, Department in, select Department ID from Employees where salary is greater than $70,000. We can also access multiple tables by specifying them in the From clause of the query. Consider the example, select star from Employees, Departments. Here we specified two tables in the From clause. This results in a table join, but note we are not explicitly using the join operator. The resulting join in this example is called a full join or Cartesian join because every row in the first table is joined with every row in the second table. If you examine the result set, you will see more rows than in both tables individually. We can use additional operands to limit the result set. Let's look at an example where we limit the result set to only rows with matching department IDs. Select star from Employees, Departments, where Employees, Department ID equals Departments, Department ID, Department. Notice that in the Where clause, we prefix the name of the column with the name of the table. This is to fully qualify the column name, since it's possible that different tables could have some column names that are exactly the same. Since the table names can sometimes be long, we can use shorter aliases for table names as shown here. Select star from Employees E, Departments D, where E, Department ID, equals D, Department ID, Department. Here we define the alias E for Employees table and D for Departments table, and then use these aliases in the Where clause. If we wanted to see the department name for each employee, we would enter the code as follows. Select Employee ID, Department Name from Employees E, Departments D, where E, Department ID equals D, Department ID, Department. Similar to before, The column names in the select clause can also be prefixed by aliases, as shown in the query select E employee ID, D department ID department from employees E departments D, where E department ID equals D department ID department. In this lesson, we have shown you how to work with multiple tables using subqueries and implicit joins. Thanks for watching.
Hello! In this video, you will learn how to access databases using Python. Databases are powerful tools for data scientists. After completing this module, you will be able to explain the basic concepts related to using Python to connect to databases. Then you will create tables, load data, and query data using SQL from Jupyter Notebooks, and finally, analyze the data. In the lab assignments, you will learn how to create an instance in the cloud, connect to a database, query data from the database using SQL, and analyze the data using Python. You will be able to explain the basic concepts related to connecting a Python application to a database, describe SQL APIs, as well as list some of the proprietary APIs used by popular SQL-based DBMS systems. Let's quickly review some of the benefits of using Python, a popular scripting language for connecting to databases. The Python ecosystem is very rich and provides easy-to-use tools for data science. Some of the most popular packages are NumPy, pandas, matplotlib, and scipy. Python is easy to learn and has a simple syntax. Due to its open-source nature, Python has been ported to many platforms. All your Python programs can work on any of these platforms without requiring any changes at all, if you are careful and avoid any system-dependent features. Python supports relational database systems. Writing Python code to access databases is made easier by the presence of the Python Database API, commonly referred to as the DB API. And detailed documentation related to Python is easily available. Notebooks are also very popular in the field of data science because they run in an environment that allows creation and sharing of documents that contain live code, equations, visualizations, and explanatory text. A notebook interface is a virtual notebook environment used for programming. Examples of notebook interfaces include the Mathematica Notebook, Maple Worksheet, MATLAB Notebook, IPython Jupyter, R Markdown, Apache Zeppelin, Apache Spark Notebook, and the Databricks Cloud. In this module, we will be using Jupyter Notebooks. The Jupyter Notebook is an open-source web application that allows you to create and share documents that contain live code, equations, visualizations, and narrative text. Here are some of the advantages of using Jupyter Notebooks. Notebooks support for over 40 programming languages, including Python, R, Julia, and Scala. Notebooks can be shared with others by email, Dropbox, GitHub, and the Jupyter Notebook Viewer. Your code can produce rich interactive output, HTML, images, videos, LaTeX, and custom MIME types. You can leverage big data tools such as Apache Spark from Python, R, and Scala, and explore that same data with pandas, scikit-learn, ggplot2, and TensorFlow. This is how a typical user accesses databases using Python code written on a Jupyter Notebook, a web-based editor. There is a mechanism by which the Python program communicates with the DBMS. The Python code connects to the database using API calls. We will explain the basics of SQL APIs and Python DB APIs. An application programming interface is a set of functions that you can call to get access to some type of service. A SQL API consists of library function calls as an application programming interface API for the DBMS. To pass SQL statements to the DBMS, an application program calls functions in the API, and it calls other functions to retrieve query results and status information from the DBMS. The basic operation of a typical SQL API is illustrated in the figure. The application program begins its database access with one or more API calls that connect the program to the DBMS. To send a SQL statement to the DBMS, the program builds the statement as a text string in a buffer and then makes an API call to pass the buffer contents to the DBMS. The application program makes API calls to check the status of its DBMS request and to handle errors. The application program ends its database access with an API call that disconnects it from the database. Now let's learn basic concepts about some of the proprietary APIs used by popular SQL-based DBMS systems. Each database system has its own library. As you can see, the table shows a list of a few applications and corresponding SQL APIs. MySQL-C API provides low-level access to the MySQL client server protocol and enables C programs to access database contents. The PsychoPG2 API connects Python applications in PostgreSQL databases. The IBM_DB API is used to connect Python applications to IBM DB2 databases. The DBlib API is used to connect to SQL Server databases. ODBC is used for database access for Microsoft Windows OS. OCI is used by Oracle databases. And finally, JDBC is used by Java applications. Thanks for watching this video.
Hello and welcome to Writing Code using DB API. After completing this video, you will be able to explain the basic concepts related to the Python DB API and database cursors, and also write code using DB APIs. As we saw in the beginning of this module, the user writes Python programs using a Jupyter notebook. There is a mechanism by which the Python code communicates with the DBMS. The Python code connects to the database using DB API calls. DB API is Python's standard API for accessing relational databases. It is a standard that allows you to write a single program that works with multiple kinds of relational databases, instead of writing a separate program for each one. So, if you learn the DB API functions, then you can apply that knowledge to use any database with Python. Here are some advantages of using the DB API. It's easy to implement and understand. This API has been defined to encourage similarity between the Python modules that are used to access databases. It achieves consistency, which leads to more easily understood modules. The code is generally more portable across databases, and it has a broader reach of database connectivity from Python. As we know, each database system has its own library. As you can see, the table shows a list of a few databases and corresponding DB APIs to connect to Python applications. The IBM_DB library is used to connect to an IBM DB2 database. The MySQL connector Python library is used to connect to a Compose for MySQL database. The PsychoPG2 library is used to connect to a Compose from PostgreSQL database. And finally, the PyMongo library is used to connect to a Compose from MongoDB database. The two main concepts in the Python DB API are connection objects and query objects. You use connection objects to connect to a database and manage your transactions. Cursor objects are used to run queries. You open a cursor object and then run queries. The cursor works similar to a cursor in a text processing system, where you scroll down in your results set and get your data into the application. Cursors are used to scan through the results of a database. The DB API includes a connect constructor for creating a connection to the database. It returns a connection object, which is then used by the various connection methods. These connection methods are the cursor method, which returns a new cursor object using the connection, the commit method, which is used to commit any pending transaction to the database, the rollback method, which causes the database to roll back to the start of any pending transaction. The close method, which is used to close a database connection. These objects represent a database cursor, which is used to manage the content of a fetch operation. Cursors created from the same connection are not isolated. That is, any changes done to the database by a cursor are immediately visible by the other cursors. Cursors created from different connections can or cannot be isolated depending on how the transaction support is implemented. A database cursor is a control structure that enables transversal over the records in a database. It behaves like a file name or file handle in a programming language. Just as a program opens a file to access its contents, it opens a cursor to gain access to the query results. Similarly, the program closes a file to end its access and closes a cursor to end access to the query results. Another similarity is that just as file handle keeps track of the program's current position within an open file, a cursor keeps track of the program's current position within the query results. Let's walk through a Python application that uses the DB API to query a database. First, you import your database module by using the Connect API from that module. To open a connection to the database, you use the Connect constructor and pass in the parameters, that is, the database name, username, and password. The Connect function returns connection object. After this, you create a cursor object on the connection object. The cursor is used to run queries and fetch results. After running the queries using the cursor, we also use the cursor to fetch the results of the query. Finally, when the system is done running the queries, it frees all resources by closing the connection. Remember that it is always important to close connections to avoid unused connections taking up resources. Thanks for watching this video.
Hello, and welcome to connecting to a database using the IBM_DB API. After completing this lesson, you will be able to understand the IBM_DB API, as well as the credentials required to connect to a database using Python. We will also demonstrate how to connect to an IBM DB2 database using Python code written on a Jupyter notebook. The IBM_DB API provides a variety of useful Python functions for accessing and manipulating data in an IBM data server database, including functions for connecting to a database, preparing and issuing SQL statements, fetching rows from result sets, calling stored procedures, committing and rolling back transactions, handling errors, and retrieving metadata. The IBM_DB API uses the IBM Data Server driver for ODBC and CLI APIs to connect to IBM DB2 and Informix. We import the IBM_DB library into our Python application. Connecting to the DB2 requires the following information: a driver name, a database name, a host DNS name or IP address, a host port, a connection protocol, a user ID, and a user password. Here is an example of creating a DB2 database connection in Python. We create a connection object, DSN, which stores the connection credentials. The connect function of the IBM_DB API will be used to create a non-persistent connection. The DSN object is passed as a parameter to the connection function. If a connection has been established with the database, then the code returns connected as the output, otherwise the output will be unable to connect to database. Then we free all resources by closing the connection. Remember that it is always important to close connections so that we can avoid unused connections taking up resources. Thank you for watching this video. Hello, and welcome to creating tables, loading data, and querying data. After completing this lesson, you will be able to understand basic concepts related to creating tables, loading data, and querying data using Python, as well as demonstrate an example of how to perform these tasks using the IBM DB2 on Cloud database and Jupyter notebooks. For this example, we will be using DB2 as the database. We first obtain a connection resource by connecting to the database by using the connect method of the IBM_DB API. There are different ways of creating tables in DB2. One is using the web console provided by DB2, and the other option is to create tables from any SQL, R, or Python environments. Let's take a look at how to create tables in DB2 from our Python application. Here is a sample table of a commercial trucks database. Let's see how we can create the trucks table in the DB2 using Python code. To create a table, we use the IBM_DB exec_immediate function. The parameters for the function are connection, which is a valid database connection resource that is returned from the IBM_DB connect or IBM_DB pconnect function. Statement, which is a string that contains the SQL statement. And options, which is an optional parameter that includes a dictionary that specifies the type of cursor to return for result sets. Here is the code to create a table called trucks in Python. We use the IBM_DB exec_immediate function of the IBM_DB API. The connection resource that was created passes the first parameter to this function. The next parameter is the SQL statement, which is the create table query used to create the trucks table. The new table created will have 5 columns. Serial_no will be the primary key. Now let's take a look at loading data. We use the IBM_DB exec_immediate function of the IBM_DB API. The connection resource that was created passes the first parameter to this function. The next parameter is the SQL statement, which is the insert into query used to insert data in the trucks table. A new row will be added to the trucks table. Similarly, we add more rows to the trucks table using the IBM_DB exec_immediate function. Now that your Python code has been connected to a database instance and the database table has been created and populated with data, let's see how we can fetch data from the trucks table that we created on DB2 using Python code. We use the IBM_DB exec_immediate function of the IBM_DB API. The connection resource that was created passed as the first parameter to this function. The next parameter is the SQL statement, which is the select from table query. The Python code returns the output, which shows the fields of the data in the trucks table. You can check if the output returned by the select query shown is correct by referring to the DB2 console. Let's look at how we can use pandas to retrieve data from the database tables. Pandas is a popular Python library that contains high-level data structures and manipulation tools designed to make data analysis fast and easy in Python. We load data from the trucks table into a data frame called df. A data frame represents a tabular spreadsheet-like data structure containing an ordered collection of columns, each of which can be a different value type. Thanks for watching this video. Hello, and welcome to Analyzing Data with Python. After completing this video, you will be able to understand basic concepts related to performing exploratory analysis on data. We will demonstrate an example of how to store data using the IBM DB2 on Cloud database, and then use Python to do some basic data analysis on this data. In this video, we will be using the McDonald's menu nutritional facts data for popular menu items at McDonald's, while using Python to perform basic exploratory analysis. McDonald's is an American fast food company and the world's largest restaurant chain by revenue. Although McDonald's is known for fast food items such as hamburgers, French fries, soft drinks, milkshakes, and desserts, the company has added to its menu salads, fish, smoothies, and fruit. McDonald's provides nutrition analysis of their menu items to help you balance your McDonald's meal with other foods you eat. The dataset used in this lesson has been obtained from the Nutritional Facts for McDonald's menu from Kaggle. We need to create a table on DB2 to store the McDonald's menu nutrition facts dataset that we will be using. We will also be using the console provided by DB2 for this process. There are 4 steps involved in loading data into a table: source, target, define, and finalize. We first load the spreadsheet into the DB2 using the console. We then select the target schema, and then you will be given an option to load the data into an existing table or create a new table. When you choose to create a new table, you have the option to specify the table name. Next, you will see a preview of the data where you can also define the columns and data types. Review the settings and begin the load. When the loading is complete, you can see the statistics on the loaded data. Next, view the table to explore further. DB2 allows you to analyze data using in-database analytics, APIs, RStudio, or Python. The data has been loaded into our relational database. You can run Python scripts that retrieve data from and write data to a DB2 database. Such scripts can be powerful tools to help you analyze your data. For example, you can use them to generate statistical models based on data in your database, and to plot the results of these models. In this lesson, we will be using Python scripts that will be run within a Jupyter notebook. Now, after obtaining a connection resource by connecting to the database by using the connect method of the IBM _DB API, we use the SQL select query to verify the number of rows that have been loaded in the table created. The figure shows a snapshot of the output. The output obtained is 260, which is similar to the number of rows in the DB2 console. Now let's see how we can use pandas to retrieve data from the database tables. We load data from the McDonald's _nutrition table into the data frame df using the read_SQL method. The SQL select query and the connection object are passed as parameters to the read_SQL method. We can view the first few rows of the data frame df that we created using the head method. Now it's time to learn about your data. Pandas methods are equipped with a set of common mathematical and statistical methods. Let's use the describe method to view the summary statistics of the data in the data frame. Then explore the output of the describe method. We see that there are 260 observations or food items in our data frame. We also see that there are 9 unique categories of food items in our data frame. We can also see summary statistics information such as frequency, mean, median, standard deviation, etc. for the 260 food items across the different variables. For example, the maximum value for total fat is 118. Let's investigate this data further. Let's try to understand one of the nutrients in the food items, which is sodium. A main source of sodium is table salt. The average American eats 5 or more teaspoons of salt each day. This is about 20 times as much as the body needs. Sodium is found naturally in foods, but a lot of it is added during processing and preparation. Many foods that do not taste salty may still be high in sodium. Large amounts of sodium can be hidden in canned, processed, and convenience foods. Sodium controls fluid balance in our bodies and maintains blood volume and blood pressure. Eating too much sodium may raise blood pressure and cause fluid retention, which could lead to swelling of the legs and feet or other health issues. When limiting sodium in your diet, a common target is to eat less than 2,000 milligrams of sodium per day. Now, using the nutrition data set from McDonald's, let's do some basic data analysis to answer the question: which food item has the maximum sodium content? We first use visualization to explore the sodium content of food items. Using the swarm plot method provided by the Seaborn package, we create a categorical scatter plot as shown on the right. Then give, as the input, category on the x-axis, sodium on the y-axis, and the data will be the data frame df that contains the nutritional dataset from McDonald's. The plot shows the sodium values for the different food items by category. Notice a high value of around 3,600 for sodium on the scatter plot. We will be learning about visualizations later in this module. Let's further explore this high sodium value and identify which food items on the menu have this value for sodium. Let's do some basic data analysis using Python to find which food items on the menu have maximum sodium content. To check the values of sodium levels in the food items within the dataset, we use the code as shown in Code 1. The describe method is used to understand the summary statistics associated with sodium. Notice that the maximum value of sodium is given as 3,600. Now let's further explore the row associated with the maximum sodium variable as shown in Code 2. We use the IDX max method to compute the index values at which the maximum value of sodium is obtained in the data frame. We see that the output is 82. Now let's find the item name associated with the 82nd item in our data frame. As shown in code 3, we will use the .at method to find the item name by passing the index of 82 and the column name item to be returned for the 82nd row. Finally, we find that the food item on the menu that has the highest sodium content is Chicken McNuggets, 40 pieces. Visualizations are very useful for initial data exploration. They can help us understand relationships, patterns, and outliers in the data. Let's first create a scatter plot with protein on the x-axis and total fat on the y-axis. Scatter plots are very popular visualization tools and show the relationship between two variables with a point for each observation. To do this, we can use the joint plot function provided by the Seaborn package and give as input protein on the x-axis and total fat on the y-axis. And the data will be the data frame DF that contains the nutritional data set from McDonald's. The output scatter plot is shown on the right side. The plot has an interesting shape. It shows the correlation between the two variables, protein and fat. Correlation is a measure of association between two variables and has a value of between -1 and +1. We see that the points on the scatter plot are closer to a straight line in the positive direction, so we have a positive correlation between the two variables. On the top right corner of the scatter plot, we have the values of the Pearson correlation, 0.81, and the significance of the correlation denoted as p, which is a good value that shows the variables are certainly correlated. The plot also shows two histograms, one on the top and the other on the right side. The histogram on the top is that of the variable protein, and the histogram on the right side is that of the variable total fat. We also notice that there is a point on the scatter plot outside the general pattern. This is a possible outlier. Now let's see how we can visualize data using box plots. Box plots are charts that indicate the distribution of one or more variables. The box in a box plot captures the middle 50% of data. Lines and points indicate possible skewness and outliers. Let's create a box plot for sugar. The function we are going to use is boxplot from the Seaborn package. We give the column name sugars as input to the boxplot function. The output is shown on the right side, where we have the boxplot with average values of sugar in food items around 30 grams. We also notice a few outliers that indicate food items with extreme values of sugar. There exists food items in the dataset that have sugar content of around 128 grams. Candies may be among these high sugar content food items on the menu. Now that you know how to do basic exploratory data analysis using pandas and visualization tools, proceed to the labs in this module where you can practice the concepts learned. Thank you for watching this video.
Hello and welcome. In this video, we'll give you a few hints and tips for working with real-world datasets. Many of the real-world datasets are made available as .csv files. These are text files which contain data values typically separated by commas. In some cases, a different separator, such as a semicolon, may be used. For this video, we will use an example of a file called dogs.csv. Although this is a fictional dataset that contains names of dogs and their breeds, we will use it to illustrate concepts that you will then apply to real datasets. Sample contents of the dogs.csv file are shown here. The first row in the table, in many cases, contains attribute labels, which map to column names in a table. In dogs.csv, the first row contains the name of 3 attributes. ID is the name of the first attribute, and the subsequent rows contain ID values of 1, 2, and 3. The name of the dog is the second attribute. In this case, the dog names, Wolfie, Fluffy, and Huggy, are the values. And the third attribute is called breed, either the dominant breed or pure breed name. It has values of German Shepherd, Pomeranian, and Labrador. As we've just seen, CSV files can have the first or a header row that contains the names of the attributes. If you're loading the data into the database using the Visual Load tool in the database console, ensure the header in first row is enabled. This will map the attribute names in the first row of the CSV file into column names in the database table, and the rest of the rows into the data rows in the table, as shown here. Note that the default column names may not always be database or query friendly, and if that is the case, you may want to edit them before the table is created. Now, let's talk about querying column names that are lower or mixed case, that is, a combination of upper and lower case. Let's assume we loaded the dogs.csv file using the default column names from the CSV. If we try to retrieve the contents of the ID column using the query select lowercase id from dogs, we'll get an error, as shown, indicating the ID is not valid. This is because the database parser assumes uppercase names by default, whereas when we loaded the CSV file into the database, it had the ID column name in mixed case, i.e., an uppercase I and a lowercase d. In this case, to select data from a column with a mixed case name, we need to specify the column name in its correct case within double quotes, as follows. Select double quotes, uppercase I, lowercase d, end double quotes from dogs. Ensure you use double quotes around the column name and not single quotes. Next, we'll cover querying column names that have spaces and other characters. In a CSV file, if the name of the column contains spaces, by default the database may map them to underscores. For example, in the name of dog column, there are spaces in between the three words. The database may change it to name underscore of underscore dog. Other special characters like parentheses or brackets may also get mapped to underscores. Therefore, when you write a query, ensure you use proper case formatting within quotes and substitute special characters to underscores, as shown in this example. Select ID, name of dog, breed, dominant breed if not pure breed, from dogs. Please note the underscores separating the words within double quotes. Also, note the double underscore between breed and dominant as shown. Finally, it's also important to note the trailing underscore after the word breed near the end of the query. This is used in place of the closing bracket. When using quotes in Jupyter Notebooks, you may be issuing queries in a notebook by first assigning them to Python variables. In such cases, if your query contains double quotes, for example, to specify a mixed case column name, you could differentiate the quotes by using single quotes for the Python variable to enclose the SQL query and double quotes for the column names. For example, select query equals open single quote select ID in double quotes from dogs close single quote. Now, what if you need to specify single quotes within the query, for example, to specify a value in the where clause? In this case, you can use backslash as the escape character as follows. Select query equals open single quote select star from dogs where open double quote name of dog close double quote equals backslash single quote Huggy backslash single quote close single quote. If you have very long queries, such as join queries or nested queries, it may be useful to split the query into multiple lines for improved readability. In Python notebooks, you can use the backslash character to indicate continuation to the next row, as shown in this example. %SQL select ID, name of dog, backslash from dogs, backslash where name of dog equals Huggy. It would be helpful at this point to take a moment to review the special characters as shown. Please keep in mind that you might get an error if you split the query into multiple lines in a Python notebook without the backslash. When using SQL Magic, you can use the $%SQL in the first line of the cell in Jupyter notebooks. It implies that the rest of the content of the cell is to be interpreted by SQL Magic. For example, $SQL, new row, select ID, name of dog, new row from dogs, new row where name of dog equals Huggy. Again, please note the special characters as shown. When using $SQL, the backslash is not needed at the end of each line. At this point, you might be asking, how would you restrict the number of rows retrieved? It's a good question because a table may contain thousands or even millions of rows, and you may only want to see some sample data, or look at just a few rows to see what kind of data the table contains. You may be tempted to just do select star from table name to retrieve the results in a pandas data frame and do a head function on it. But doing so may take a long time for a query to run. Instead, you can restrict the result set by using the limit clause. For example, use the following query to retrieve just the first 3 rows in a table called census data. Select star from census_data limit 3. In this video, we looked at some considerations and tips for working with real-world datasets. Thanks for watching. Hello and welcome. In this video, we'll look at how to get information about tables and their columns in a database. Now, how would you get a list of tables in the database? Sometimes your database may contain several tables and you may not remember the correct name. For example, you may wonder whether the table is called dog, dogs, or four-legged mammals. Database systems typically contain system or catalog tables from where you can query the list of tables and get their properties. In DB2, this catalog is called syscat tables. In SQL Server, it's information schema tables, and in Oracle, it's all tables or user tables. To get a list of tables in a DB2 database, you can run the following query. Select star from syscat tables. This select statement will return too many tables, including system tables, so it's better to filter the result as shown here. Select tab schema, tab name, create _time from syscat tables, where tab schema equals ABC12345. Please ensure that you replace ABC12345 with your own DB2 username. When you do a select star from syscat tables, you get all the properties of the tables. Sometimes we're interested in specific properties such as creation time. Let's say you've created several tables with similar names. For example, dog1, dog_test, dog test1, and so on. But you want to check which of these tables was the last one you created. To do so, you can issue a query like select tab schema, tab name, create _time from syscat tables, where tab schema equals QCM54853. The output will contain the schema name, table name, and creation time for all tables in your schema. Next, let's talk about how to get a list of columns in a table. If you can't recall the exact name of a column, for example, whether it had any lowercase characters or an underscore in its name, in DB2 you can issue a query like the one shown here. Select star from syscat columns where tab name equals dogs. For your information, in MySQL you can simply run the command show columns from dogs. Or you may want to know specific properties like the data type and length of the data type. In DB2, you can issue a statement like select distinct name, call type, length from sys IBM, sys columns, where TB name equals dogs. Here we look at the results of retrieving column properties for a real table called Chicago Crime Data from a Jupyter notebook. Notice in the output you can tell certain column names show different cases. For example, the column titled Arrest has an uppercase A and the rest of the characters are lowercase. So, keep in mind that when you refer to this column in your query, not only must you enclose the word arrest within double quotes, you must also preserve the correct case inside the quotes. In this video, we saw how to retrieve table and column information. Thanks for watching.
In this video, we'll be talking about data analysis and the scenario in which we'll be playing the data analyst or data scientist. But before we begin talking about the problem, used car prices, we should first understand the importance of data analysis. As you know, data is collected everywhere around us, whether it's collected manually by scientists or collected digitally every time you click on a website or your mobile device. But data does not mean information. Data analysis, and in essence data science, helps us unlock the information and insights from raw data to answer our questions. So data analysis plays an important role by helping us to discover useful information from the data, answer questions, and even predict the future or the unknown. So let's begin with our scenario. Let's say we have a friend named Tom, and Tom wants to sell his car. But the problem is, he doesn't know how much he should sell his car for. Tom wants to sell his car for as much as he can, but he also wants to set the price reasonably so someone would want to purchase it. So the price he sets should represent the value of the car. How can we help Tom determine the best price for his car? Let's think like data scientists and clearly define some of his problems. For example, is there data on the prices of other cars and their characteristics? What features of cars affect their prices? Color? Brand? Does horsepower also affect the selling price, or perhaps something else? As a data analyst or data scientist, these are some of the questions we can start thinking about. To answer these questions, we're going to need some data. In the next videos, we'll be going into how to understand the data, how to import it into Python, and how to begin looking into some basic insights from the data. In this video, we'll be looking at the dataset on used car prices. The dataset used in this course is an open dataset by Jeffrey C. Schlimmer. This dataset is in CSV format, which separates each of the values with commas, making it very easy to import in most tools or applications. Each line represents a row in the dataset. In the hands-on lab for this module, you'll be able to download and use the CSV file. Do you notice anything different about the first row? Sometimes the first row is a header which contains a column name for each of the 26 columns, but in this example, it's just another row of data. So here's the documentation on what each of the 26 columns represent. There are a lot of columns, and I'll just go through a few of the column names, but you can also check out the link at the bottom of the slide to go through the descriptions yourself. The first attribute, symboling, corresponds to the insurance risk level of a car. Cars are initially assigned a risk factor symbol associated with their price. Then, if an automobile is more risky, this symbol is adjusted by moving it up the scale. A value of +3 indicates that the auto is risky. -3, that it's probably pretty safe. The second attribute, normalized losses, is the relative average loss payment per insured vehicle year. This value is normalized for all autos within a particular size classification. Two-door small, station wagons, sports specialty, etc., and represents the average loss per car per year. The values range from 65 to 256. The other attributes are easy to understand. If you would like to check out more details, refer to the link at the bottom of the slide. Okay, after we understand the meaning of each feature, we'll notice that the 26th attribute is price. This is our target value or label, in other words. This means price is the value that we want to predict from the dataset, and the predictors should be all the other variables listed, like symboling, normalized losses, make, and so on. Thus, the goal of this project is to predict price in terms of other car features. Just a quick note, this dataset is actually from 1985, so the car prices for the models may seem a little low, but just bear in mind that the goal of this exercise is to learn how to analyze the data. In order to do data analysis in Python, we should first tell you a little bit about the main packages relevant to analysis in Python. A Python library is a collection of functions and methods that allow you to perform lots of actions without writing any code. The libraries usually contain built-in modules providing different functionalities which you can use directly. And there are extensive libraries offering a broad range of facilities. We have divided the Python data analysis libraries into 3 groups. The first group is called Scientific Computing Libraries. Pandas offers data structure and tools for effective data manipulation and analysis. It provides fast access to structured data. The primary instrument of Pandas is a 2-dimensional table consisting of column and row labels, which are called a data frame. It is designed to provide easy indexing functionality. The NumPy library uses arrays for its inputs and outputs. It can be extended to objects for matrices, and with minor coding changes, developers can perform fast array processing. SciPy includes functions for some advanced math problems as listed on this slide, as well as data visualization. Using data visualization methods is the best way to communicate with others, showing them meaningful results of analysis. These libraries enable you to create graphs, charts, and maps. The matplotlib package is the most well-known library for data visualization. It is great for making graphs and plots. The graphs are also highly customizable. Another high-level visualization library is Seaborn. It is based on matplotlib. It's very easy to generate various plots such as heat maps, time series, and violin plots. With machine learning algorithms, we're able to develop a model using our dataset and obtain predictions. The algorithmic libraries tackle some machine learning tasks from basic to complex. Here we introduce 2 packages. The scikit-learn library contains tools for statistical modeling, including regression, classification, clustering, and so on. This library is built on NumPy, SciPy, and matplotlib. StatsModels is also a Python module that allows users to explore data, estimate statistical models, and perform statistical tests. In this video, we'll look at how to read in data using Python's pandas package. Once we have our data in Python, then we can perform all the subsequent data analysis procedures we need. Data acquisition is a process of loading and reading data into Notebook from various sources. To read any data using Python's pandas package, there are 2 important factors to consider: format and file path. Format is the way data is encoded. We can usually tell different encoding schemes by looking at the ending of the file name. Some common encodings are CSV, JSON, XLSX, HDF, and so forth. The path tells us where the data is stored. Usually it is stored either on the computer we are using or online on the internet. In our case, we found a data set of used cars which was obtained from the web address shown on the slide. When Jerry entered the web address in his web browser, he saw something like this. Each row is 1 data point. A large number of properties are associated with each data point. Because the properties are separated from each other by commas, we can guess the data format is CSV, which stands for comma-separated values. At this point, these are just numbers and don't mean much to humans, but once we read in this data, we can try to make more sense out of it. In Pandas, the readCSV method can read in files with columns separated by commas into a Pandas data frame. Reading data in Pandas can be done quickly in 3 lines. First, import Pandas, then define a variable with a file path, and then use the readCSV method to import the data. However, Read CSV assumes that the data contains a header. Our data on used cars has no column headers, so we need to specify Read CSV to not assign headers by setting header to none. After reading the data set, it is a good idea to look at the data frame to get a better intuition and to ensure that everything occurred the way you expected. Since printing the entire data set may take up too much time and resources, to save time, we can just use dataframe.head to show the first n rows of the data frame. Similarly, dataframe.tail shows the bottom n rows of data frame. Here we printed out the first 5 rows of data. It seems that the dataset was read successfully. We can see that pandas automatically set the column header as a list of integers because we set header equals none when we read the data. It is difficult to work with the data frame without having meaningful column names. However, we can assign column names in pandas. In our present case, it turned out that we have the column names in a separate file online. We first put the column names in a list called headers. Then, we set df.columns equals headers to replace the default integer headers by the list. If we use the head method introduced in the last slide to check the dataset, we see the correct headers inserted at the top of each column. At some point in time, after you've done operations on your data frame, you may want to export your pandas data frame to a new CSV file. You can do this using the method to_CSV. To do this, specify the file path, which includes the file name, that you want to write to. For example, if you would like to save data frame df as automobile.csv to your own computer, you can use the syntax df.to_CSV. For this course, we will only read and save CSV files. However, pandas also supports importing and exporting of most data file types with different dataset formats. The code syntax for reading and saving other data formats is very similar to read or save CSV file. Each column shows a different method to read and save files into a different format. In this video, we introduce some simple pandas methods that all data scientists and analysts should know when using Python, pandas, and data. At this point, we assume that the data has been loaded. It's time for us to explore the data set. Pandas has several built-in methods that can be used to understand the data type of features or to look at the distribution of data within the data set. Using these methods gives an overview of the data set and also point out potential issues, such as the wrong data type of features which may need to be resolved later on. Data has a variety of types. The main types stored in pandas objects are object, float, int, and datetime. The data type names are somewhat different from those in native Python. This table shows the differences and similarities between them. Some are very similar, such as the numeric data types int and float. The object pandas type function similar to string in Python, save for the change in name, while the datetime pandas type is a very useful type for handling time series data. There are 2 reasons to check data types in a data set. Pandas automatically assigns types based on the encoding it detects from the original data table. For a number of reasons, this assignment may be incorrect. For example, it should be awkward if the car price column, which we should expect to contain continuous numeric numbers, is assigned the data type of object. It would be more natural for it to have the float type. Jerry may need to manually change the data type to float. The second reason is that it allows an experienced data scientist to see which Python functions can be applied to a specific column. For example, some math functions can only be applied to numerical data. If these functions are applied to non-numerical data, an error may result. When the dtype method is applied to the data set, the data type of each column is returned in a series. A good data scientist's intuition tells us that most of the data types make sense. The make of cars, for example, are names, so this information should be of type object. The last one on the list could be an issue. As bore is a dimension of an engine, we should expect a numerical data type to be used. Instead, the object type is used. In later sections, Jerry will have to correct these type mismatches. Now we would like to check the statistical summary of each column to learn about the distribution of data in each column. The statistical metrics can tell the data scientist if there are mathematical issues that may exist, such as extreme outliers and large deviations. The data scientist may have to address these issues later. To get the quick statistics, we use the describe method. It returns the number of terms in the column as count, average column value as mean, column standard deviation as STD, the maximum minimum values, as well as the boundary of each of the quartiles. By default, the dataframe.describe function skips rows and columns that do not contain numbers. It is possible to make the describe method work for object type columns as well. To enable a summary of all the columns, we could add an argument include equals all inside the describe function bracket. Now the outcome shows the summary of all the 26 columns, including object typed attributes. We see that for the object type columns, a different set of statistics is evaluated, like unique, top, and frequency. Unique is the number of distinct objects in the column. Top is the most frequently occurring object, and freq is the number of times the top object appears in the column. Some values in the table are shown here as NaN, which stands for not a number. This is because that particular statistical metric cannot be calculated for that specific column data type. Another method you can use to check your dataset is the dataframe.info function. This function shows the top 30 rows and bottom 30 rows of the data frame. Hello! In this video, you will learn how to access databases using Python. Databases are powerful tools for data scientists. After completing this module, you will be able to explain the basic concepts related to using Python to connect to databases. This is how a typical user accesses databases using Python code written on a Jupyter notebook, a web-based editor. There is a mechanism by which the Python program communicates with the DBMS. The Python code connects to the database using API calls. We will explain the basics of SQL APIs and Python DB APIs. An application programming interface is a set of functions that you can call to get access to some type of service. A SQL API consists of library function calls as an application programming interface API for the DBMS. To pass SQL statements to the DBMS, an application program calls functions in the API, and it calls other functions to retrieve query results and status information from the DBMS. The basic operation of a typical SQL API is illustrated in the figure. The application program begins its database access with one or more API calls that connect the program to the DBMS. To send a SQL statement to the DBMS, the program builds the statement as a text string in a buffer and then makes an API call to pass the buffer contents to the DBMS. The application program makes API calls to check the status of its DBMS request and to handle errors. The application program ends its database access with an API call that disconnects it from the database. DB API is Python's standard API for accessing relational databases. It is a standard that allows you to write a single program that works with multiple kinds of relational databases, instead of writing a separate program for each one. So if you learn the DB API functions, then you can apply that knowledge to use any database with Python. The two main concepts in the Python DB API are connection objects and query objects. You use connection objects to connect to a database and manage your transactions. Cursor objects are used to run queries. You open a cursor object and then run queries. The cursor works similar to a cursor in a text processing system where you scroll down in your results set and get your data into the application. Cursors are used to scan through the results of a database. Here are the methods used with connection objects. The cursor method returns a new cursor object using the connection. The commit method is used to commit any pending transaction to the database. The rollback method causes the database to roll back to the start of any pending transaction. The close method is used to close a database connection. Let's walk through a Python application that uses the DB API to query a database. First, you import your database module by using the Connect API from that module. To open a connection to the database, you use the connection function and pass in the parameters, that is, the database name, username, and password. The connect function returns a connection object. After this, you create a cursor object on the connection object. The cursor is used to run queries and fetch results. After running the queries using the cursor, we also use the cursor to fetch the results of the query. Finally, when the system is done running the queries, it frees all resources by closing the connection. Remember that it is always important to close connections to avoid unused connections taking up resources. Thanks for watching this video. In this video, we'll be going through some data pre-processing techniques. If you're unfamiliar with the term, data pre-processing is a necessary step in data analysis. It is the process of converting or mapping data from one raw form into another format to make it ready for further analysis. Data pre-processing is often called data cleaning or data wrangling, and there are likely other terms. Here are the topics that we'll be covering in this module. First, we'll show you how to identify and handle missing values. A missing value condition occurs whenever a data entry is left empty. Then we'll cover data formats. Data from different sources may be in various formats, in different units, or in various conventions. We will introduce some methods in Python pandas that can standardize the values into the same format, or unit, or convention. After that, we'll cover data normalization. Different columns of numerical data may have very different ranges, and direct comparison is often not meaningful. Normalization is a way to bring all data into a similar range for more useful comparison. Specifically, we'll focus on the techniques of centering and scaling. And then we'll introduce data binning. Binning creates bigger categories from a set of numerical values. It is particularly useful for comparison between groups of data. And lastly, we'll talk about categorical variables and show you how to convert categorical values into numeric variables to make statistical modeling easier. In Python, we usually perform operations along columns. Each row of the column represents a sample, i.e., a different used car in the database. You access a column by specifying the name of the column. For example, you can access symboling and body style. Each of these columns is a pandas series. There are many ways to manipulate data frames in Python. For example, you can add a value to each entry of a column. To add one to each symboling entry, use this command. This changes each value of the data frame column by adding 1 to the current value. In this video, we will introduce the pervasive problem of missing values, as well as strategies on what to do when you encounter missing values in your data. When no data value is stored for a feature for a particular observation, we say this feature has a missing value. Usually, missing value in dataset appears as $NA, 0, or just a blank cell. In the example here, the normalized losses feature has a missing value, which is represented with NaN. But how can you deal with missing data? There are many ways to deal with missing values, and this is regardless of Python, R, or whatever tool you use. Of course, each situation is different and should be judged differently. However, these are the typical options you can consider. The first is to check if the person or group that collected the data can go back and find what the actual value should be. Another possibility is just to remove the data where that missing value is found. When you drop data, you could either drop the whole variable or just the single data entry with the missing value. If you don't have a lot of observations with missing data, usually dropping the particular entry is the best. If you're removing data, you want to look to do something that has the least amount of impact. Replacing data is better, since no data is wasted. However, it is less accurate since we need to replace missing data with a guess of what the data should be. One standard replacement technique is to replace missing values by the average value of the entire variable. As an example, Suppose we have some entries that have missing values for the normalized losses column, and the column average for entries with data is 4,500. While there is no way for us to get an accurate guess of what the missing values under the normalized losses column should have been, you can approximate their values using the average value of the column, 4,500. But what if the values cannot be averaged, as with categorical variables? For a variable like fuel type, there isn't an average fuel type, since the variable values are not numbers. In this case, one possibility is to try using the mode the most common, like gasoline. Finally, sometimes we may find another way to guess the missing data. This is usually because the data gatherer knows something additional about the missing data. For example, he may know that the missing values tend to be old cars, and the normalized losses of old cars are significantly higher than the average vehicle. And of course, finally, in some cases, you may simply want to leave the missing data as missing data. For one reason or another, it may be useful to keep that observation, even if some features are missing. Now let's go into how to drop missing values or replace missing values in Python. To remove data that contains missing values, Pandas library has a built-in method called dropNA. Essentially, with the dropNA method, you can choose to drop rows or columns that contain missing values, like NaN. So you'll need to specify axis equals 0 to drop the rows, or axis equals 1 to drop the columns that contain the missing values. In this example, there is a missing value in the price column. Since the price of used cars is what we're trying to predict in our upcoming analysis, we'd have to remove the cars, the rows, that don't have a listed price. It can simply be done in one line of code, using dataframe.dropNA. Setting the argument inPlace to true allows the modification to be done on the dataset directly. InPlace equals true, just writes the result back into the data frame. This is equivalent to this line of code. Don't forget that this line of code does not change the data frame, but is a good way to make sure that you are performing the correct operation. To modify the data frame, you have to set the parameter InPlace equal to true. You should always check the documentation if you are not familiar with a function or method. The Pandas webpage has lots of useful resources. To replace missing values like NaNs with actual values, Pandas library has a built-in method called replace, which can be used to fill in the missing values with the newly calculated values. As an example, assume that we want to replace the missing values of the variable normalized losses by the mean value of the variable. Therefore, the missing value should be replaced by the average of the entries within that column. In Python, first we calculate the mean of the column. Then we use the method replace to specify the value we would like to be replaced as the first parameter, in this case, NaN. The second parameter is the value we would like to replace it with, i.e. the mean in this example. This is a fairly simplified way of replacing missing values. There are, of course, other techniques, such as replacing missing values for the average of the group, instead of the entire data set. So we've gone through two ways in Python to deal with missing data. We learned to drop problematic rows or columns containing missing values, and then we learned how to replace missing values with other values. But don't forget the other ways to deal with missing data. You can always check for a higher quality dataset or source. Or, in some cases, you may want to leave the missing data as missing data. In this video, we'll look at the problem of data with different formats, units, and conventions, and the Pandas methods that help us deal with these issues. Data is usually collected from different places, by different people, which may be stored in different formats. Data formatting means bringing data into a common standard of expression that allows users to make meaningful comparisons. As a part of dataset cleaning, data formatting ensures that data is consistent and easily understandable. For example, people may use different expressions to represent New York City, such as uppercase N, uppercase Y, uppercase N, lowercase y, uppercase N, uppercase y, and New York. Sometimes this unclean data is a good thing to see. For example, if you're looking at the different ways people tend to write New York, then this is exactly the data that you want. Or if you're looking for ways to spot fraud, perhaps writing N.Y. is more likely to predict an anomaly than if someone wrote out New York in full. But perhaps, more often than not, we just simply want to treat them all as the same entity or format to make statistical analyses easier down the road. Referring to our used car dataset, there's a feature named city miles per gallon in the dataset, which refers to a car fuel consumption in miles per gallon unit. However, you may be someone who lives in a country that uses metric units, so you would want to convert those values to liters per 100 kilometers, the metric version. To transform miles per gallon to liters per 100 kilometers, we need to divide 235 by each value in the city miles per gallon column. In Python, this can easily be done in one line of code. You take the column and set it to equal to 235 divided by the entire column. In the second line of code, rename column name from city miles per gallon to city liters per 100 kilometers using the data frame rename method. For a number of reasons, including when you import a dataset into Python, the data type may be incorrectly established. For example, here we notice that the assigned data type to the price feature is object, although the expected data type should really be an integer or float type. It is important for later analysis to explore the feature's data type and convert them to the correct data types. Otherwise, the developed models later on may behave strangely, and totally valid data may end up being treated like missing data. There are many data types in pandas. Objects can be letters or words. int64 are integers, and floats are real numbers. There are many others that we will not discuss. To identify a feature's data type, in Python we can use the dataframe.dtypes method and check the data type of each variable in a data frame. In the case of wrong data types, the method dataframe.asType can be used to convert a data type from one format to another. For example, using asType int for the price column, you can convert the object column into an integer type variable. In this video, we'll be talking about data normalization, an important technique to understand in data pre-processing. When we take a look at the used car dataset, we notice in the data that the feature length ranges from 150 to 250, while feature width and height ranges from 50 to 100. We may want to normalize these variables so that the range of the values is consistent. This normalization can make some statistical analyses easier down the road. By making the ranges consistent between variables, normalization enables a fairer comparison between the different features, making sure they have the same impact. It is also important for computational reasons. Here is another example that will help you understand why normalization is important. Consider a data set containing two features, age and income, where age ranges from 0 to 100, while income ranges from 0 to 20,000 and higher. Income is about 1,000 times larger than age and ranges from 20,000 to 500,000. So these two features are in very different ranges. When we do further analysis, like linear regression for example, the attribute income will intrinsically influence the result more, due to its larger value. But this doesn't necessarily mean it is more important as a predictor. So, the nature of the data biases the linear regression model to weigh income more heavily than age. To avoid this, we can normalize these two variables into values that range from 0 to 1. Compare the two tables at the right. After normalization, both variables now have a similar influence on the models we will build later. There are several ways to normalize data. I will just outline 3 techniques. The first method, called simple feature scaling, just divides each value by the maximum value for that feature. This makes the new values range between 0 and 1. The second method, called min-max, takes each value x underscore old, subtract it from the minimum value of that feature, then divides by the range of that feature. Again, the resulting new values range between 0 and 1. The third method is called z-score or standard score. In this formula, for each value, you subtract the mu, which is the average of the feature, and then divide by the standard deviation, sigma. The resulting values hover around 0 and typically range between -3 and +3, but can be higher or lower. Following our earlier example, we can apply the normalization method on the length feature. First, we use the simple feature scaling method, where we divide it by the maximum value in the feature. Using the pandas method max, this can be done in just one line of code. Here's the min-max method on the length feature. We subtract each value by the minimum of that column, then divide it by the range of that column, the max minus the min. Finally, we apply the z-score method on length feature to normalize the values. Here, we apply the mean and std method on the length feature. Mean method will return the average value of the feature in the data set, and std method will return the standard deviation of the features in the data set. In this video, we'll be talking about binning as a method of data pre-processing. Binning is when you group values together into bins. For example, you can bin age into 0 to 5, 6 to 10, 11 to 15, and so on. Sometimes binning can improve accuracy of the predictive models. In addition, sometimes we use data binning to group a set of numerical values into a smaller number of bins to have a better understanding of the data distribution. As example, price. Here is an attribute range from 5,000 to 45,500. Using binning, we categorize the price into 3 bins: low price, medium price, and high prices. In the actual car data set, price is a numerical variable ranging from 5,188 to 45,400. It has 201 unique values. We can categorize them into 3 bins: low, medium, and high price cars. In Python, we can easily implement the binning. We would like 3 bins of equal bin width, so we need 4 numbers as dividers that are equal distance apart. First, we use the NumPy function linspace to return the array bins that contains 4 equally spaced numbers over the specified interval of the price. We create a list group underscore names that contains the different bin names. We use the pandas function cut to segment and sort the data values into bins. You can then use histograms to visualize the distribution of the data after they've been divided into bins. This is the histogram that we plotted based on the binning that we applied in the price feature. From the plot, it is clear that most cars have a low price, and only very few cars have high price. In this video, we'll discuss how to turn categorical variables into quantitative variables in Python. Most statistical models cannot take in objects or strings as input and, for model training, only take the numbers as inputs. In the car dataset, the fuel type feature as a categorical variable has 2 values, gas or diesel, which are in string format. For further analysis, Jerry has to convert these variables into some form of numeric format. We encode the values by adding new features corresponding to each unique element in the original feature we would like to encode. In the case where the feature fuel has 2 unique values, gas and diesel, we create 2 new features, gas and diesel. When a value occurs in the original feature, we set the corresponding value to 1 in the new feature. The rest of the features are set to 0. In the fuel example, for car B, the fuel value is diesel. Therefore, we set the feature diesel equal to 1 and the gas feature to 0. Similarly, for car D, the fuel value is gas. Therefore, we set the feature gas equal to 1 and the feature diesel equal to 0. This technique is often called one-hot encoding. In pandas, we can use get_dummies method to convert categorical variables to dummy variables. In Python, Transforming categorical variables to dummy variables is simple. Following the example, pd.get_dummies method gets the fuel type column and creates the data frame dummy_variable_1. The get_dummies method automatically generates a list of numbers, each one corresponding to a particular category of the variable. In this module, we're going to cover the basics of exploratory data analysis using Python. Exploratory data analysis, or in short, EDA, is an approach to analyze data in order to summarize main characteristics of the data, gain better understanding of the data set, uncover relationships between different variables, and extract important variables for the problem we're trying to solve. The main question we are trying to answer in this module is, what are the characteristics that have the most impact on the car price? We will be going through a couple of different useful exploratory data analysis techniques in order to answer this question. In this module, you will learn about descriptive statistics, which describe basic features of a data set and obtains a short summary about the sample and measures of the data, basic of grouping data using group by, and how this can help to transform our data set, the correlation between different variables, and lastly, advanced correlation, where we'll introduce you to various correlation statistical methods, namely Pearson correlation and correlation heat maps. In this video, we'll be talking about descriptive statistics. When you begin to analyze data, it's important to first explore your data before you spend time building complicated models. One easy way to do so is to calculate some descriptive statistics for your data. Descriptive statistical analysis helps to describe basic features of a data set and obtains a short summary about the sample and measures of the data. Let's show you a couple different useful methods. One way in which we can do this is by using the describe function in pandas. Using the describe function and applying it on your data frame, the describe function automatically computes basic statistics for all numerical variables. It shows the mean, the total number of data points, the standard deviation, the quartiles, and the extreme values. Any NaN values are automatically skipped in these statistics. This function will give you a clearer idea of the distribution of your different variables. You could have also categorical variables in your data set. These are variables that can be divided up into different categories or groups and have discrete values. For example, in our data set we have the drive system as a categorical variable, which consists of the categories forward-wheel drive, rear-wheel drive, and four-wheel drive. One way you can summarize the categorical data is by using the function value_counts. We can change the name of the column to make it easier to read. We see that we have 118 cars in the front-wheel drive category, 75 cars in the rear-wheel drive category, and 8 cars in the four-wheel drive category. Box plots are a great way to visualize numeric data, since you can visualize the various distributions of the data. The main features that the box plot shows are the median of the data, which represents where the middle data point is. The upper quartile shows where the 75th percentile is. The lower quartile shows where the 25th percentile is. The data between the upper and lower quartile represents the interquartile range. Next, you have the lower and upper extremes. These are calculated as 1.5 times the interquartile range above the 75th percentile, and as 1.5 times the IQR below the 25th percentile. Finally, box plots also display outliers as individual dots that occur outside the upper and lower extremes. With box plots, you can easily spot outliers and also see the distribution and skewness of the data. Box plots make it easy to compare between groups. In this example, using box plot, we can see the distribution of different categories of the drive wheels feature over price feature. We can see that the distribution of price between the rear wheel drive and the other categories are distinct, but the price for front wheel drive and four-wheel drive are almost indistinguishable. Oftentimes, we tend to see continuous variables in our data. These data points are numbers contained in some range. For example, in our dataset, price and engine size are continuous variables. What if we want to understand the relationship between engine size and price? Could engine size possibly predict the price of a car? One good way to visualize this is using a scatter plot. Each observation in a scatter plot is represented as a point. This plot shows the relationship between two variables. The predictor variable is the variable that you are using to predict an outcome. In this case, our predictor variable is the engine size. The target variable is the variable that you are trying to predict. In this case, our target variable is the price, since this would be the outcome. In a scatter plot, we typically set the predictor variable on the x-axis or horizontal axis, and we set the target variable on the y-axis or vertical axis. In this case, we will thus plot the engine size on the x-axis and the price on the y-axis. We are using the matplotlib function scatter here, taking in x and a y variable. Something to note is that it's always important to label your axes and write a general plot title so that you know what you're looking at. Now, how is the variable engine size related to price? From the scatter plot, we see that as the engine size goes up, the price of the car also goes up. This is giving us an initial indication that there is a positive linear relationship between these two variables. In this video, we'll cover the basics of grouping and how this can help to transform our data set. Assume you want to know, is there any relationship between the different types of drive system, forward, rear, and four-wheel drive, and the price of the vehicles? If so, which type of drive system adds the most value to a vehicle? It would be nice if we could group all the data by the different types of drive wheels and compare the results of these different drive wheels against each other. In pandas, this can be done using the group by method. The group by method is used on categorical variables. Groups the data into subsets according to the different categories of that variable. You can group by a single variable, or you can group by multiple variables by passing in multiple variable names. As an example, let's say we are interested in finding the average price of vehicles and observe how they differ between different types of body styles and drive wheels variables. To do this, we first pick out the 3 data columns we are interested in, which is done in the first line of code. We then group the reduced data according to drive wheels and body style in the second line. Since we are interested in knowing how the average price differs across the board, we can take the mean of each group and appended this bit at the very end of the line too. The data is now grouped into subcategories, and only the average price of each subcategory is shown. We can see that, according to our data, rear-wheel drive convertibles and rear-wheel drive hardtops have the highest value, while four-wheel drive hatchbacks have the lowest value. A table of this form isn't the easiest to read, and also not very easy to visualize. To make it easier to understand, we can transform this table to a pivot table by using the pivot method. In the previous table, both drive wheels and body style were listed in columns. A pivot table has one variable displayed along the columns and the other variable displayed along the rows. Just with one line of code, and by using the pandas pivot method, we can pivot the body style variable so it is displayed along the columns, and the drive wheels will be displayed along the rows. The price data now becomes a rectangular grid, which is easier to visualize. This is similar to what is usually done in Excel spreadsheets. Another way to represent the pivot table is using a heat map plot. Heat map takes a rectangular grid of data and assigns a color intensity based on the data value at the grid points. It is a great way to plot the target variable over multiple variables, and through this get visual clues of the relationship between these variables and the target. In this example, we use pyplot's pcolor method to plot heat map and convert the previous pivot table into a graphical form. We specified the red-blue color scheme. In the output plot, each type of body style is numbered along the x-axis, and each type of drive wheels is numbered along the y-axis. The average prices are plotted with varying colors based on their values, according to the color bar. We see that the top section of the heat map seems to have higher prices than the bottom section. In this video, we'll talk about the correlation between different variables. Correlation is a statistical metric for measuring to what extent different variables are interdependent. In other words, when we look at two variables over time, if one variable changes, how does this affect change in the other variable? For example, smoking is known to be correlated to lung cancer, since you have a higher chance of getting lung cancer if you smoke. In another example, there is a correlation between umbrella and rain variables, where more precipitation means more people use umbrellas. Also, if it doesn't rain, people would not carry umbrellas. Therefore, we can say that umbrellas and rain are interdependent, and by definition, they are correlated. It is important to know that correlation doesn't imply causation. In fact, we can say that umbrella and rain are correlated, but we would not have enough information to say whether the umbrella caused the rain or the rain caused the umbrella. In data science, we usually deal more with correlation. Let's look at the correlation between engine size and price. This time we'll visualize these two variables using a scatter plot and an added linear line called a regression line, which indicates the relationship between the two. The main goal of this plot is to see whether the engine size has any impact on the price. In this example, you can see that the straight line through the data points is very steep, which shows that there is a positive linear relationship between the two variables. With increase in values of engine size, values of price go up as well, and the slope of the line is positive, so there is a positive correlation between engine size and price. We can use Seaborn-Reg plot to create the scatter plot. As another example, now let's look at the relationship between highway miles per gallon to see its impact on the car price. As we can see in this plot, when highway miles per gallon value goes up, the value of price goes down. Therefore, there is a negative linear relationship between highway miles per gallon and price. Although this relationship is negative, the slope of the line is steep, which means that the highway miles per gallon is still a good predictor of price. These two variables are said to have a negative correlation. Finally, we have an example of a weak correlation. For example, both low peak RPM and high values of peak RPM have low and high prices. Therefore, we cannot use RPM to predict the values. In this video, we'll introduce you to various correlation statistical methods. One way to measure the strength of the correlation between continuous numerical variables is by using a method called Pearson correlation. Pearson correlation method will give you two values, the correlation coefficient and the p-value. So how do we interpret these values? For the correlation coefficient, a value close to 1 implies a large positive correlation, while a value close to -1 implies a large negative correlation, and a value close to 0 implies no correlation between the variables. Next, the p-value will tell us how certain we are about the correlation that we calculated. For the p-value, a value less than 0.001 gives us a strong certainty about the correlation coefficient that we calculated. A value between 0.001 and 0.05 gives us moderate certainty. A value between 0.05 and 0.1 will give us a weak certainty, and a p-value larger than 0.1 will give us no certainty of correlation at all. We can say that there is a strong correlation when the correlation coefficient is close to 1 or -1 and the p-value is less than 0.001. The following plot shows data with different correlation values. In this example, we want to look at the correlation between the variables horsepower and car price. See how easy you can calculate the Pearson correlation using the SciPy stats package? We can see that the correlation coefficient is approximately 0.8, and this is close to 1, so there is a strong positive correlation. We can also see that the p-value is very small, much smaller than 0.001, and so we can conclude that we are certain about this strong positive correlation. Taking all variables into account, we can now create a heat map that indicates the correlation between each of the variables with one another. The color scheme indicates the Pearson correlation coefficient, indicating the strength of the correlation between two variables. We can see a diagonal line with a dark red color, indicating that all the values on this diagonal are highly correlated. This makes sense because when you look closer, the values on the diagonal are the correlation of all variables with themselves, which will be always 1. This correlation heat map gives us a good overview of how the different variables are related to one another, and most importantly, how these variables are related to price. In this video, we will learn how to find out if there is a relationship between two categorical variables. When dealing with the relationships between two categorical variables, we can't use the same correlation method for continuous variables. We will have to employ the use of the chi-square test for the association. The chi-square test is intended to test how likely it is that an observed distribution is due to chance. It measures how well the observed distribution of data fits with the distribution that is expected if the variables are independent. Before we go into an example, let's look through some important points. The chi-square tests a null hypothesis that the variables are independent. The test compares the observed data to the values that the model expects if the data was distributed in different categories by chance. Anytime the observed data doesn't fit within the model of the expected values, the probability that the variables are dependent becomes stronger, thus proving the null hypothesis incorrect. The chi-square does not tell you the type of relationship that exists between both variables, but only that a relationship exists. We will use the cars dataset. Assuming we want to test the relationship between fuel type and aspiration, these are categorical variables. It is either the fuel type of the car, gas or diesel, and the aspiration is that either the car is standard or turbo. To do this, we will find the observed counts of cars in each category. This can be done by creating a crosstab using the pandas library. A crosstab is a table showing the relationship between two or more variables. When the table only shows the relationship between two categorical variables, the crosstab is also known as a contingency table. In our case, the crosstab or contingency table shows us the counts in each category. A standard car with diesel fuel, a standard car with gas fuel, a turbo car with diesel fuel, or a turbo car with gas fuel. The formula for chi-square is given as follows. The summation of the observed value, i.e. the counts in each group minus the expected value, all squared, divided by the expected value. Expected values are based on the given totals. That is, what can we say individual cells would be if we did not know the observed values? To calculate the expected value of a standard car with diesel, we take the row total, which is 20, multiplied by the column total, 168, divided by the grand total of 205. This will give you 16.39. If we do the same thing for turbo cars with gas fuel, we will take the row total, 185, multiplied by the column total, 37, and we divide by the grand total, 205, to get 33.39. If we repeat the same procedure for all of them, we get these values. If we took the row totals, column totals, and grand total, we will get the same values as the totals as the observed values. Now going back to this formula, if we took a summation of all the observed minus the expected values, all squared, and divided by the expected value, we will get a chi-square value of 29.6. On the chi-square table, we check on the degree of freedom equals one row and find the value closest to 29.6. Here we can see that 29.6 will fall in a p-value less than 0.05. Therefore, we can say the p-value is less than 0.05. Since the p-value is less than 0.05, we reject the null hypothesis that the two variables are independent, and therefore we conclude that there is an association between fuel type and aspiration. To do this in Python, we will use the chi-square contingency function in the scipy.statistics package. The function will print out the chi-square test value 29.6. The second value is the p-value, which is very close to 0 and a degree of freedom of 1. If you remember, the chi-square table did not give an exact p-value, but a range in which it falls. Python will give the exact p-value. We can see the same results as in our previous slides. It also prints out the expected values, which we also calculated by hand. Since the p-value is close to 0, we reject the null hypothesis that the two variables are independent and conclude that there is evidence of association between fuel type and aspiration. In this video, we will examine model development by trying to predict the price of a car using our dataset. In this module, you will learn about simple and multiple linear regression, model evaluation using visualization, polynomial regression and pipelines, R-squared and MSE for in-sample evaluation, prediction and decision making, and how you can determine a fair value for a used car. A model or estimator can be thought of as a mathematical equation used to predict a value given one or more other values. Relating one or more independent variables or features to dependent variables. For example, you input a car model's highway miles per gallon as the independent variable or feature. The output of the model or dependent variable is the price. Usually, the more relevant data you have, the more accurate your model is. For example, you input multiple independent variables or features to your model. Therefore, your model may predict a more accurate price for the car. To understand why more data is important, consider the following situation. You have two almost identical cars. Pink cars sell for significantly less. You want to use your model to determine the price of two cars, one pink, one red. If your model's independent variables or features do not include color, your model will predict the same price for cars that may sell for much less. In addition to getting more data, you can try different types of models. In this course, you will learn about simple linear regression, multiple linear regression, and polynomial regression. In this video, we'll be talking about simple linear regression and multiple linear regression. Linear regression will refer to one independent variable to make a prediction. Multiple linear regression will refer to multiple independent variables to make a prediction. Simple linear regression, or SLR, is a method to help us understand the relationship between two variables, the predictor, independent variable x, and the target, dependent variable y. We would like to come up with a linear relationship between the variables shown here. The parameter b0 is the intercept. The parameter b1 is the slope. When we fit or train the model, we will come up with these parameters. This step requires lots of math, so we will not focus on this part. Let's clarify the prediction step. It's hard to figure out how much a car costs, but the highway miles per gallon is in the owner's manual. If we assume there is a linear relationship between these variables, we can use this relationship to formulate a model to determine the price of the car. If the highway miles per gallon is 20, we can input this value into the model to obtain a prediction of $22,000. In order to determine the line, we take data points from our dataset marked in red here. We then use these training points to fit our model. The results of the training points are the parameters. We usually store the data points in two data frame or NumPy arrays. The value we would like to predict is called the target that we store in the array y. We store the independent variable in the data frame or array x. Each sample corresponds to a different row in each data frame or array. In many cases, many factors influence how much people pay for a car. For example, make or how old the car is. In this model, this uncertainty is taken into account by assuming a small random value is added to the point on the line. This is called noise. The figure on the left shows the distribution of the noise. The vertical axis shows the value added, and the horizontal axis illustrates the probability that the value will be added. Usually, a small positive value is added, or a small negative value. Sometimes large values are added. But for the most part, the values added are near zero. We can summarize the process like this. We have a set of training points. We use these training points to fit or train the model and get parameters. We then use these parameters in the model. We now have a model. We use the hat on the y to denote the model is an estimate. We can use this model to predict values that we haven't seen. For example, we have no car with 20 highway miles per gallon. We can use our model to make a prediction for the price of this car. But don't forget, our model is not always correct. We can see this by comparing the predicted value to the actual value. We have a sample for 10 highway miles per gallon, but the predicted value does not match the actual value. If the linear assumption is correct, this error is due to the noise, but there can be other reasons. To fit the model in Python, first we import linear model from scikit-learn, then create a linear regression object using the constructor. We define the predictor variable and target variable, then use the method fit to fit the model and find the parameters b0 and b1. The input are the features and the targets. We can obtain a prediction using the method predict. The output is an array. The array has the same number of samples as the input x. The intercept b0 is an attribute of the object lm. The slope b1 is also an attribute of the object lm. The relationship between price and highway miles per gallon is given by this equation in bold. Price equals 38,423.31 minus 821.73 times highway miles per gallon, like the equation we discussed before. Multiple linear regression is used to explain the relationship between one continuous target y variable and two or more predictor x variables. If we have, for example, 4 predictor variables, then b0, intercept, x equals 0, b1, the coefficient or parameter of x1, b2, the coefficient of parameter x2, and so on. If there are only 2 variables, then we can visualize the values. Consider the following function. The variables x1 and x2 can be visualized on a 2D plane. Let's do an example on the next slide. The table contains different values of the predictor variables x1 and x2. The position of each point is placed on the 2D plane, color-coded accordingly. Each value of the predictor variables x1 and x2 will be mapped to a new value y hat. The new values of y hat, are mapped in the vertical direction with height proportional to the value that y hat takes. We can fit the multiple linear regression as follows. We can extract the 4 predictor variables and store them in the variable z, then train the model as before using the method train, with the features or dependent variables and the targets, colon. We can also obtain a prediction using the method predict. In this case, the input is an array or data frame with 4 columns. The number of rows corresponds to the number of samples. The output is an array with the same number of elements as number of samples. The intercept is an attribute of the object, and the coefficients are also attributes. It is helpful to visualize the equation, replacing the dependent variable names with actual names. This is identical to the form we discussed earlier. In this video, we'll look at model evaluation using visualization. Regression plots are a good estimate of the relationship between 2 variables, the strength of the correlation, and the direction of the relationship, positive or negative. The horizontal axis is the independent variable. The vertical axis is the dependent variable. Each point represents a different target point. The fitted line represents the predicted value. There are several ways to plot a regression plot. A simple way is to use regplot from the Seaborn library. First import Seaborn, then use the regplot function. The parameter x is the name of the column that contains the independent variable or feature. The parameter y contains the name of the column that contains the name of the dependent variable or target. The parameter data is the name of the data frame. The result is given by the plot. The residual plot represents the error between the actual value. Examining the predicted value and actual value, we see a difference. We obtain that value by subtracting the predicted value and the actual target value. We then plot that value on the vertical axis with an independent variable as the horizontal axis. Similarly, for the second sample, we repeat the process, subtracting the target value from the predicted value, then plotting the value accordingly. Looking at the plot gives us some insight into our data. We expect to see the results to have zero mean, distributed evenly around the x-axis with similar variance. There is no curvature. This type of residual plot suggests a linear plot is appropriate. In this residual plot, there is a curvature. The values of the error change with x. For example, in the region, all the residual errors are positive. In this area, the residuals are negative. In the final location, the error is large. The residuals are not randomly separated. This suggests the linear assumption is incorrect. This plot suggests a non-linear function. We will deal with this in the next section. In this plot, we see that variance of the residuals increases with x. Therefore, our model is incorrect. We can use Seaborn to create a residual plot. First, import Seaborn. We use the residPlot function. The first parameter is a series of dependent variable or feature. The second parameter is a series of dependent variable or target. We see in this case the residuals have a curvature. A distribution plot counts the predicted value versus the actual value. These plots are extremely useful for visualizing models with more than one independent variable or feature. Let's look at a simplified example. We examine the vertical axis. We then count and plot the number of predicted points that are approximately equal to 1. We then count and plot the number of predicted points that are approximately equal to 2. We repeat the process for predicted points that are approximately equal to 3. Then we repeat the process for the target values. In this case, all the target values are approximately equal to 2. The values of the targets and predicted values are continuous. A histogram is for discrete values. Therefore, pandas will convert them to a distribution. The vertical axis is scaled to make the area under the distribution equal to 1. This is an example of using a distribution plot. The dependent variable or feature is price. The fitted values that result from the model are in blue. The actual values are in red. We see the predicted values for prices in the range from 40,000 to 50,000 are inaccurate. The prices in the region from 10,000 to 20,000 are much closer to the target value. In this example, we use multiple features or independent variables. Comparing it to the plot on the last slide, we see predicted values are much closer to the target values. Here is the code to create a distribution plot. The actual values are used as a parameter. We want a distribution instead of a histogram, so we want the hist parameter set to false. The color is red. The label is also included. The predicted values are included for the second plot. The rest of the parameters are set accordingly. In this video, we will cover polynomial regression and pipelines. What do we do when a linear model is not the best fit for our data? Let's look into another type of regression model, the polynomial regression. We transform our data into a polynomial, then use linear regression to fit the parameter. Then we will discuss pipelines. Pipelines are a way to simplify your code. Polynomial regression is a special case of the general linear regression. This method is beneficial for describing curvilinear relationships. What is a curvilinear relationship? It's what you get by squaring or setting higher order terms of the predictor variables in the model, transforming the data. The model can be quadratic, which means that the predictor variable in the model is squared. We use a bracket to indicate it as an exponent. This is a second-order polynomial regression with a figure representing the function. The model can be cubic, which means that the predictor variable is cubed. This is a third-order polynomial regression. We see by examining the figure that the function has more variation. There also exists higher-order polynomial regressions, when a good fit hasn't been achieved by second or third order. We can see in figures how much the graphs change when we change the order of the polynomial regression. The degree of the regression makes a big difference and can result in a better fit if you pick the right value. In all cases, the relationship between the variable and the parameter is always linear. Let's look at an example from our data where we generate a polynomial regression model. In Python, we do this by using the polyfit function. In this example, we develop a third-order polynomial regression model base. We can print out the model. The symbolic form for the model is given by the following expression: -1.557 x1 cubed plus 204.8 x1 squared plus 8,965 x1 plus 1.37 times 10 to the power of 5. We can also have multidimensional polynomial linear regression. The expression can get complicated. Here are just some of the terms for a two-dimensional second-order polynomial. NumPy's polyfit function cannot perform this type of regression. We use the pre-processing library in scikit-learn. To create a polynomial feature object, the constructor takes the degree of the polynomial as a parameter. Then we transform the features into a polynomial feature with the fit_transform method. Let's do a more intuitive example. Consider the features shown here. Applying the method, we transform the data. We now have a new set of features that are a transformed version of our original features. As the dimension of the data gets larger, we may want to normalize multiple features in scikit-learn. Instead, we can use the pre-processing module to simplify many tasks. For example, we can standardize each feature simultaneously. We import standard scalar. We train the object. Fit the scale object. Then transform the data into a new data frame on array x_scale. There are more normalization methods available in the pre-processing library as well as other transformations. We can simplify our code by using a pipeline library. There are many steps to getting a prediction. For example, normalization, polynomial transform, and linear regression. We simplify the process using a pipeline. Pipelines sequentially perform a series of transformations. The last step carries out a prediction. First, we import all the modules we need. Then we import the library pipeline. We create a list of tuples. The first element in the tuple contains the name of the estimator, model. The second element contains model constructor. We input the list in the pipeline constructor. We now have a pipeline object. We can train the pipeline by applying the train method to the pipeline object. We can also produce a prediction as well. The method normalizes the data, performs a polynomial transform, then outputs a prediction. Now that we've seen how we can evaluate a model by using visualization, we want to numerically evaluate our models. Let's look at some of the measures that we use for in-sample evaluation. These measures are a way to numerically determine how good the model fits on our data. Two important measures that we often use to determine the fit of a model are mean square error, MSE, and R-squared. To measure the MSE, we find the difference between the actual value y and the predicted value y hat, then square it. In this case, the actual value is 150. The predicted value is 50. Subtracting these points, we get 100. We then square the number. We then take the mean or average of all the errors by adding them all together and dividing by the number of samples. To find the MSE in Python, we can import the mean_squared_error from scikit-learn metrics. The mean_squared_error function gets two inputs: the actual value of target variable and the predicted value of target variable. R-squared is also called the coefficient of determination. It's a measure to determine how close the data is to the fitted regression line. So how close is our actual data to our estimated model? Think about it as comparing a regression model to a simple model, i.e., the mean of the data points. If the variable x is a good predictor, our model should perform much better than just the mean. In this example, the average of the data points y bar is 6. Coefficient of determination, R-squared, is 1 minus the ratio of the MSE of the regression line divided by the MSE of the average of the data points. For the most part, it takes values between 0 and 1. Let's look at a case where the line provides a relatively good fit. The blue line represents the regression line. The blue squares represent the MSE of the regression line. The red line represents the average value of the data points. The red squares represent the MSE of the red line. We see the area of the blue squares is much smaller than the area of the red squares. In this case, because the line is a good fit, the mean squared error is small, therefore the numerator is small. The mean squared error of the line is relatively large, as such the numerator is large. A small number divided by a larger number is an even smaller number. Taken to an extreme, this value tends to 0. If we plug in this value from the previous slide for r squared, we get a value near 1. This means the line is a good fit for the data. Here is an example of a line that does not fit the data well. If we just examine the area of the red squares compared to the blue squares, we see the area is almost identical. The ratio of the areas is close to 1. In this case, the r squared is near 0. This line performs about the same as just using the average of the data points. Therefore, this line did not perform well. We find the r squared value in Python by using the score method in the linear regression object. From the value that we get from this example, we can say that approximately 49.695% of the variation of price is explained by the simple linear model. Your r squared value is usually between 0 and 1. If your r squared is negative, it could be due to overfitting that we will discuss in the next module. In this video, our final topic will be on prediction and decision making. How can we determine if our model is correct? The first thing you should do is make sure your model results make sense. You should always use visualization, numerical measures for evaluation, and comparing between different models. Let's look at an example of prediction. If you recall, we trained the model using the fit method. Now we want to find out what the price would be for a car that has a highway miles per gallon of 30. Plugging this value into the predict method gives us a resulting price of $13,771.30. This seems to make sense. For example, the value is not negative, extremely high, or extremely low. We can look at the coefficients by examining the coef underscore attribute. If you recall, the expression for the simple linear model that predicts price from highway miles per gallon. This value corresponds to the multiple of the highway miles per gallon feature. As such, an increase of 1 unit in highway miles per gallon, the value of the car decreases approximately $821. This value also seems reasonable. Sometimes your model will produce values that don't make sense. For example, if we plot the model out for highway miles per gallon in the ranges of 0 to 100, we get negative values for the price. This could be because the values in that range are not realistic. The linear assumption is incorrect, or we don't have data for cars in that range. In this case, it is unlikely that a car will have fuel mileage in that range, so our model seems valid. To generate a sequence of values in a specified range, import NumPy, then use the NumPy arrange function to generate the sequence. The sequence starts at 1 and increments by 1 till we reach 100. The first parameter is the starting point of the sequence. The second parameter is the endpoint plus 1 of the sequence. The final parameter is the step size between elements in the sequence. In this case, it's 1, so we increment the sequence one step at a time, from 1 to 2, and so on. We can use the output to predict new values. The output is a NumPy array. Many of the values are negative. Using a regression plot to visualize your data is the first method you should try. See the labs for examples of how to plot polynomial regression. For this example, the effect of the independent variable is evident in this case. The data trends down as the dependent variable increases. The plot also shows some nonlinear behavior. Examining the residual plot, we see in this case the residuals have a curvature suggesting nonlinear behavior. A distribution plot is a good method for multiple linear regression. For example, we see the predicted values for prices in the range from 30,000 to 50,000 are inaccurate. This suggests a nonlinear model may be more suitable, or we need more data in this range. The mean square error is perhaps the most intuitive numerical measure for determining if a model is good or not. Let's see how different measures of mean square error impact the model. The figure shows an example of a mean square error of 3,495. This example has a mean square error of 3,652. The final plot has a mean square error of 12,870. As the square error increases, the targets get further from the predicted points. As we discussed, R-squared is another popular method to evaluate your model. It tells you how well your line fits into the model. R-squared values range from 0 to 1. R-squared tells us what percent of the variability in the dependent variable is accounted for by the regression on the independent variable. An R-squared of 1 means that all movements of another dependent variable are completely explained by movements in the independent variables. In this plot, we see the target points in red and the predicted line in blue. An R-squared of 0.9986, the model appears to be a good fit. That means that more than 99% of the variability of the predicted variable is explained by the independent variables. This model has an R-squared of 0.9226. There still is a strong linear relationship. Model is still a good fit. An R-squared of 0.806 looks the data. We can visually see that the values are scattered around the line. They are still close to the line, and we can say that 80% of the variability of the predicted variable is explained by the independent variables. And an R-squared 0.61 means that approximately 61% of the observed variation can be explained by the independent variables. An acceptable value for R-squared depends on what field you are studying and what your use case is. Falk and Miller, 1992, suggests that an acceptable R-squared value should be at least 0.1. Does a lower mean square error imply better fit? Not necessarily. MSE for an MLR model will be smaller than the MSE for an SLR model, since the errors of the data will decrease when more variables are included in the model. Polynomial regression will also have a smaller MSE than regular regression. In the next section, we will look at more accurate ways to evaluate the model. Model evaluation tells us how our model performs in the real world. In the previous module, we talked about in-sample evaluation. In-sample evaluation tells us how well our model fits the data already given to train it. It does not give us an estimate of how well the trained model can predict new data. The solution is to split our data up, use the in-sample data, or training data, to train the model. The rest of the data, called test data, is used as out-of-sample data. This data is then used to approximate how the model performs in the real world. Separating data into training and testing sets is an important part of model evaluation. We use the test data to get an idea how our model will perform in the real world. When we split a data set, usually the larger portion of data is used for training and a smaller part is used for testing. For example, we can use 70% of the data for training. We then use 30% for testing. We use training set to build a model and discover predictive relationships. We then use a testing set to evaluate model performance. When we have completed testing our model, we should use all the data to train the model. A popular function in the scikit-learn package for splitting datasets is the train-test-split function. This function randomly splits a dataset into training and testing subsets. From the example code snippet, this method is imported from sklearn.cross validation. The input parameters y_data is the target variable. In the car appraisal example, it would be the price. And x_data, the list of predictor variables. In this case, it would be all the other variables in the car data set that we are using to try to predict the price. The output is an array, x_train and y_train. The subsets for training, x_test and y_test, the subsets for testing. In this case, the test size is a percentage of the data for the testing set. Here it is 30%. The random state is a random seed for random data set splitting. Generalization error is a measure of how well our data does at predicting previously unseen data. The error we obtain using our testing data is an approximation of this error. This figure shows the distribution of the actual values in red compared to the predicted values from a linear regression in blue. We see the distributions are somewhat similar. If we generate the same plot using the test data, we see the distributions are relatively different. The difference is due to a generalization error and represents what we see in the real world. Using a lot of data for training gives us an accurate means of determining how well our model will perform in the real world. But the precision of the performance will be low. Let's clarify this with an example. The center of this bullseye represents the correct generalization error. Let's say we take a random sample of the data using 90% of the data for training and 10% for testing. The first time we experiment, we get a good estimate of the training data. If we experiment again, training the model with a different combination of samples, we also get a good result, but the results will be different relative to the first time we run the experiment. Repeating the experiment again with a different combination of training and testing samples, the results are relatively close to the generalization error, but distinct from each other. Repeating the process, we get good approximation of the generalization error, but the precision is poor, i.e., all the results are extremely different from one another. If we use fewer data points to train the model and more to test the model, the accuracy of the generalization performance will be less, but the model will have good precision. The figure above demonstrates this. All our error estimates are relatively close together, but they are further away from the true generalization performance. To overcome this problem, we use cross-validation. One of the most common out-of-sample evaluation metrics is cross-validation. In this method, the data set is split into k equal groups. Each group is referred to as a fold. For example, 4 folds. Some of the folds can be used as a training set, which we use to train the model, and the remaining parts are used as a test set, which we use to test the model. For example, we can use 3 folds for training, then use 1 fold for testing. This is repeated until each partition is used for both training and testing. At the end, we use the average results as the estimate of out-of-sample error. The evaluation metric depends on the model. For example, the R-squared. The simplest way to apply cross-validation is to call the cross_val_score function, which performs multiple out-of-sample evaluations. This method is imported from sklearn's model selection package. We then use the function cross_val_score. The first input parameter is the type of model we are using to do the cross-validation. In this example, we initialized a linear regression model, or object LR, which we passed the cross_val_score function. The other parameters are x_data, the predictor variable data, and y_data, the target variable data. We can manage the number of partitions with the CV parameter. Here, CV equals 3, which means the dataset is split into 3 equal partitions. The function returns an array of scores, one for each partition that was chosen as the testing set. We can average the result together to estimate out-of-sample R-squared using the mean function in NumPy. Let's see an animation. Let's see the result of the score array in the last slide. First, we split the data into 3 folds. We use 2 folds for training, the remaining fold for testing. The model will produce an output. We will use the output to calculate a score. In the case of the R-squared, i.e. coefficient of determination, we will store that value in an array. We will repeat the process using 2 folds for training and 1 fold for testing. Save the score, then use a different combination for training and the remaining fold for testing. We store the final result. The cross-val_score function returns a score value to tell us the cross-validation result. What if we want a little more information? What if we want to know the actual predicted values supplied by our model before the R-squared values are calculated? To do this, we use the cross_val_predict function. The input parameters are exactly the same as the cross-val_score function, but the output is a prediction. Let's illustrate the process. First, we split the data into 3 folds. We use 2 folds for training, the remaining fold for testing. The model will produce an output, and we will store it in an array. We will repeat the process using 2 folds for training, 1 for testing. The model produces an output again. Finally, we use the last 2 folds for training. Then we use the testing data. This final testing fold produces an output. These predictions are stored in an array. If you recall, in the last module, we discussed polynomial regression. In this section, we will discuss how to pick the best polynomial order and problems that arise when selecting the wrong order polynomial. Consider the following function. We assume the training points come from a polynomial function plus some noise. The goal of model selection is to determine the order of the polynomial to provide the best estimate of the function yx. If we try and fit the function with a linear function, the line is not complex enough to fit the data. As a result, there are many errors. This is called underfitting, where the model is too simple to fit the data. If we increase the order of the polynomial, the model fits better. But the model is still not flexible enough and exhibits underfitting. This is an example of the 8th order polynomial used to fit the data. We see the model does well at fitting the data and estimating the function, even at the inflection points. Increasing it to a 16th order polynomial, the model does extremely well at tracking the training point, but performs poorly at estimating the function. This is especially apparent where there is little training data. The estimated function oscillates, not tracking the function. This is called overfitting, where the model is too flexible and fits the noise rather than the function. Let's look at a plot of the mean square error for the training and testing set of different order polynomials. The horizontal axis represents the order of the polynomial. The vertical axis is the mean square error. The training error decreases with the order of the polynomial. The test error is a better means of estimating the error of a polynomial. The error decreases till the best order of the polynomial is determined. Then the error begins to increase. We select the order that minimizes the test error. In this case, it was 8. Anything on the left would be considered underfitting. Anything on the right is overfitting. If we select the best order of the polynomial, we will still have some errors. If you recall the original expression for the training points, we see a noise term. This term is one reason for the error. This is because the noise is random and we can't predict it. This is sometimes referred to as an irreducible error. There are other sources of errors as well. For example, our polynomial assumption may be wrong. Our sample points may have come from a different function. For example, in this plot, the data is generated from a sine wave. The polynomial function does not do a good job at fitting the sine wave. For real data, the model may be too difficult to fit, or we may not have the correct type of data to estimate the function. Let's try different order polynomials on the real data using horsepower. The red points represent the training data. The green points represent the test data. If we just use the mean of the data, our model does not perform well. A linear function does fit the data better. A second order model looks similar to the linear function. A third order function also appears to increase, like the previous 2 orders. Here we see a 4th order polynomial. At around 200 horsepower, the predicted price suddenly decreases. This seems erroneous. Let's use r² to see if our assumption is correct. The following is a plot of the r² value. The horizontal axis represents the order polynomial models. The closer the r² is to 1, the more accurate the model is. Here we see the r² is optimal when the order of the polynomial is 3. The r² drastically decreases when the order is increased to 4, validating our initial assumption. We can calculate different r² values as follows. First, we create an empty list to store the values. We create a list containing different polynomial orders. We then iterate through the list using a loop. We create a polynomial feature object with the order of the polynomial as a parameter. We transform the training and test data into a polynomial using the fit transform method. We fit the regression model using the transformed data. We then calculate the r² using the test data and store it in the array. In this video, we'll discuss ridge regression. Ridge regression prevents overfitting. In this video, we will focus on polynomial regression for visualization, but overfitting is also a big problem when you have multiple independent variables or features. Consider the following fourth-order polynomial in orange. The blue points are generated from this function. We can use a 10th-order polynomial to fit the data. The estimated function in blue does a good job at approximating the true function. In many cases, real data has outliers. For example, this point shown here does not appear to come from the function in orange. If we use a 10th-order polynomial function to fit the data, the estimated function in blue is incorrect and is not a good estimate of the actual function in orange. If we examine the expression for the estimated function, we see the estimated polynomial coefficients have a very large magnitude. This is especially evident for the higher-order polynomials. Ridge regression controls the magnitude of these polynomial coefficients by introducing the parameter alpha. Alpha is a parameter we select before fitting or training the model. Each row in the following table represents an increasing value of alpha. Let's see how different values of alpha change the model. This table represents the polynomial coefficients for different values of alpha. The column corresponds to the different polynomial coefficients, and the rows correspond to the different values of alpha. As alpha increases, the parameters get smaller. This is most evident for the higher-order polynomial features, but alpha must be selected carefully. If alpha is too large, the coefficients will approach 0 and underfit the data. If alpha is 0, the overfitting is evident. For alpha equal to 0.001, the overfitting begins to subside. For alpha equal to 0.01, the estimated function tracks the actual function. When alpha equals 1, we see the first signs of underfitting. The estimated function does not have enough flexibility. At alpha equals to 10, we see extreme underfitting. It does not even track the 2 points. In order to select alpha, we use cross-validation. To make a prediction using ridge regression, import ridge from sklearn linear models. Create a ridge object using the constructor. The parameter alpha is one of the arguments of the constructor. We train the model using the fit method. To make a prediction, we use the predict method. In order to determine the parameter alpha, we use some data for training. We use a second set called validation data. This is similar to test data, but it is used to select parameters like alpha. We start with a small value of alpha. We train the model, make a prediction using the validation data, then calculate the R-squared and store the values. Repeat the value for a larger value of alpha. We train the model again, make a prediction using the validation data, then calculate the R-squared and store the values of R-squared. We repeat the process for a different alpha value, training the model and making a prediction. We select the value of alpha that maximizes the R-squared. Note that we can use other metrics to select the value of alpha, like mean squared error. The overfitting problem is even worse if we have lots of features. The following plot shows the different values of R-squared on the vertical axis. The horizontal axis represents different values for alpha. We use several features from our used car dataset and a second-order polynomial function. The training data is in red and validation data is in blue. We see as the value for alpha increases, the value of R-squared increases and converges at approximately 0.75. In this case, we select the maximum value of alpha because running the experiment for higher values of alpha have little impact. Conversely, as alpha increases, the R-squared on the test data decreases. This is because the term alpha prevents overfitting. This may improve the results in the unseen data, but the model has worse performance on the test data. See the lab on how to generate this plot. Grid search allows us to scan through multiple free parameters with few lines of code. Parameters like the alpha term discussed in the previous video are not part of the fitting or training process. These values are called hyperparameters. scikit-learn has a means of automatically iterating over these hyperparameters using cross-validation. This method is called grid search. Grid search takes the model or objects you would like to train and different values of the hyperparameters. It then calculates the mean square error, or R squared, for various hyperparameter values, allowing you to choose the best values. Let the small circles represent different hyperparameters. We start off with one value for hyperparameters and train the model. We use different hyperparameters to train the model. We continue the process until we have exhausted the different free parameter values. Each model produces an error. We select the hyperparameter that minimizes the error. To select the hyperparameter, we split our data set into three parts: the training set, validation set, and test set. We train the model for different hyperparameters. We use the R squared, or mean square error, for each model. We select the hyperparameter that minimizes the mean squared error or maximizes the R squared on the validation set. We finally test our model performance using the test data. This is the scikit-learn webpage, where the object constructor parameters are given. It should be noted that the attributes of an object are also called parameters. We will not make the distinction, even though some of the options are not hyperparameters per se. In this module, we will focus on the hyperparameter alpha and the normalization parameter. The value of your grid search is a Python list that contains a Python dictionary. The key is the name of the free parameter. The value of the dictionary is the different values of the free parameter. This can be viewed as a table with various free parameter values. We also have the object or model. The grid search takes on the scoring method, in this case R squared, the number of folds, the model or object, and the free parameter values. Some of the outputs include the different scores for different free parameter values. In this case, the R squared along with the free parameter values that have the best score. First, we import the libraries we need, including grid search CV, the dictionary of parameter values. We create a ridge regression object or model. We then create a grid search CV object. The inputs are the ridge regression object, the parameter values, and the number of folds. We will use R squared. This is the default scoring method. We fit the object. We can find the best values for the free parameters using the attribute best estimator. We can also get information like the mean score on the validation data using the attribute CV result. One of the advantages of grid search is how quickly we can test multiple parameters. For example, ridge regression has the option to normalize the data. To see how to standardize, see Module 4. The term alpha is the first element in the dictionary. The second element is the normalize option. The key is the name of the parameter. The value is the different options, in this case because we can either normalize the data or not. The values are true or false, respectively. The dictionary is a table or grid that contains two different values. As before, we need the ridge regression object or model. The procedure is similar, except that we have a table or grid of different parameter values. The output is the score for all the different combinations of parameter values. The code is also similar. The dictionary contains the different free parameter values. We can find the best value for the free parameters. The resulting scores of the different free parameters are stored in this dictionary, grid1.cv_results_. We can print out the score for the different free parameter values. The parameter values are stored as shown here. See the course labs for more examples.
Hello everyone, and welcome to Data Visualization with Python. I'm Alex Ackelson, a data scientist at IBM, and I'm your instructor for this course. Throughout this course, we're going to learn how to create meaningful, effective, and aesthetically pleasing data visuals and plots in Python using matplotlib and a couple of other libraries, namely Seaborn and Folium.
This course will consist of 3 modules. In Module 1, we will briefly discuss data visualization and some of the best practices to keep in mind when creating data visuals. We will then learn about matplotlib, its history, architecture, and the 3 layers that form its architecture. We will also learn about the data set that we will use throughout the course in these lectures, as well as the hands-on sessions. We will essentially be working with a data set that was curated by the United Nations on immigration from different countries to Canada from 1980 to 2013. Then, we will start learning how to use matplotlib to create plots and visuals, and we will start off with line plots. Now we will generate the majority of our plots and visualizations in this course using data stored in pandas data frames. For those of you who don't know what pandas is a Python library for data manipulation and analysis. So before we start building visualizations and plots, we will take a brief crash course on pandas and learn how to use it to read data from CSV files, like the one shown here, into what's called a pandas data frame, like the one shown here. Now, if you're interested in learning more about the pandas library, we actually cover it in much more detail in our next course in this specialization, which is data analysis with Python. So make sure to complete the next course in this specialization. In Module 2, we will continue on with a few more basic data visualizations, such as area plots, histograms, and bar charts, and learn how to use matplotlib to create them and even create different versions of these plots. We will also cover a set of specialized visualizations such as pie charts, box plots, scatter plots, and bubble plots, and we will learn how to create them still using matplotlib. In Module 3, we will learn about more advanced visuals such as waffle charts that provide a fine-grained view of the proportions of different categories in a data set. We will also learn about word clouds that depict word frequency or importance in a body of text. Also, in this module, we will explore another library, Seaborn, which is built on top of matplotlib to simplify the process of creating plots and visuals, and we will get a taste of its effectiveness through the creation of regression plots. Finally, in this module, we will explore another library, Folium, which was built primarily to visualize geospatial data. So we will learn how to create maps of different regions of the world, superimpose markers of different shapes on top of maps, and learn how to create choropleth maps. Now, before I conclude this video, let me stress one thing. Data visualization is best learned through hands-on exercises and sessions. Therefore, don't worry if you find some of the videos to be short. The labs and the hands-on sessions are very thorough and cover a lot of the concepts that are discussed in the videos in much more detail. So it's very important that you complete the labs and the hands-on sessions, although they are ungraded components of the course. I hope that you remember this and you keep it in mind as you progress in this course. After completing this course, you will be able to use different visualization libraries in Python, namely matplotlib, Seaborn, and Folium, to create expressive visual representations of your data for different purposes. So let's get right into it.
Hello everyone, and welcome to the first module of the Data Visualization with Python course. In this video, we're going to introduce data visualization and go over an example of transforming a given visual into one which is more effective, attractive, and impactful. So let's get started. Now, one might ask, why would I need to learn how to visualize data? Well, data visualization is a way to show complex data in a form that is graphical and easy to understand. This can be especially useful when one is trying to explore the data and getting acquainted with it. Also, since a picture is worth 1,000 words, then plots and graphs can be very effective in conveying a clear description of the data, especially when disclosing findings to an audience or sharing the data with other peer data scientists. Also, they can be very valuable when it comes to supporting any recommendations you make to clients, managers, or other decision makers in your field. Dark Horse Analytics is a company that spun out of a research lab at the University of Alberta in 2008 and has done fascinating work on data visualization. Dark Horse Analytics specializes in quantitative consulting, in several areas including data visualization and geospatial analysis. Their approach when creating a visual revolves around 3 key points. Less is more effective, it is more attractive, and it is more impactive. In other words, any feature or design you incorporate in your plot to make it more attractive or pleasing should support the message that the plot is meant to get across and not distract from it. Let's take a look at an example. So here's a pie chart of what looks like people's preferences when it comes to different types of pig meat. The chart's message is almost half of the people surveyed preferred bacon over the other types of pig meat. But I'm sure that almost all of you agree that there's a lot going on in this pie chart, and we're not even sure if features such as the blue background or the 3D orientation are meant to convey anything. In fact, these additional unnecessary features distract from the main message and can be confusing to the audience. So let's apply Dark Horse Analytics' approach to transform this into a visual that's more effective, attractive, and impactive. As I mentioned earlier, the message here is that people are most likely to choose bacon over other types of pig meat. So let's get rid of everything that can be distracting from this core message. The first thing is let's get rid of the blue background and the gray background. Let's also get rid of borders as they do not convey any extra information. Also, let's drop the redundant legend since the pie chart is already color-coded. 3D isn't adding any extra information, so let's say bye to it. Text bolding is also unnecessary. And let's get rid of the different colors. And the wedges. Whoa, what just happened? Well, let's thicken the lines to make them more meaningful. Now, this looks a little familiar. Yes, this is a bar graph after all, one with horizontal bars. And finally, let's emphasize bacon so that it stands out among the other types of pig meat. Now, let's juxtapose the pie chart and the bar graph and compare which is better and easy to understand. I hope that we unanimously agree that the bar graph is the better of the two. It is simple, cleaner, less distracting, and much easier to read. In fact, pie charts have recently come under fire from data visualization experts who argue that they are relevant only in the rarest of circumstances. Bar graphs and charts, on the other hand, are argued to be far superior ways to quickly get a message across. But don't worry about this for now. We will come back to this point when we learn how to create pie charts and bar graphs with Matplotlib. For more similar and interesting examples, check out Dark Horse Analytics' website. They have a couple more examples on how to clean bar graphs and maps of geospatial data. All these examples reinforce the concept of less is more effective, attractive, and impactive. In this video, we will start learning about Matplotlib. This video will focus on the history of Matplotlib and its architecture. Matplotlib is one of the most widely used, if not the most popular, data visualization library in Python. It was created by John Hunter, who was a neurobiologist and was part of a research team that was working on analyzing electrocorticography signals, ECOG for short. The team was using a proprietary software for the analysis. However, they had only one license and were taking turns in using it. So in order to overcome this limitation, John set out to replace the proprietary software with a MATLAB-based version that could be utilized by him and his teammates and that could be extended by multiple investigators. As a result, Matplotlib was originally developed as an ECOG visualization tool, and just like MATLAB, Matplotlib was equipped with a scripting interface for quick and easy generation of graphics represented by pyplot. We will learn more about this in a moment. Now, Matplotlib's architecture is composed of 3 main layers. The backend layer, the artist layer, where much of the heavy lifting happens, and is usually the appropriate programming paradigm when writing a web application server or a UI application, or perhaps a script to be shared with other developers. And the scripting layer, which is the appropriate layer for everyday purposes, and is considered a lighter scripting interface to simplify common tasks and for quick and easy generation of graphics and plots. Now let's go into each layer in a little more details. So the backend layer has three built-in abstract interface classes. Figure canvas, which defines and encompasses the area on which the figure is drawn. Renderer, an instance of the renderer class, knows how to draw on the figure canvas. And finally, event, which handles user inputs such as keyboard strokes and mouse clicks. Moving on to the artist layer, it is composed of one main object, which is the artist. The artist is the object that knows how to take the renderer and use it to put ink on the canvas. Everything you see in a Matplotlib figure is an artist instance. The title, the lines, the tick labels, the images, and so on all correspond to an individual artist. There are two types of artist objects. The first type is the primitive type, such as a line, a rectangle, a circle, or text. And the second type is the composite type, such as the figure or the axes. The top-level Matplotlib object that contains and manages all of the elements in a given graphic is the figure artist. And the most important composite artist is the axes, because it is where most of the Matplotlib API plotting methods are defined, including methods to create and manipulate the ticks, the axis lines, the grid, or the plot background. Now, it is important to note that each composite artist may contain other composite artists as well as primitive artists. So a figure artist, for example, would contain an axis artist as well as a rectangle or text artists. Now, let's put the artist layer to use and see how we can use it to generate a graphic. So let's try to generate a histogram of 10,000 random numbers using the artist layer. First, we import the figure canvas from the backend _ag and attach the figure artist to it. Note that ag stands for anti-grain geometry, which is a high-performance library that produces attractive images. Then we import the NumPy library to generate the random numbers. Next, we create an axes artist. The axes artist is added automatically to the figure axes container, fig.axes. And note here that 111 is from the MATLAB convention. So it creates a grid with one row and one column and uses the first cell in that grid for the location of the new axes. Then we call the axes method hist to generate the histogram. Hist creates a sequence of rectangle artists for each histogram bar and adds them to the axes container. Here, 100 means create 100 bins. Finally, we decorate the figure with a title and we save it. Now, this is the generated histogram. And so this is how we use the artist layer to generate a graphic. As for the scripting layer, it was developed for scientists who are not professional programmers. And I'm sure you agree with me based on the histogram that we just created that the artist layer is syntactically heavy, as it is meant for developers and not for individuals whose goal is to perform quick exploratory analysis of some data. Matplotlib's scripting layer is essentially the matplotlib.pyplot interface, which automates the process of defining a canvas and defining a figure artist instance and connecting them. So let's see how the same code that we used earlier using the artist layer to generate a histogram of 10,000 random numbers would now look like. So first, we import the pyplot interface, and you can see how all the methods associated with creating the histogram and other artist objects and manipulating them, whether it is the hist method or showing the figure, are part of the pyplot interface. If you're interested in learning more about the history of Matplotlib and its architecture, this link will take you to a chapter written by the creators of Matplotlib themselves. It is definitely a recommended read. In this video, we will learn how to use Matplotlib to create plots, and we will do so using the Jupyter Notebook as our environment. Now, Matplotlib is a well-established data visualization library that is well supported in different environments, such as in Python scripts, in the IPython shell, web application servers, in graphical user interface toolkits, as well as the Jupyter Notebook. Now, for those of you who don't know what the Jupyter Notebook is, it's an open source web application that allows you to create and share documents that contain live code, visualizations, and some explanatory text as well. Jupyter has some specialized support for matplotlib, and so if you start a Jupyter Notebook, all you have to do is import matplotlib and you're ready to go. In this course, we will be working mostly with the scripting interface. In other words, we will learn how to create almost all of the visualization tools using the scripting interface. As we proceed in the course, you will appreciate the power of this interface when you find out that you can literally create almost all of the conventional visualization tools such as histograms, bar charts, box plots, and many others using one function only, the plot function. Let's start with an example. Let's first import the scripting interface as PLT, and let's plot a circular mark at the position 5, 5. So x equals 5 and y equals 5. Notice how the plot was generated within the browser and not in a separate window, for example. If the plot gets generated in a new window, then you can enforce generating plots within the browser using what's called a magic function. A magic function starts with $sign matplotlib, and to enforce plots to be rendered within the browser, you pass in inline as the backend. Matplotlib has a number of different backends available. One limitation of this backend is that you cannot modify a figure once it's rendered. So after rendering the above figure, there is no way for us to add, for example, a figure title or labels to its axes. We will need to generate a new plot and add a title and the axis labels before calling the show function. A backend that overcomes this limitation is the Notebook backend. With the Notebook backend in place, if a PLT function is called, it checks if an active figure exists, and any functions you call will be applied to this active figure. If a figure does not exist, it renders a new figure. So when we call the plt.plot function to plot a circular mark at position 5, 5, the backend checks if an active figure exists. Since there isn't an active figure, it generates a figure and adds a circular mark to position 5, 5. And what is beautiful about this backend is that now we can easily add a title, for example, or labels to the axes after the plot was rendered, without the need to regenerate the figure. Finally, another thing that is great about matplotlib is that pandas also has a built-in implementation of it. Therefore, plotting in pandas is as simple as calling the plot function on a given pandas series or data frame. So say we have a data frame of the number of immigrants from India and China to Canada from 1980 to 1996. And say we're interested in generating a line plot of these data. All we have to do is call the plot function on this data frame, which we called India_China_df, and set the parameter kind to line, and there you have it, a line plot of the data in the data frame. Plotting a histogram of the data is not any different. So say we would like to plot a histogram of the India column in our data frame. All we have to do is call the plot function on that column and set the parameter kind to hist for histogram. And there you have it, a histogram of the number of Indian immigrants to Canada from 1980 to 1996. This concludes our video on basic plotting with matplotlib. See you in the next video.
In this video, we will learn more about the data set that we will be using throughout the course. The Population Division of the United Nations compiled immigration data pertaining to 45 countries. The data consists of the total number of immigrants from all over the world to each of the 45 countries, as well as other metadata pertaining to the immigrants' countries of origin. In this course, we will focus on immigration to Canada, and we will work primarily with the data set involving immigration to the Great White North. Here is a snapshot of the UN data on immigration to Canada in the form of an Excel file. As you can see, the first 20 rows contain textual data about the UN department and other irrelevant information. Row 21 contains the labels of the columns. Following that, each row represents a country and contains metadata about the country, such as what continent it resides in, what region it belongs to, and whether the region is developing or developed. Each row also contains the total number of immigrants from that country for the years 1980 all the way to 2013. Throughout this course, we will be using pandas for any analysis of the data before creating any visualizations. So in order to start creating different types of plots of the data, whether for exploratory analysis or for presentation, we will need to import the data into a pandas data frame. To do that, we will need to import the pandas library as well as the XLRD library, which is required to extract data from Excel spreadsheets files. Then we call the pandas function read_Excel to read the data into a pandas data frame. And let's name this data frame df_can. Notice how we're skipping the first 20 rows to read only the data corresponding to each country. If you want to confirm that you have imported your data correctly, in pandas, you can always use the head function to display the first 5 rows of the data frame. So if we call this function on our data frame df_can, here's the output. As you can see, the output of the head function looks correct, with the columns having the correct labels, and each row representing a country and containing the total number of immigrants from that country. This concludes our video on the Immigration to Canada dataset. I will see you in the next video. In this video, things will start getting more exciting. We will generate our first visualization tool, the line plot. So what is a line plot? As its name suggests, it is a plot in the form of a series of data points connected by straight line segments. It is one of the most basic type of chart and is common in many fields, not just data science. The more important question is when to use line plots. The best use case for a line plot is when you have a continuous data set and you're interested in visualizing the data over a period of time. As an example, say we're interested in the trend of immigrants from Haiti to Canada. We can generate a line plot, and the resulting figure will depict the trend of Haitian immigrants to Canada from 1980 to 2013. Based on this line plot, we can then research for justifications of obvious anomalies or changes. So in this example, we see that there is a spike of immigration from Haiti to Canada in 2010. A quick Google search for major events in Haiti in 2010 would return the tragic earthquake that took place in 2010, and therefore this influx of immigration to Canada was mainly due to that tragic earthquake. Okay, now how can we generate this line plot? Before we go over the code to do that, let's do a quick recap of our dataset. Each row represents a country and contains metadata about the country, such as where it is located geographically and whether it is developing or developed. Each row also contains numerical figures of annual immigration from that country to Canada from 1980 to 2013. Now let's process the data frame so that the country name becomes the index of each row. This should make querying specific countries easier. Also, let's add an extra column, which represents the cumulative sum of annual immigration from each country from 1980 to 2013. So for Afghanistan, it is 58,639 total, and for Albania, it is 15,699, and so on. And let's name our data frame df_Canada. So now that we know how our data is stored in the data frame df_Canada, let's generate the line plot corresponding to immigration from Haiti. First, we import matplotlib as MPL and its scripting interface as PLT. Then we call the plot function on the row corresponding to Haiti, and we set kind equals line to generate a line plot.
Note that we used years, which is a list containing string format of years from 1980 to 2013, in order to exclude the column of total immigration that we added. Then to complete the figure, we give it a title, and we label its axes. Finally, we call the show function to display the figure. Note that this is the code to generate the line plot using the magic function %sign matplotlib with the inline backend. And there you have it, a line plot that depicts immigration from Haiti to Canada from 1980 to 2013. In the lab session, we explore line plots in more details, so make sure to complete this module's lab session. This concludes our video on line plots. I'll see you in the next video. In this video, we will learn about another visualization tool, the area plot, which is actually an extension of the line plot that we learned about in an earlier video. So what is an area plot? An area plot, also known as an area chart or graph, is a type of plot that depicts accumulated totals using numbers or percentages over time. It is based on the line plot and is commonly used when trying to compare two or more quantities. So how can we generate an area plot with matplotlib? Before we go over the code to do that, let's do a quick recap of our data set. Recall that each row represents a country and contains metadata about the country, such as where it is located geographically and whether it is developing or developed. Each row also contains numerical figures of annual immigration from that country to Canada from 1980 to 2013. Now let's process the data frame so that the country name becomes the index of each row. This should make retrieving rows pertaining to specific countries a lot easier. Also, let's add an extra column which represents the cumulative sum of annual immigration from each country from 1980 to 2013. So for Afghanistan, it is 58,639 total, and for Albania, it is 15,699, and so on. And let's name our data frame df_Canada. So now that we know how our data is stored in the data frame df_Canada, let's try to generate area plots for the countries with the highest number of immigration to Canada. We can try to find these countries by sorting our data frame in descending order of cumulative total immigration from 1980 to 2013. We use the sort_values function to sort our data frame in descending order, and here is the result. So it turns out that India, followed by China, then the UK, Philippines, and Pakistan are the top 5 countries with the highest number of immigration to Canada. So can we now go ahead and generate the area plots using the first 5 rows of this data frame? Not quite yet. First, we need to create a new data frame of only these 5 countries, and we need to exclude the total column. More importantly, to generate the area plots for these countries, we need the years to be plotted on the horizontal axis and the annual immigration to be plotted on the vertical axis. Note that matplotlib plots the indices of a data frame on the horizontal axis. And with the data frame as shown, the countries will be plotted on the horizontal axis. So to fix this, we need to take the transpose of the data frame. Let's see how we can do this. After we sort our data frame in descending order of cumulative annual immigration, we create a new data frame of the top 5 countries, and let's call it df_top5. We then select only the columns representing the years 1980 to 2013 in order to exclude the total column before applying the transpose method. The resulting data frame is exactly what we want, with 5 columns, where each column represents one of the top 5 countries, and the years being the indices. Now we can go ahead and call the plot function on data frame df_top5 to generate the area plots. To do that, first we import matplotlib as MPL and its scripting interface as PLT. Then we call the plot function on the data frame df_top5, and we set kind equals area to generate an area plot. Then to complete the figure,
we give it a title, and we label its axes. Finally, we call the show function to display the figure. Note that here we're generating the area plot using the inline backend. And there you have it, an area plot that depicts the immigration trend of the 5 countries with the highest immigration to Canada from 1980 to 2013. In the lab session, we explore area plots in more details, so make sure to complete this module's lab session. And with this, we conclude our video on area plots. I'll see you in the next video. In this video, we will learn about another visualization tool, the histogram, and we will learn how to create it using matplotlib. Let's start by defining what a histogram is. A histogram is a way of representing the frequency distribution of a numeric dataset. The way it works is it partitions the spread of the numeric data into bins, assigns each data point in the dataset to a bin, and then counts the number of data points that have been assigned to each bin. So the vertical axis is actually the frequency or the number of data points in each bin. For example, let's say the range of the numeric values in the dataset is 34,129. Now the first step in creating the histogram is partitioning the horizontal axis in, say, 10 bins of equal width. And then we construct the histogram by counting how many data points have a value that is between the limits of the first bin, the second bin, the third bin, and so on. Say the number of data points having a value between 0 and 3,413 is 175. Then we draw a bar of that height for this bin. We repeat the same thing for all the other bins. And if no data points fall into a bin, then that bin would have a bar of height 0. So how do we create a histogram using matplotlib? Before we go over the code to do that, let's do a quick recap of our dataset. Recall that each row represents a country and contains metadata about the country, such as where it is located geographically and whether it is developing or developed. Each row also contains numerical figures of annual immigration from that country to Canada from 1980 to 2013. Now let's process the data frame so that the country name becomes the index of each row. This should make retrieving rows pertaining to specific countries a lot easier. Also, let's add an extra column which represents the cumulative sum of annual immigration from each country from 1980 to 2013. So for Afghanistan, for example, it is 58,639 total, and for Albania, it is 15,699, and so on. And let's name our data frame df_Canada. So now that we know how our data is stored in the data frame df_Canada, say we're interested in visualizing the distribution of immigrants to Canada in the year 2013. The simplest way to do that is to generate a histogram of the data in column 2013, and let's see how we can do that with matplotlib. First, we import matplotlib as MPL and its scripting interface as PLT. Then we call the plot function on the data in column 2013, and we set kind equals hist to generate a histogram. Then to complete the figure, we give it a title and we label its axes. Finally, we call the show function to display the figure. And there you have it, a histogram that depicts the distribution of immigration to Canada in 2013. But notice how the bins are not aligned with the tick marks on the horizontal axis. This can make the histogram hard to read. So let's try to fix this in order to make our histogram more effective. One way to solve this issue is to borrow the histogram function from the NumPy library. So as usual, we start by importing matplotlib and its scripting interface, but this time we also import the NumPy library. Then we call the NumPy histogram function on the data in column 2013. What this function is going to do is it is going to partition the spread of the data in column 2013 into 10 bins of equal width, compute the number of data points that fall in each bin, and then return this frequency of each bin, which we're calling count here, and the bin edges, which we're calling bin_edges. We then pass these bin edges as an additional parameter in our plot function to generate the histogram. And there you go. A nice looking histogram whose bin edges are aligned with the tick marks on the horizontal axis. In the lab session, we explore histograms in more details, so make sure to complete this module's lab session. And with this, we conclude our video on histograms. I'll see you in the next video. In this video, we will learn about an additional visualization tool, namely the bar chart, and learn how to create it using matplotlib. A bar chart is a very popular visualization tool. Unlike a histogram, a bar chart, also known as a bar graph, is a type of plot where the length of each bar is proportional to the value of the item that it represents. It is commonly used to compare the values of a variable at a given point in time. For example, say we're interested in visualizing in a discrete fashion how immigration from Iceland to Canada looked like from 1980 to 2013. One way to do that is by building a bar chart where the height of the bar represents the total immigration from Iceland to Canada in a particular year. So how do we do that with matplotlib? Before we go over the code to do that, let's do a quick recap of our data set. Recall that each row represents a country and contains metadata about the country, such as where it is located geographically and whether it is developing or developed. Each row also contains numerical figures of annual immigration from that country to Canada from 1980 to 2013. Now let's process the data frame so that the country name becomes the index of each row. This should make retrieving rows pertaining to specific countries a lot easier. Also, let's add an extra column which represents the cumulative sum of annual immigration from each country from 1980 to 2013. So for Afghanistan, for example, it is 58,639 total, and for Albania, it is 15,699, and so on. And let's name our data frame df_Canada. So now that we know how our data is stored in the data frame df_Canada, let's see how we can use matplotlib to generate a bar chart to visualize how immigration from Iceland to Canada looked like from 1980 to 2013. As usual, we start by importing matplotlib and its scripting interface. Then we use the years variable to create a new data frame. Let's name it df_Iceland, which includes the data pertaining to annual immigration from Iceland to Canada and excluding the total column. Then we call the plot function on df_Iceland, and we set kind equals bar to generate a bar chart. Then to complete the figure, we give it a title, and we label its axes. Finally, we call the show function to display the figure. And there you have it, a bar chart that depicts the immigration from Iceland to Canada from 1980 to 2013. By examining the bar chart, we notice that immigration to Canada from Iceland has seen an increasing trend since 2010. I'm sure that the curious among you are already wondering who the culprit behind this increasing trend is. In the lab session, we revealed the reason, and we also learned how to create a bar chart with horizontal bars. So make sure to complete this module's lab session. And with this, we conclude our video on bar charts. I'll see you in the next video. In this video, we will learn about another visualization tool, the pie chart, and we will learn how to create it using matplotlib. So what is a pie chart? A pie chart is a circular statistical graphic divided into slices to illustrate numerical proportion. For example, here is a pie chart of the Canadian federal election back in 2015, where the Liberals in red won more than 50% of the seats in the House of Commons. That is why the red color occupies more than half of the circle. So how do we create a pie chart with matplotlib? Before we go over the code to do that, let's do a quick recap of our data set. Recall that each row represents a country and contains metadata about the country, such as where it is located geographically and whether it is developing or developed. Each row also contains numerical figures of annual immigration from that country to Canada from 1980 to 2013. Now let's process the data frame so that the country name becomes the index of each row. This should make retrieving rows pertaining to specific countries a lot easier. Also, let's add an extra column which represents the cumulative sum of annual immigration from each country from 1980 to 2013. So for Afghanistan, for example, it is 58,639 total, and for Albania, it is 15,699, and so on. And let's name our data frame df_Canada. So now that we know how our data is stored in the data frame df_Canada, say we're interested in visualizing a breakdown of immigration to Canada continent-wise. The first step is to group our data by continent using the continent column, and we use pandas for this. We call the pandas group by function on df_Canada, and we sum the number of immigrants from the countries that belong to the same continent. Here is the resulting data frame, and let's name it df_continents. The resulting data frame has 6 rows, each representing a continent, and 35 columns, representing the years from 1980 to 2013, plus the cumulative sum of immigration for each continent. And now, we're ready to start creating our pie chart. We start with the usual, importing matplotlib as MPL, and its scripting layer, the pyplot interface, as PLT. Then we call the plot function on column total of the data frame df_continents, and we set kind equals pi to generate a pie chart. Then to complete the figure, we give it a title. Finally, we call the show function to display the figure. And there you have it, a pie chart that depicts each continent's proportion of immigration to Canada from 1980 to 2013. In the lab session, we will go through the process of creating a very professional looking and aesthetically pleasing pie chart and transform the pie chart that we just created into one that looks like this. So make sure to complete this module's lab session. One last comment on pie charts. There are some very vocal opponents to the use of pie charts under any circumstances. Most argue that pie charts fail to accurately display data with any consistency. Bar charts are much better when it comes to representing the data in a consistent way and getting the message across. If you're interested in learning more about the arguments against pie charts, here is a link to a very interesting article that discusses very clearly the flaws of pie charts. You can also find the link under the video. And with this, we conclude our video on pie charts. I'll see you in the next video.
In this video, we will learn about another visualization tool, the box plot, and how to create one using matplotlib. So, what is a box plot? A box plot is a way of statistically representing the distribution of given data through 5 main dimensions. The first dimension is minimum, which is the smallest number in the sorted data. Its value can be obtained by subtracting 1.5 times the IQR, where IQR is interquartile range from the first quartile. The second dimension is first quartile, which is 25% of the way through the sorted data. In other words, a quarter of the data points are less than this value. The third dimension is median, which is the median of the sorted data. The fourth dimension is third quartile, which is 75% of the way through the sorted data. In other words, 3/4 of the data points are less than this value. And the final dimension is maximum, which is the highest number in the sorted data, where maximum equals third quartile summed with 1.5 multiplied by IQR. Finally, box plots also display outliers as individual dots that occur outside the upper and lower extremes. Now let's see how we can create a box plot with matplotlib. Before we go over the code to do that, let's do a quick recap of our data set. Recall that each row represents a country and contains metadata about the country, such as where it is located geographically and whether it is developing or developed. Each row contains numerical figures of annual immigration from that country to Canada from 1980 to 2013. Now let's process the data frame so that the country name becomes the index of each row. This should make retrieving rows pertaining to specific countries a lot easier. Also, let's add an extra column which represents the cumulative sum of annual immigration from each country from 1980 to 2013. So for Afghanistan, for example, it is 58,639 total, and for Albania, it is 15,699, and so on. And let's name our data frame df_Canada. So now that we know how our data is stored in the data frame df_Canada, say we're interested in creating a box plot to visualize immigration from Japan to Canada. As with other tools that we learned so far, we start by importing matplotlib as MPL and the pyplot interface as PLT. Then we create a new data frame of the data pertaining to Japan, and we're excluding the column total using the years variable. Then we transpose the resulting data frame to make it in the correct format to create the box plot. Let's name this new data frame df_Japan. Following that, we call the plot function on df_Japan and we set kind equals box to generate a box plot. Then, to complete the figure, we give it a title and we label the vertical axis. Finally, we call the show function to display the figure. And there you have it, a box plot that provides a pleasing distribution of Japanese immigration to Canada from 1980 to 2013. In the lab session, we explore box plots in more detail and learn how to create multiple box plots as well as horizontal box plots, so make sure to complete this module's lab session. And with this, we conclude our video on box plots. See you in the next video.
In this video, we will learn about an additional visualization tool, the scatter plot, and we will learn how to create it using matplotlib. So what is a scatter plot? A scatter plot is a type of plot that displays values pertaining to typically two variables against each other. Usually it is a dependent variable to be plotted against an independent variable in order to determine if any correlation between the two variables exists. For example, here is a scatter plot of income versus education. And by looking at the plotted data, one can conclude that an individual with more years of education is likely to earn a higher income than an individual with fewer years of education. So how can we create a scatter plot with matplotlib? Before we go over the code to do that, let's do a quick recap of our data set. Recall that each row represents a country and contains metadata about the country, such as where it is located geographically and whether it is developing or developed. Each row also contains numerical figures of annual immigration from that country to Canada from 1980 to 2013. Now let's process the data frame so that the country name becomes the index of each row. This should make retrieving rows pertaining to specific countries a lot easier. Also, let's add an extra column which represents the cumulative sum of annual immigration from each country from 1980 to 2013. So for Afghanistan, for example, it is 58,639 total, and for Albania, it is 15,699, and so on. And let's name our data frame df_Canada. So now that we know how our data is stored in the data frame df_Canada, say we're interested in plotting a scatter plot of the total annual immigration to Canada from 1980 to 2013. To be able to do that, we first need to create a new data frame that shows each year and the corresponding total number of immigration from all the countries worldwide as shown here. Let's name this new data frame df_total. In the lab session, we will walk together through the process of creating df_total from df_Canada, so make sure to complete this module's lab session. Then we proceed as usual. We import matplotlib as MPL and its scripting layer, the pyplot interface, as PLT. Then we call the plot function on the data frame df_total, and we set kind equals scatter to generate a scatter plot. Now, unlike the other data visualization tools, where only passing the kind parameter was enough to generate the plot, with scatter plots, we also need to pass the variable to be plotted on the horizontal axis as the x parameter and the variable to be plotted on the vertical axis as the y parameter. In this case, we're passing column year as the x parameter and column total as the y parameter. Then, to complete the figure, we give it a title and we label its axes. Finally, we call the show function to display the figure. And there you have it, a scatter plot that shows total immigration to Canada from countries all over the world from 1980 to 2013. The scatter plot clearly depicts an overall rising trend of immigration with time. In the lab session, we explore scatter plots in more details and learn about a very interesting variation of the scatter plot, a plot called the bubble plot, and we learn how to create it using matplotlib. So make sure to complete this module's lab session. And with this, we conclude our video on scatter plots. I'll see you in the next video. In this video, we will learn about what some consider an advanced visualization tool, namely the waffle chart. So what is a waffle chart? A waffle chart is a great way to visualize data in relation to a whole or to highlight progress against a given threshold. For example, say immigration from Scandinavia to Canada is comprised only of immigration from Denmark, Norway, and Sweden. And we're interested in visualizing the contribution of each of these countries to the Scandinavian immigration to Canada. The main idea here is for a given waffle chart whose desired height and width are defined, the contribution of each country is transformed into a number of tiles that is proportional to the country's contribution to the total. So the more the contribution, the more the tiles, resulting in what resembles a waffle when combined, hence the name waffle chart. Unfortunately, matplotlib does not have a built-in function to create waffle charts. Therefore, in the lab session, I'll walk you through the process of creating your own Python function to create a waffle chart. So it's really important that you complete this module's lab session. And with this, we conclude our video on waffle charts. I'll see you in the next video. In this video, we will learn about another advanced visualization tool, the word cloud. So what is a word cloud? A word cloud is simply a depiction of the importance of different words in a body of text. A word cloud works in a simple way. The more a specific word appears in a source of textual data, the bigger and bolder it appears in the word cloud. So given some text data on recruitment, for example, we generate a cloud of words like this. This cloud is telling us that words such as recruitment, talent, candidates, and so on are the words that really stand out in these text documents. And assuming that we didn't know anything about the content of these documents, a word cloud can be very useful to assign a topic to some unknown textual data. Unfortunately, just like waffle charts, matplotlib does not have a built-in function to generate word clouds. However, luckily, a Python library for cloud word generation that was created by Andreas Muller is publicly available. So in the lab session, we will learn how to use Muller's word cloud generator, and we will also create interesting word clouds superimposed on different background images. So make sure to complete this module's lab session. And with this, we conclude our video on word clouds. I'll see you in the next video. In this video, we will learn about a new visualization library in Python, which is Seaborn. Although Seaborn is another data visualization library, it is actually based on matplotlib. It was built primarily to provide a high-level interface for drawing attractive statistical graphics such as regression plots, box plots, and so on. Seaborn makes creating plots very efficient. Therefore, with Seaborn, you can generate plots with code that is 5 times less than with matplotlib. Let's see how we can use Seaborn to create a statistical graphic. Let's look into regression plots. Let's say we have a data frame called df_total of total immigration to Canada from 1980 to 2013, with the year in one column and the corresponding total immigration in another column. And say we're interested in creating a scatter plot along with a regression line to highlight any trends in the data. With Seaborn, you can do all this with literally one line of code. The way to do this, we first import Seaborn, and let's import it as SNS. Then we call the Seaborn regplot function. We basically tell it to use the data frame df_total and to plot the column year on the horizontal axis and the column total on the vertical axis. And the output of this one line of code is a scatter plot with a regression line, and not just that, but also 95% confidence interval. Isn't that really amazing? Seaborn's regplot function also accepts additional parameters for any personal customization. So you can change the color, for example, using the color parameter. Let's go ahead and change the color to green. Also, you can change the marker shape as well using the marker parameter. Let's go ahead and change the shape of our markers to a plus marker instead of the default circular marker. In the lab session, we explored regression plots with Seaborn in more details, so make sure to complete this module's lab session. And with this, we conclude our short introduction to Seaborn and regression plots. I'll see you in the next video. In this video, we will learn about a very interesting data visualization library in Python, which is Folium. Folium is a powerful data visualization library in Python that was built primarily to help people visualize geospatial data. With Folium, you can create a map of any location in the world as long as you know its latitude and longitude values. You can also create a map and superimpose markers as well as clusters of markers on top of the map for cool and very interesting visualizations. You can also create maps of different styles such as street level map, a stamen map, and a couple others, which we will look into in just a moment. Creating a world map with Folium is pretty straightforward. You simply call the map function, and that is all. What is really interesting about the maps created by Folium is that they are interactive, so you can zoom in and out after the map is rendered, which is a super useful feature. The default map style is the OpenStreetMap, which shows a street view of an area when you're zoomed in and shows the borders of the world countries when you're zoomed all the way out. Now let's create a world map centered around Canada. To do that, we pass in the latitude and the longitude values of Canada using the location parameter. And with Folium, you can set the initial zoom level using the zoom start parameter. Now I say initial because you can easily change the zoom level after the map is rendered by zooming in or zooming out. You can play with this parameter to figure out what the initial zoom level looks like for different values. Now let's set the zoom level for our map of Canada to 4. And there you go. Here is a world map centered around Canada. Another amazing feature of Folium is that you can create different map styles using the tiles parameter. Let's create a stamen toner map of Canada. This style is great for visualizing and exploring river meanders and coastal zones. Another style is stamen terrain. Let's create a map of Canada in stamen terrain. This style is great for visualizing hill shading and natural vegetation colors. And with this, we conclude our introduction to Folium. I'll see you in the next video. In this video, we will continue working with the Folium library and learn how to superimpose markers on top of a map for interesting visualizations. In the previous video, we learned how to create a world map centered around Canada. So let's create this map again and name it Canada_map this time. Ontario is a Canadian province and contains about 40% of the Canadian population. It is considered Canada's most populous province. Let's see how we can add a circular mark to the center of Ontario. To do that, we need to create what is called a feature group. Let's go ahead and create a feature group named Ontario. Now, when a feature group is created, it is empty. And that means what's next is to start creating what is called children and adding them to the feature group. So let's create a child in the form of a red circular mark located at the center of the Ontario province. We specify the location of the child by passing in its latitude and longitude values. And once we're done adding children to the feature group, we add the feature group to the map. And there you have it, a red circular mark superimposed on top of the map and added to the center of the province of Ontario. Now, it would be nice if we could actually label this marker in order to let other people know what it actually represents. To do that, we simply use the marker function and the pop-up parameter to pass in whatever text we want to add to this marker. And there you go. Now our marker displays Ontario when clicked on. In the lab session, we will look into a real-world example and explore crime rate in San Francisco. We will create a map of San Francisco and superimpose thousands of these markers on top of the map. Not just that, but I'll show you how you can also create clusters of markers in order to make your map look less congested. This module's lab session is a very interesting one, so please make sure to complete it. And with this, we conclude our video on adding markers to maps with Folium. I'll see you in the next video. In this video, we will learn how to create a special type of map called choropleth map with Folium. I'm sure that most of you have seen maps similar to this one and this one. These are what we call choropleth maps. So what is a choropleth map? A choropleth map is a thematic map in which areas are shaded or patterned in proportion to the measurement of the statistical variable being displayed on the map, such as population density or per capita income. The higher the measurement, the darker the color. So the map to the left is a choropleth map of the world showing infant mortality rate per 1,000 births. The darker the color, the higher the infant mortality rate. According to the map, African countries have very high infant mortality rates, with some of them reporting a rate that is higher than 160 per 1,000 births. Similarly, the map to the right is a choropleth map of the US showing population per square mile by state. Again, the darker the color, the higher the population. According to the map, states in the eastern part of the US tend to be more populous than states in the western part, with California being an exception. In order to create a choropleth map of a region of interest, Folium requires a GeoJSON file that includes geospatial data of the region. For a choropleth map of the world, we would need a GeoJSON file that lists each country, along with any geospatial data to define its borders and boundaries. Here is an example of what the GeoJSON file would include about each country. The example here pertains to the country Brunei. As you can see, the file includes the country's name, its ID, geometry shape, and the coordinates that define the country's borders and boundaries. So let's see how we can create a choropleth map of the world like this one showing immigration to Canada. Before we go over the code to do that, let's do a quick recap of our data set. Recall that each row represents a country and contains metadata about the country, such as where it is located geographically and whether it is developing or developed. Each row also contains numerical figures of annual immigration from that country to Canada from 1980 to 2013. Now let's process the data, and let's add an extra column which represents the cumulative sum of annual immigration from each country from 1980 to 2013. So for Afghanistan, for example, it is 58,639 total, and for Albania, it is 15,699, and so on. And let's name our data frame df_Canada. So now that we know how our data is stored in the data frame df_Canada, let's see how we can generate a choropleth map of the world showing immigration to Canada. We should be experts now in creating world maps with volume. So let's go ahead and create a world map, but this time let's use the Mapbox Bright tile set. The result is a nice world map displaying the name of every country. Now to convert this map into a choropleth map, we first define a variable that points to our GeoJSON file. Then we apply the choropleth function to our world map, and we tell it to use the columns country and total in our df_Canada data frame, and to use the country names to look up the geospatial information about each country in the GeoJSON file. And there you have it, a choropleth map of Canada showing the intensity of immigration from different countries worldwide. In the lab session, we explore choropleth maps in more details, so please make sure to complete this module's lab session. And with this, we conclude our video on choropleth maps.
In this video, we are going to see how an interactive data application can help improve business performance and the tools available for building the application. With real-time visuals on the dashboard, understanding a business's moving parts becomes easy. Based on the report type and data, suitable graphs and charts can be created in one central location. This provides an easy way for stakeholders to understand what is going right, wrong, and what needs to be improved. Getting the big picture in one place can help businesses make informed decisions. This improves business performance. In general, the best dashboards answer critical business questions. Let us say you are assigned a task to monitor and report the performance of domestic U.S. flights. Following are the yearly review report items. The top 10 airline carriers in the year 2019 in terms of number of flights. The number of flights in 2019 split by month. And the number of travelers from the state of California to other states split by distance group. Let us look at the two ways of presenting the report. For this Type 1 report, the information is presented through tables, with inference from tables documented for reference. For Report Type 2, we are presenting the same report in the dashboard format. Hovering over each chart will provide details about the data points. In the bottom sunburst chart, you can click on different numbers, drill down into levels, and get detailed information about each segment. Can you observe the difference in the presentation of the findings? And what if we need to get the report on the real-time data, not the static data? Also, presenting the result using tables and documents is time-consuming, less visually appealing, and more difficult to comprehend. A data scientist should be able to create and deliver a story around the findings in a way stakeholders can easily understand. With that in mind, dashboards are the way to go. Let us take a look at web-based dashboarding tool options available in Python. Dash is a Python framework for building web analytic applications. It is written on top of Flask, Plotly.js, and React.js. Dash is well suited for building data visualization apps with highly custom user interfaces. Panel works with visualizations from Bokeh, Matplotlib, HoloViews, and many other Python plotting libraries, making them instantly viewable either individually or when combined with interactive widgets that control them. Panel works equally well in Jupyter notebooks for creating quick data exploration tools. Panel can also be used in standalone deployed apps and dashboards, allowing you to easily switch between those contexts as needed. Voila turns Jupyter Notebooks into standalone web applications. It can be used with separate layout tools like Jupyter Flex or templates like Voila Viewtify. Streamlit can easily turn data scripts into shareable web apps with 3 main applications. Embrace Python scripting, treat widgets as variables, and reuse data and computation. There are other tools that can be used for dashboarding. Bokeh is a plotting library, a widget, and app library. It acts as a server for both plots and dashboards. Panel is one of the web-based dashboarding tools built on Bokeh. IBM Widgets provides an array of Jupyter-compatible widgets and an interface supported by many Python libraries, but sharing a dashboard requires a separate deployable server like Voila. Matplotlib is a comprehensive library for creating static, animated, and interactive visualizations in Python. Bowtie allows users to build dashboards in pure Python. Flask is a Python-backed web server that can be used to build arbitrary websites, including those with Python plots that function as Flask dashboards. Learn more about the tools from the source link. In this course, we will be focusing on Dash. In this video, we are going to provide an overview of the Plotly Python library. So, what is Plotly? Plotly is an interactive open-source plotting library that supports over 40 unique chart types. It is available in Python, R, and JavaScript. Plotly Python is built on top of Plotly JavaScript library and includes chart types like statistical, financial, maps, scientific, and three-dimensional data. The web-based visualizations created using Plotly Python can be displayed in Jupyter Notebook, saved to standalone HTML files, or served as part of pure Python-built web applications using Dash. The focus of this lesson will be on 2 of the Plotly submodules, Plotly Graph Objects and Plotly Express. Plotly Graph Objects is the low-level interface to figures, traces, and layout. The Plotly Graph Objects module provides an automatically generated hierarchy of classes, figures, traces, and layout called graph objects. These graph objects are used for representing figures with a top-level class plotly.graph_objects.figure. Plotly expresses a high-level wrapper for Plotly. It is a recommended starting point for creating most common figures provided by Plotly using a more simple syntax. It uses graph objects internally. Let us see how to use plotly.graph_objects submodule by creating a simple line chart. First, import the required packages. Here we are importing graph objects as Go. Then generate sample data using NumPy. The plotly.graph contains a JSON object which has a dictionary structure. Since we imported Plotly graph objects as Go in the previous slide, Go will be the JSON object. The chart can be plotted by updating the values of the Go object keywords. We will create the figure by adding a scatter type trace. Next, the layout of the figure is updated using the update layout method. Here we are updating the x-axis, y-axis, and chart title. This is the plotted figure. Now we will create the same line chart using Plotly Express. In Plotly Express, the entire line chart can be created using a single command. Visualization is automatically interactive. Plotly Express makes visualization easy to create and modify. And now it's time to play with the Plotly library. Next is going to be a lab session. We will be using the airline reporting database from Data Asset Exchange to demonstrate how to use Plotly Graph Objects and Express for creating charts. Here is a quick overview of the airline reporting dataset. The reporting carrier on-time performance dataset contains information on approximately 200 million domestic U.S. flights reported to the United States Bureau of Transportation Statistics. The dataset contains basic information about each flight, such as date, time, departure airport, arrival airport, and if applicable, the amount of time the flight was delayed and information about the reason for the delay. Now let us start the lab. In this video, we are going to see an overview of Dash library. Dash is an open-source user interface Python library for creating reactive, web-based applications. It is enterprise-ready and a first-class member of Plotly's open-source tools. Dash applications are web servers running Flask and communicating JSON packets over HTTP requests. Dash's front-end renders components using React.js. It is easy to build a graphical user interface using Dash as it abstracts all technologies required to build the applications. Dash is declarative and reactive. Dash output can be rendered in web browser and can be deployed to servers. Dash uses a simple reactive decorator for binding code to the UI. This is inherently mobile and cross-platform ready. Let us say you are planning to create an application to answer a business question. As a first step, you need to determine the layout of the application. Decide which chart to use and where to place, for example. This is called layout part in Dash. The second part is to add interactivity to the application. There are two components of Dash. First is core components. We can import core components as DCC using the import statement. Next is HTML components. We can import HTML components as HTML using this import statement. Let us explore these further. The dash_HTML_components library has a component for every HTML tag. You can compose your layout using Python structures with the dash-HTML-components library. The dash_HTML_components library also provides classes for all of the HTML tags. The keyword arguments describe the HTML attributes like style, class name, and ID. No knowledge of HTML or CSS is required, but can help in styling the dashboards. Let us see an example of how to use HTML components. We start by creating a Dash application. From here, we create division in our application layout and then add components to it. In the outer layer division, we first provide a name for our application using the HTML heading component h1. The style parameter is used to change the font color, size, and border of the heading. Next, we will add paragraph content to the page using an HTML paragraph component p. Division can be created inside the outer division. Here we are providing division content as "This is a new division" and styling it using style parameter components. To put all this together, in the application layout, create an HTML division and add components. Multiple divisions can be added to the outer application layout. The dash_core_components describe higher-level components that are interactive and generated with JavaScript, HTML, and CSS through the React.js library. Some examples of core components are creating a slider, input area, check items, and date picker. You can explore other components using the reference link provided at the end of the slide. Now let us see how to add a slicer and dropdown to the application. For the dropdown, we use the dcc.dropdown component. We will create a dropdown list under the options parameter as a dictionary. Label will hold the dropdown display label name and value will hold the value of the label. We can also provide a default dropdown display label using value parameter. For the slider, we use the dcc.slider component and provide min and max value to the slider. The marks parameter is used for adding a slide marker and value parameter for adding default value. In this video, we will see how to connect core and HTML components using callbacks. A callback is a Python function that is automatically called by dash whenever an input component's property changes. Callback function is decorated with @app.callbackDecorator. So what does this decorator tell dash? Basically, whenever there is a change in the input component value, the callback function wrapped by the decorator is called, followed by the update to the output component children in the application layout. Let us look at the callback function skeleton. First, create a function that will perform operations to return the desired result for the output component. Decorate the callback function with @app.callbackDecorator. This takes two parameters. Output, this sets the result returned from the callback function to a component ID. And input, this sets the input provided to the callback function to a component ID. From here, we will connect the input and output to desired properties. We will see this in action with an example using the airline data. The use case here is to extract the top 10 airline carriers in the provided input year selected by the number of flights. Based on the input year, the output will change. First, we import the required packages. As seen before, we will import pandas, dash core, and HTML components. The new entry here has dash dependencies. From dash dependencies, we will import input and output that we will use in the callback function. We read the airline data into the pandas data frame. We load our data frame at the start of the app, and it can be read inside the callback function. We will start designing the dash application layout by adding components. First, we will provide the title to the dash app using the HTML heading component, h1, and style it using the style parameter. Next, we will add an HTML division and text input core component. In dash, the inputs and outputs of the application are simply the properties of a particular component. In this example, our input is the value property of the component that has the ID input-year. By default, the value has 2010. We will update this value in our callback function. Lastly, we will add a division with a graph core component. The core component has bar-plot as ID, which we will update inside the callback function. Note the component IDs. We will add a callback decorator app.callback. Input to the callback will be the component with ID input-year and property value. Output to the callback will be the component with ID bar-plot and property figure. Component_ID and component_property keywords are optional and are included here for clarity. Next, we will define the callback function get_graph. The entered year will be the input. Using the year, we extracted the required information from data. Finally, the application layout graph is updated. And lastly, we will run the application. This is the output of the code. Our initial input year is 2010. Note that as we update the year, the graph is updated for that year. Second example is a callback with two inputs. It is similar to the one input callback except for a few changes. We will add a division with one more text input with the component ID input-AB. Now we will add the new input and component ID input-AB to the decorator inside the list. Next, we will define callback function get_graph. This takes the entered year and the entered state as input parameters. Computation is performed to extract the information and the application layout is updated with the graph. This is the output of the code. Our initial input year is 2010 and state is AL, which is Alabama. As I updated the year and state, you can observe that the graph is updated in parallel. Now let us start the lab. Congratulations on making it this far! Successfully completing this capstone project will earn you the Data Analyst Professional Certificate. This capstone provides you a practical hands-on experience to demonstrate all of the skills you have picked up so far in this professional certificate program. As part of the capstone project, you will take on the role of a data analyst with a global IT and business services firm. In this role, you will be analyzing several data sets to help identify trends for emerging technologies. In Module 1, you will collect data for the technology skills that are in demand from various sources, including job postings, blog posts, and surveys. In Module 2, you will take the collected data and prepare it for analysis by using data wrangling techniques, like finding duplicates, removing duplicates, finding missing values, and inputting missing values. You'll continue to Module 3 and apply statistical techniques to analyze the data and identify insights and trends like, what are the top programming languages that are in demand? What are the top database skills that are in demand? What are the most popular IDEs? And demographic data like gender and age distribution of developers. In Module 4, you'll focus on choosing an appropriate visualization based on the data you want to present, using charts, plots, and histograms to help reveal your findings and trends. In Module 5, you will employ Cognos to create interactive dashboards to help you analyze and present the data dynamically. And in the final module, you will use your storytelling skills to provide a narrative and present the findings of your analysis. You will be provided with a presentation template to begin the process and to help you create a compelling story and present your findings. Each module includes a short quiz to test your knowledge. You will be evaluated based on the quizzes in each module. The dashboard and the storytelling presentation you create will be reviewed and graded by your peers. To begin, I recommend taking a few minutes to explore the course site. Review the material we'll cover each week and preview the assignments you'll need to complete to pass the course. Click Discussions to see forums where you can discuss the course material with fellow learners and course team. If you have questions about course content, please post them in the forums to get help from others in the course community. For technical problems with the Coursera platform, visit the Learner Help Center. We are excited to have you join us and hope you enjoy the course. Good luck, and let's get started. While finding and cleaning data is an important first step in data analysis, a concept can be lost if you are not able to organize and represent the findings effectively to your audience. In this video, you will learn how to represent your findings by focusing on specific elements to create a successful data findings report. After the data has been collected, cleaned, and organized, the work of interpretation begins. You are now able to obtain a complete view of the data and hopefully answer the questions that were formed before starting the analysis. Now you typically begin to compose a findings report that explains what was learned. Depending on the stakeholders and how they received the information, the report could vary in form. This could include a paper-style report, a slideshow presentation, or maybe even both. The findings report is a crucial part of data analysis as it conveys what was discovered. When beginning this process, the collected data and information may seem a little overwhelming. The best way to get through this block is to begin by creating an outline. By completing an outline, you can then get a complete picture and begin to write in a precise but simple manner. While there are many different formats for creating a data-driven presentation, we have created a simple outline that is easy to follow, yet effective. When creating your outline, always remember to structure it towards your audience and create a presentation that is appropriate for your situation. You first begin with your cover page. This beginning section will have the title of your presentation, your name, and then the date. The next section in your outline will be an executive summary and then the table of contents. The table of contents will contain the sections and subsections of your report in order to give your audience an overview of the contents. This also enables readers to go directly to a specific section that may be more important to them. Continue your presentation with the introduction, methodology, results, discussion, conclusion, and finally, the appendix. Note that the depth and length for each element may vary depending on the audience and format of report. The first step in creating your report is properly creating an executive summary. This summary will briefly explain the details of the project and should be considered a standalone document. This information is taken from the main points of your report, and while it is acceptable to repeat information, no new information is presented. The next section after the table of contents is the introduction. The introduction explains the nature of the analysis, states the problem, and gives the questions that were to be answered by performing the analysis. The next section is methodology. Methodology explains the data sources that were used in the analysis and outlines the plan for the collected data. For example, was the cluster or regression method used to analyze the data? Next, we have the results section. This section goes into the detail of the data collection, how it was organized, and how it was analyzed. This portion would also contain the charts and graphs that would substantiate the results and call attention to more complex or crucial findings. By providing this interpretation of data, you are able to give a detailed explanation to the audience and convey how it relates to the problem that was stated in the introduction. Next, discuss the report findings and implications. For this section, you would engage the audience with a discussion of your implications that were drawn from the research. For example, let's say you were conducting research for top programming languages for college graduates. Would you find they need to learn multiple languages to remain competitive in the job market, or would one language always reign supreme? We have now reached the conclusion of the report findings. This final section should reiterate the problem given in the introduction and gives an overall summary of the findings. It would also state the outcome of the analysis and if any other steps would be taken in the future. And last, we have the appendix. This section would contain information that really didn't fit in the main body of the report, but you deemed it was still important enough to include. This type of information could include locations where the raw data was collected, or other details such as resources, acknowledgments, or references. In this video, we learned about the important elements in creating a successful data findings report. In the next video, we will learn the best practices when presenting your findings. Okay, you've spent weeks, maybe months, studying the data, and the time has come to report your findings. The questions have been answered, and you feel good about the story. So how will you speak to your audience so they leave with the intended message? In this video, learn how to present your findings in a way that will engage and keep the attention of your audience. Delivering data-driven presentations may seem easy, but there are a few important factors to remember in accurately conveying your message. Make sure charts and graphs are not too small and are clearly labeled. Use the data only as supporting evidence. Share only one point from each chart or graph, and eliminate data that does not support the key message. Have you ever sat through a presentation and the information being presented was difficult to read or understand? While this may seem apparent, small charts and labels can be easily overlooked. Make sure to test the visualizations by sitting at different distances like your audience, and if the data cannot be seen clearly, then maybe a redesign should be considered. When preparing the report, you may feel the only way to explain the findings is to pack the slides with data. While this may seem sensible as a data analyst, your audience will probably not appreciate the intricacies of the data and just see a pile of numbers. To resolve this issue, begin by forming the key messages that need to be conveyed to the audience and build the story around these messages. After forming the outline, go back and insert the data to support your findings. By not relying heavily on the data and using this method to create the presentation, you will create a story that is engaging and interesting to your audience. Presenting your data using charts and graphs is the best way to get your message across. However, if you are supplying too much information, it can be confusing. For example, look at this pie chart. Can you decipher what the key message is and what the presenter is trying to convey? In the example, the chart has so much information it is hard to determine what point the presenter is trying to make and what the focus should be for the audience. By sticking with one idea and not summarizing multiple points into one visualization, you are able to accurately convey the idea to the audience and avoid any confusion. Data analysts can spend months researching data. However, some items that seem interesting to the analyst may not be relevant to the project. Trying to explain every little detail to your audience and not recognizing irrelevant data could damage the key message. By eliminating this unnecessary data and highlighting only data points that support your key ideas, you will keep the presentation clear and concise. In this video, we learned about creating a data-driven presentation that will keep your audience engaged, and how to deliver a clear and concise message.